Okay, can everyone see my slides? No? Yes? Okay. All right, one sec. Okay, well, welcome everyone to the 4th annual Neuro-Symbolic AI Summer School. I'm Alex Gray. I'm the head of the Centaur AI Institute, which is putting this on. So let me first thanks everyone. So this program was built by this program committee. Thanks to Luis, by the way, and Key, top people in Neuro-Symbolic AI. Luis, you may know, both of them have spoken in our past summer schools, but one of the pioneers of Neuro-Symbolic AI. And on the logistics, many of you have already seen Ken online. He'll be the technical director of this event. Assisting him will be Kevin. And Olga is our head of operations at the Institute, and she'll be helping with Q&A. Okay. So now, one second. Okay. All right. Well, now many of you are here because you already know about Neuro-Symbolic AI, of course, but so this is at least a reminder for many. But if you're new to Neuro-Symbolic AI, let me give you some motivation. Well, first of all, is AI solved? You might think so. Reading news headlines and so on in the popular press, but it's far from true. Now, we have lots of serious issues still open. Of course, one of the most prominent ones is errors due to hallucinations. I sort of put this in the same category. I put two things in the same category. The fact that there are errors is one thing, but sort of compounding that is the fact of being a black box, which means you actually don't know how to fix those errors, okay, except in a very indirect way. And, you know, some people think, oh, this will like go away, or maybe it's not that big a problem. Well, it sort of is a problem. You can read lots of things about this. So second one, arguably, in some sense, the deepest one, can't reason. Now, this is confusing because you keep reading about reasoning models. But see, for example, recent papers by Apple. And I'll say more about this. And reasoning, why is reasoning important? Well, for one thing, if it gets complex enough, your problem, then pattern recognition is insufficient. So it has to do with the complexity of the problem, but also if you've never seen the situation before, it's sort of your only path forward. If you just don't have any pattern in the past that looks very close to what you're seeing. So, and then the third one you could say is cost. And this is cost in terms of data. How many data do you need to learn? And closely related to that is the compute cost. So for those of you who are familiar, you have, if you want a sort of universal predictor as one terminology, then you need a non-parametric model, which means the size of your model grows with the number of data. So this is sort of the inherent relationship that sort of relates data and effectively compute cost. Okay, so now, are these issues, sort of little temporary issues? Okay. Well, not really, no. These are very deep issues, fundamental issues. So, and what's the cause of them? So, roughly speaking, why are you getting these errors, hallucinations? Well, it has something to do with the concepts underneath. And, if you're going to fix it, then those concepts need to be clear somehow to whoever's trying to fix it. So this is what motivates symbolic, just to give a little look ahead, because humans arguably understand things best, at least. Maybe we can understand other things, but we have gravitated toward things like language and math and so on, which are in symbols, to understand each other. Okay, so we use symbols to understand each other. Now, so arguably, for a model that we can understand, it sort of has to be symbolic. Okay, this is potentially a point of great debate. So, and we have a time for that, which is the end of the summer school in the panel. Okay. Now, something interesting here, which you may not know, which is a very nice result that we'll be showing in this summer school. Hallucinations actually can't be eliminated. Okay, you'll see that with the current kinds of models, that mathematically, provably. Now, reasoning. So why, are the so-called reasoning models, unable to go past a certain point? And well, because they're relying on past patterns, as I said. Now, when I say reasoning, this includes a bunch of things. This is a confusing topic, perhaps, because the word reasoning is overloaded. But there is a very formal sense of reasoning, deduction, at least. There's another one, you could say probabilistic reasoning, including causal reasoning. Planning can be seen as a special case of formal deductive reasoning. And because we include probabilistic reasoning here, we have to talk about uncertainty and being aware of your uncertainty, given uncertainty in your inputs. Okay, and there are at least two kinds of uncertainty. There's a sort of probabilistic kind, would include their subjective belief. It's also a very deep and old argument, but also ignorance, knowing what you know and what you don't know. And then, so all that is sort of in the bucket of, being able to reason clearly and properly. And we have a lot of work on that in various areas. Now, cost, as I mentioned, one way to understand why the costs of current approaches are so high, you could say, is to look to learning theory, and Les Valiant and others laid the groundwork for that. You could say, in lieu of reasoning, real reasoning, what are we doing? We're wanting to see all the possible patterns. In effect, that's one way to go about it. And you can kind of approximate that maybe with the entire internet, but you're paying a cost for that. Okay, so these are, okay, just to be a little provocative, I'll quote someone who is not shy about being provocative, Jan LeCun. So you can see a quote from him here. So you could say maybe these are the kinds of things that motivate this kind of quote. So, although I won't speak for him, into making the exact connection to these issues, and maybe one day we'll have Jan appear here and tell us in his own words. Now, so let me just put on the professorial hat for a second. So let's look back a little bit at history. Now, of course, if you've been around as long as I have, you lived part of this and you know this, but for many, if you've, of course, it's not necessarily obvious, but most AI researchers really have only kind of seen the current paradigm. This is because there's been an exponential growth in the number of AI researchers. I haven't seen many people talk about that. That's great, but it means you may not have really seen or digested the history, which, at the risk of sounding like a curmudgeon, is actually important. Why? Because what do you see here in this little cartoon history? Well, you see that there are multiple paradigms, even within one of the two major paradigms, KRR, machine learning. You have multiple paradigms that have waxed and waned. I don't want to say started and ended, because nothing ever really dies, and that's a good thing in research, because often, just like in fashion, it comes back, but it comes back with a twist. And you could say that's partly what's going on here. So this first paradigm, KRR, had a lot of good things about it and a lot of bad things, which is why it got sort of surpassed in terms of dominance. But a lot of people work on the deep issues of symbolic AI and continue to work on them. Now, so I use this to give as close a definition as we can to neurosymbolic AI. I say, and this is my definition, roughly speaking, what we really mean, or what I mean, is machine learning plus KRR. I mean, when I say KRR, you could say, well, you could sort of reason with vectors and so on. That's a kind of reasoning, maybe. But I mean symbolic KRR, which is the classic KRR, because of at least the human interpretability aspect of that I mentioned. So now, what motivates that? Well, it's because actually, if you just look at the pros and cons of symbolic AI and ML or statistical AI, they're remarkably complementary. So the weaknesses of one are the strengths of the other. In particular, because there's so much focus now on the weaknesses, you could say, of ML, we're sort of naturally reminded that things like abstract world knowledge, rigorous reasoning, and so on, these were the hallmarks of KRR and sort of the things missing today, or at least we need more of it. Okay, now some thoughtful people started thinking about neurosymbolic AI, or what's now called neurosymbolic AI. It's come under, you could say, various names, at least since 2000-ish, but probably there are arguments for why there is a form of neurosymbolic AI, or learning plus reasoning, all the way back to the very beginning of AI. So, these are cartoons, so really we're showing when things started to become a little bit more prominent. So now some people have been noticing this, and Gartner pleasantly has pointed this out, you could say. So the promise of neurosymbolic AI. And here's their famous hype cycle curve. Now, the very top of this curve is the peak hype point, and it goes downhill from there into a trough of disillusionment. Now, Neuro-Symbolic AI, they put it, I believe, 10 years out or so. So we have at least 10 years before we become hype. So now, in Gartner's view, now, all right. So as I said, it's actually a lot of stuff has sort of hit on these issues and under different names. And here are just at least a few of them. Many of people I consider real leaders in Neuro-Symbolic AI were or are part of the STAR AI community. So that stands for Statistical and Relational Learning, or AI. Inductive logic programming. There's a big movement around explainable AI, which is some aspect of this. All of these are overlapping. So, and these are various places where you'll find work that, and there are more. Okay, even now, even in core neural network, meaning in iClear and NeurIPS and so on. Okay, there are many approaches. So the plus part in this little equation is not at all obvious. It's still open. Okay, so how do you put these two things together in a way that somehow preserves the best of both? So this is the exciting, you could say, to me, this is the frontier of AI, is what is that plus? And it's a simple way to say it. Okay, now I try in my effort here, we try to highlight, put a spotlight on all of the major kind of ways that people are exploring this plus, you could say. Okay, I have my own research, and we do our own research. We explore our own kind of things that we think are promising. But I think it's, even for us, we like to look at everything and try to understand all different viewpoints that people are taking. And we believe it's important for everyone to see a little bit of everything. So now, and then I just want to say, a lot of people, and I agree with them, boil it down to, when the question comes up, what's missing from AI today? What's the big kind of next thing? World models is often what people say. You could say another way to express that is semantics. Have some understanding underneath conceptually, build up the right concepts. So now, again, that was always part of the symbolic AI approach. World models, that's what you're doing, typically in logic and so on. Okay, so that's a big part of why those ideas or new versions of those ideas are really getting into the deep issues that many people feel we need to address. Okay, now, why might you find this interesting? So if you're a researcher, well, many people feel, for these reasons, this kind of a thing, Neuro-Symbolic AI's collection of ideas, is somehow on the path to solving these key open issues of AI. Maybe also on the path to solving AGI. What is AGI? So we're starting to see actual definitions. So there's a lot of talk about them in companies, but hype aside, there, I think, are real ways to begin to talk about AGI formally. And but I think to make progress there, we can start with the G, general, and we talk about generalization in AI, and that's a beginning of how we can formalize. So I'll come to that in a second. Now, students, this is actually, you are actually, if you're a student, our most important audience here. You're going to develop the next generation of AI, and many people feel that sort of set of directions somehow lies in this zone. So if you, and this is relatively green field, that's where you want to look if you're a PhD student. Now, a lot's been done, but much more has not been done. Okay? Now, and then data scientists and AI developers, we are starting to get pretty interesting emerging tools in this area. Now, meaning they work, they can do some things better than existing ML tools. Okay. Now, why did we start these summer schools? Well, the first kind of big observation when I sort of got into this in a bigger way, which was in 2017, 2018. So is that this is difficult. This is particularly difficult to get into because, or at least the core reason that you've got these two big paradigms, and each, I find it interesting. It's like when people on the West Coast of the US versus the East Coast, sort of they have, some a slight suspicion of the other side, tend to minimize whatever's good about the other side. So, but a particular, I think, a particular kind of blind spot people have is people tend to think the other side is not that complicated, but it is. Trust me, both sides are complicated and very thick with lots of work, many deep principles. So if you're an ML person, logic, reasoning is not a one-liner. Okay, there's a lot to it. Same on the other side. Neural nets, machine learning, not a one-liner. So, so in order to work in this area effectively, or I would say the most, and make the deepest progress, you got to really understand as much as you can about both sides in a deep way. Now, and there's just a lot. Okay, so our attempt, of course, we can't teach you all of AI, but we can at least give you a crash course. This is what motivated this as a crash course, just to get you in the game, to kind of see some parts that we think are important as an invitation to go deeper. Okay, and because that's the big problem is we don't have time. We're working researchers and so on. Now, we split it into tutorials and talks. Tutorials are usually giving a very broad overview of a whole area. A talk is usually some focused result, but the line is thin often between them when we're working at the edge of research. So now, also, as I mentioned, there are many disparate approaches, taking, in some cases, quite different philosophical takes. So part of what we try to do is curate from many sources. And now there are new Neuro-Symbolic conferences, for example. NESI is the oldest. NESI is coming up. By the way, in Santa Cruz, NEWS is a new conference. It's exciting. Steve Muggleton has been running this ILP conference for a long time. Lots of great stuff there. Now, but it's increasingly, works that I consider in this space are increasingly appearing in all major AI conferences in ML and AI. So now, and even in other fields. So I try to monitor everything. And so this is in some sense a curation. So this is part education, part art museum, part intellectual party. So at a minimum, you're going to see a lot of interesting ideas, and hopefully just sit back, something will spark some new thinking in your mind. Now, and what's our goal here? Well, it's to accelerate progress in Neuro-Symbolic AI, because we think our hypothesis is that leads to smarter and safer AI, and maybe even AGI, say, the biggest goals in AI. So, great. So we've got this nice program. Let me give you a quick guide. So, I've touched upon many of these topics. And this is, warning, this is kind of very technical. Now, this is for a technical audience, but if you're looking for the big picture, so an excellent talk, I believe, will be next, right after this, Arvind's talk. The panel, we have a very exciting panel, and for all of us researchers, we should be inspired by folks like Rich Sutton, 2024 Turing Award winner, and also other luminaries on the panel, Arthur and Leo Demora. So, and we're going to talk very generally about the future of AI. So now tools, as I mentioned, so that's Friday morning. Check that out. Planning. Oh, I forgot to list mathematics here. Okay, planning. Mathematics is obvious. That's sort of the finale, right before the panel. And you can see here safety, interpretability. Even though I called out the theme of this event as being mathematics, reasoning, and planning, it's more just to draw attention to those areas that Neuro-Symbolic AI is having impact in. But really, all of the issues I mentioned, we touch on them in every summer school. Interpretability, out of distribution, generalization. This is the thing I want to mention that maybe is the thing many people are least familiar with here, as far as words at least. Compositionality. It may not be obvious, but compositionality, in my view, is key to out of distribution generalization, meaning being able to predict well in new situations that are potentially far from your training data. Okay, so do check those out. What is the deep nature of symbols and being, symbolic? So check out the talk by Peihao. And category theory, now this is scary. Okay, warning, this is like as scary as you can get mathematically. Okay, but I believe it's a big part of the future in AI in general, is ideas from category theory. So if you have the stomach for it, check that out. And then a very important, hallucinations. We have a remarkable result on efficiency by Felix. And reasoning sort of spread everywhere. Now, we offer a certificate, just to remind everyone, for those interested in that. That means see everything, and then we give you more information on that, how to get the certificate. Okay, just a little bit. I know I'm just going to be 1 or 2 more minutes at the last slide. So about the Institute. So we are a nonprofit. Our mission is smarter and safer AI. Hypothesis is that can be reached through Neuro-Symbolic AI. We're about research and education. We have, some full-time staff, but we also work with a lot of collaborators. We have about 40 people working in our collaborations. We're, gearing up to ultimately fund academics, so stay tuned. Now, how do you participate in, I'm going to call this a movement. So it's many people have told me they think of it as a movement. Now, number one thing is, hey, come hang out with us and do research, and especially PhD students. Let me call out our formal summer intern, Bowen Lee, very successful internship, and you'll see his work on Friday. Amazing results. And also Bowen, another Bowen, Duke, Kevin, who I mentioned. We have some very talented undergrads. Now, we also do grants with academics. So many ways to volunteer. We're all educational stuff we're putting together, moving toward the stuff you're seeing as an actual course, okay, 4-credit course through partner universities, something we're working on. Of course, events like this, Discord. Community, by the way, is on Discord. So if you want to sit or stay in tune with everything, that's the place to go, Discord. And many other things, including curation. By curation, I mean, find us stuff. It's getting to be a lot of stuff. So find us the coolest things. Let us know, hey, you guys should check out this paper. Maybe you should feature this paper in a summer school or something. And then open source software. And you'll be seeing that. That's a big effort how we're doing, is trying to do some very useful open source software and maintaining it. Okay, now I'll mention we also help startups. That's part of our, part of our mission, you could say, is to make this stuff get to the point, Neuro-Symbolic AI, I mean, get to the point of having commercial impact. So now, because there's a certain line we can't go beyond as a nonprofit, we do have other ways to work with startups. Now, and then journalists also, if you want more information about any of this stuff, let us know. Now, you can help us too. Corporate sponsorships is something we're formalizing, and you can donate money now. We have ways to do that now. So just some things coming up. We have a consortium we're putting together, and these are some of the topics. These are specialties within that consortium. This is aimed at industry to sort of help bring Neuro-Symbolic AI ideas to different industries, including executives. We'll be putting together a reading group. I'm going to come back to all of this at the very end of the summer school. I'm going to give you some pointers for how to join these things. And a lot more will be coming on the website, including our scientific advisory committee and a Neuro-Symbolic event calendar and so on. Okay, I think that's it. So I'm just going to leave this up and take any questions. Okay, now I'm looking at the questions. By the way the event will work, so we're going to have, you can watch on YouTube. You can also, and please follow along on Discord, and you can ask questions there or on YouTube. We're going to have our busy bees funneling those questions over to me, and then I will relating to the speaker. So, so, and by the way, I see there are a lot of people all over the world, so it's great to see all the folks around the globe. Okay, we have a question. How do you define neurosymbolic AI? A combination of symbolic and neural network / connectionist. Well, that's I want to make a comment about that. So this is a term, you know, if you've been around long enough in AI, you see lots of terms, you know, appear and so on, and sometimes we have multiple, you know, as I was pointing out, overlapping terms and so on. It's because nothing is ever perfect, and we're trying to capture something with a term like neurosymbolic AI, but it's never perfect. So this is in particular the neural part. So at least, of course, neural nets are the current major ML paradigm, you could say, but and there's something very interesting and important about them, but it's not the only way to learn. So the deeper issue to me is a more foundational kind of way to look at it is this is about fusing learning and reasoning. So learning can come in many forms, and it may, you know, the line between a neural net and something else is fuzzy, but it may not be a neural net. So the neural part to me is not, not necessarily the most important thing. It's learning. Symbolic, even symbolic, there are many sort of versions of symbolic, you could say. Often it's expressed as logic, but it could also be code or programs. And if you're familiar with things like the Curry-Howard isomorphism, those are equivalent. So you can equally well talk about learning programs, for example, so and be neurosymbolic. And then category theory is that, even a different generalization that you could say gives you even more abstract insights into symbolic. Okay, so but I argue there is something special about symbolic, which is has to do with the fact that humans can understand each other and understand a model if it's about crisp concepts. Okay, maybe I'm out of time. Okay. All right, so let me now pass it to Arvind. So we're going to do this in a very informal style in general. We do a fairly informal style in these summer schools. So all of these speakers really could be a headliner typically. We would give normally in an academic setting, we'd give a long kind of intro with all of their credentials and awards and so on, and all of them are generally very accomplished. So, but let me just say, our next speaker is Arvind. He's fantastic. He's been illuminating things for a lot of people. He's going to tell you some stuff that you should know, and you should follow his newsletter. He has a fantastic newsletter. And he's been saying a lot of things I wish I had said in the way that he says it. So let me just bring you the joy right now without further ado. Take it away, Arvind.
All right. Thank you, Alex. Really appreciate the informal vibe here. Happy to be here. Thank you so much for inviting me. Hi, everybody. And as Alex earlier said in the outline, this is going to be a high-level talk. But it is going to be hopefully provocative. That's kind of my job. That's why I get invited to things. So I'll plan to speak for about 25, 30 minutes, and then would love to have a little bit of discussion at the end. this picture is just a teaser. I'll get to this picture near the end of the talk. The point of the talk today is to think about the speed of progress, both within AI research and when AI is applied to other scientific fields. And I have some thoughts about that. I have been doing some work on this from a science of science and philosophy of science perspective. So science of science is applying scientific methods to the understanding of scientific progress itself, and philosophy of science is a branch of philosophy that studies what is science, what are the goals of science, etc. I am a computer scientist, but I've been dipping my toe into these waters. So this is going to be an overview and a provocation based on what a lot of these folks have been saying. Okay, and in the first 10 to 15 minutes, I'm going to talk about the AI research community itself, and then in the latter part, I will talk about applying AI to other scientific disciplines. So let's start with AI research itself and ask a seemingly very simple question: is AI progress accelerating? That might seem like a silly question to ask. You might think, of course it is, and this has been quantified in some ways by looking at the number of AI ML papers on arXiv, and you can see it's doubling with a very, very good fit for a linear curve on a log scale, so that's exponential growth, doubling every 23 months or so. And you can find the citation at the bottom. And this is, this stops a couple of years ago and perhaps has accelerated even more because of LLMs and generative AI. I'm not sure. However, putting out papers is not the same as progress, obviously. And we've written about this. We've called this the production progress paradox. I think a lot of people share this intuition. So for instance, there was a Twitter poll recently, not scientific, but with that caveat, this person asked, there are a lot of papers, but do you think the underlying science is actually progressing more quickly? And only about 40% of people think it's faster now than in 2016. And a lot of people even think it's slower, and others are uncommitted. But clearly, there is some disconnect between the exponential growth in the number of papers and what we might intuitively think of as progress in ideas in AI and machine learning. Of course, the technology is advancing rapidly, but how much of that is just due to hardware investment as opposed to doing the science faster? So when you want to go beyond these Twitter vibes and want to tease these two apart, you immediately run into problems, because philosophers of science have been asking what even is progress, and there's not a lot of consensus on it. So this is a good paper that looks at 4 different notions of what progress might mean. So for our purposes today, I don't want us to get bogged down in this philosophical debate. So I'm going to make some simplifications. I'm going to assume, even though this is highly contested, I'm going to assume that the goal of the AI community and the AI industry is to make progress toward more powerful and more general techniques. So for instance, when ImageNet came along and deep neural networks started to do really well in computer vision compared to the earlier wave of SIFT features or whatever people were using, let's assume retrospectively we can look back at that and agree that that constitutes progress. Again, this is highly contested. Some people might say this view of progress takes away attention from interpretability and other things that are equally important, not just more powerful models. And many people have questioned, should we be even trying to progress towards generality, AGI, all this stuff, or should we keep it domain specific for many reasons, including safety? This is a very Rich Sutton-esque view, I think, of what is desirable, and I know that he's going to be here tomorrow. But the reason I'm making this assumption is that the AI industry in particular, and a lot of the mainstream of researchers behave as if this is the goal. So let's assume, this is the most charitable light in which we can look at the behavior of the AI community. Even if this were the goal, I want to argue maybe we're not optimally making progress. So that's the key claim that I want to make. So to be able to make that claim, we have to have a little bit of a model of how scientific progress happens and AI progress happens. And for this, I want to go back to, by far, the most famous thing in the philosophy of science, Kuhn's The Structure of Scientific Revolutions. And it's a complex framework, but I'm going to simplify it by saying he points out that progress happens in alternating periods of normal incremental progress and revolutionary progress. So you're working with one particular paradigm and knowledge accumulates, but eventually the underlying assumptions, frameworks, theories behind the paradigm are not really up to par, and you stop being able to make too much progress, and then you have to tear things down and rebuild them and go to a new paradigm. So for instance, classic example, the Greeks, and in the medieval times, they thought the earth was the center of the universe, but within that paradigm they got really good at predicting the motions of the planets using hacks like epicycles. I'm going to come back to that in the second half of the talk. But eventually they stopped being able to make progress, and they had to recognize that the sun is actually the center of the solar system. So that's the cyclical nature of progress between normal and revolutionary. So does this apply to AI? I think yes. And if we were to go back to our earlier example of SIFT features in computer vision versus deep neural networks, we can think of it as an instance of this kind of model, which you can also think of as a punctuated equilibrium. So at some point, there's an equilibrium. Everybody is working with this hand-coded features paradigm. You gradually make progress, but then it plateaus, it tops out, and then you need something new, radical, like neural networks, to puncture that equilibrium and get to kind of the next level. And in NLP in particular, so that I talked about computer vision a little bit, but in NLP, there's been a paper that actually looks back at NLP progress and formalizes this. And they also use the nice analogy of explore, exploit phases. So in equilibrium, the AI community is exploiting the current paradigm, and eventually they stop being able to do that, and they have to explore, come up with a new thing in order to make progress. Another model that has the same intuition is kind of the stacked S-curves model. So at any point, you're on one particular S-curve, but you stop being able to go too far with that, and then you kind of need a new paradigm to make progress. Okay, so given this, the key claim I want to make that the AI community is very good at exploiting any given paradigm, but is actually not very good at exploring and coming up with new paradigms. That might seem very surprising, so I want to give you evidence of this. So let me start with the first part, which is that we're actually very good at exploitation. And this has been written about. There are a few specific reasons for this. One is that innovations in building more powerful AI methods are composable. So what do I mean by that? Someone might come up with a new architecture, someone else might come up with a new optimization algorithm, and a third person might come up with a better training data pipeline. Typically, all of these are composable, so you can make a lot of progress in parallel as long as you're within an existing paradigm. And a second one is what is called frictionless reproducibility. This is something we take for granted in AI, so we might not even recognize that this is a thing, but there's a citation at the bottom where you can read more about this. In most other fields, replication of findings is very hard because, let's say, psychology, a field that has famously had many reproducibility or replicability crises. Someone publishes the results of an experiment. If you're kind of skeptical of it, it costs you tens of thousands of dollars to recruit a new sample of people and do new experiments on them. But in AI, it's just running some computational experiments again. Recently, it started to get expensive because of how costly these LLMs are. But until recently, redoing someone else's computational experiments was very, very easy. So that has led to very fast reproducibility. And clear comparison in the form of benchmarks. If one method is better than another, we generally expect it to have better benchmark performance. Of course, there are limitations of benchmarks. I'm going to get to that next. Okay, so far so good. But what I want to argue is that exploration, when your current paradigm is not working, you need to get to a new thing. These types of methods don't work well. Essentially, the whole community is stuck in a local minimum. So again, I want to keep going back to some historical examples. Let's say, back in the 90s, people thought SVMs are better than neural networks. And so neural networks research was kind of sidelined. And so that was an example, I would say, of a local minimum. It took a decade or two before neural networks, with the help of GPUs and large data sets like ImageNet, were able to show that they can excel at computer vision tasks or tasks in other domains. So I want to argue that this is a different process from exploitation. It's not incrementally exploring the local minimum you're in, but kind of temporarily backtracking, looking in new directions. And I think we're bad at that. The reason we're bad at that, I have to introduce a key concept. This is the notion of turnover of ideas. And you can see a citation at the bottom. It's not specific to AI, but it turns out that every large field, especially fast-growing fields, struggle with turnover of ideas. If there is an idea that's currently central to the community, Like, again, going back 15 years ago, the idea of hand engineering your features, but in retrospect, it turns out to be not such a great idea. How quickly can the community recognize that and move past that idea that's holding you back? How quickly can an idea that's central be displaced by new ideas? And when fields are large and fast growing, it turns out to be harder to displace those ideas because there's too much going on, and all researchers seek comfort in building upon the ideas that are already considered central in the field. So that's roughly the insight of the cited paper. But now let's apply that to AI. I want to argue that discarding ideas when they need to be discarded should be seen as the true bottleneck to progress, as opposed to accumulating new ideas, which is relatively easy. And the reason this is particularly hard in AI might be that the composability that I was talking about earlier breaks down, and this becomes an interdependency between different things that are generally looked upon, explored in parallel. So what do I mean by this? Suppose 10 years from now, we're going to look back and think, oh my God, transformers were really holding us back in 2025. We should have let go of them much earlier than that. But it might be the case that proving this requires changes not just to the architecture, but to the optimization algorithm, the training data pipelines, and even evaluation methods. As long as you're just looking at perplexity, maybe you're never going to be able to show that transformers are holding us back. So doing all this at the same time is too much for one paper or even one research project. And so this kind of thing doesn't tend to happen. People are tweaking one element at a time, and unless tweaking that one element results in improvements to the state of the art in established benchmarks, that tweak is not going to be taken seriously by the rest of the community. So that's a classic thing that gets you stuck in a local minimum. You're not able to take a big step. You're only taking small steps one at a time. So I think we need to do things differently. And in particular, the fact that there is so much investment, especially from the industry, going into sustaining the currently dominant paradigms means that any new ideas, new paradigms, have to compete with these billions of dollars that are going into making the dominant paradigm the state of the art, right? So in a way, the increased investment in AI is paradoxically, while it's making it easier to exploit the current paradigm, it's making it harder to take that big step to get unstuck from the local minimum and explore a truly new direction. Okay, so yeah, as I've been saying, benchmarks might be useful for exploitation, but when you're exploring, temporarily you have to look bad on benchmarks until a year or two later, enough new innovations have accumulated that you have the new state of the art. So, and the classic solution to this is to have subcommunities, and subcommunities pursue different things. Earlier, I was talking about how neural networks research was sidelined when people thought SVMs were the hot thing. But the reason neural networks research were sustained is because there was a community of people who truly believed in them. And as long as their research was valued by each other, they kept on trucking instead of following the herd and following the rest of the community. Right. And so maybe today, Neuro-Symbolic AI is in a similar situation. Right. As Alex was saying, maybe it's, it's maybe not quite good enough yet to really be commercially adopted. So the mainstream is not paying attention to it. Maybe it's going to take a few more years before that changes. But until then, this community has to sustain itself because these ideas are treated as valuable by the community of peers. And in particular, that can only happen if the criteria for what constitutes success, what constitutes progress, are different from mainstream AI/ML research. Because otherwise, if every new paper has to demonstrate the state of the art on something, that's almost definitionally equivalent to getting stuck in a local minimum. And finally, a subcommunity can only be successful if it's big and powerful enough to take this criteria for what constitutes progress, what is valued in this community, and defend it when scholars are being hired, when they're coming up for promotion or tenure or something like that. Because otherwise, they're going to be evaluated by AI/ML scholars that are outside the subcommunity by different criteria, and their work is not going to look that good. So these are all the things I think that it takes for a subcommunity to succeed. And wrapping up part one of this, everything I've said so far is about why the invention process is can be slow in AI research. We have a paper called AI as Normal Technology with my co-author Sayash Kapoor. This is probably what I'm best known for these days, where we talk about speed limits more broadly in AI and its impacts on the world, especially on the economy. So going beyond the research stage, we talk about commercialization, and we talk about how those products get adopted by the economy, by users, by other enterprises, et cetera. And we talk about the fact that there are much more serious speed limits in those stages. So check it out if you're interested. Okay, so that's part one. Let me take maybe 10 or 15 minutes to talk about applying AI to other sciences, whether it's social science or medicine or mathematics or whatever it is, and what are some limitations to the speed of progress there. So many people are saying that AI can supercharge science, and we wanted to investigate this in a recent essay. And what we concluded, and I'm going to talk about this, is that the way that things are currently going, it's more likely that AI is going to slow science than speed it up. That might seem, again, very counterintuitive. I do think we can change this, but the current path is not good. And let me explain why. So we basically identified 3 bottlenecks. So again, what's not a bottleneck is the rate of producing scientific papers in medicine or social science or math. That's not the bottleneck. But more papers doesn't mean faster progress in ideas. The actual bottlenecks, one, you have to minimize the rate of errors and the amount of energy wasted on replication. Right? I said earlier that in AI, replication and reproduction is not such a serious issue, but in other sciences, it's a much more serious issue. And the second bottleneck, this is something we already talked about in the case of AI, it's about how quickly you can let go of theories that are not working well anymore, as opposed to how quickly you can accumulate new ideas. And the third bottleneck is human understanding. And you might think, oh, we're going to automate science. We don't need human understanding anymore. Well, I have some things to say about that. So let's look at each of these in turn, how AI is currently impacting these, and how we can potentially change that. So first, let's look at the impact on errors. It turns out, unfortunately, that when non-AI experts in other disciplines are using AI for their disciplines, a lot of that work is completely filled with errors. And we've identified 2 root causes for this. One is just poor software engineering practices. And the second is that the AI industry has often pitched these tools as kind of plug and play. And, a lot of scientists, I think, have swallowed this hype and are using these tools without necessarily understanding them, without understanding that there are methodological pitfalls that are being introduced. So this is not even specific to AI. Scientists are poor users of technological tools in general. So when geneticists are using Excel, for instance, to format their data, they don't recognize that sometimes Excel auto-formats things in the wrong way, and that leads to errors in their data. And this has affected, I think, tens of thousands of papers until somebody noticed that this is happening. So if these kinds of rampant errors are possible with as simple a tool as Excel, imagine how much worse the problems are when people are using generative AI for writing code automatically or something like that. So we've done some research into this. Apologies for the busy slide. And what we found is that this is a survey of systematic reviews in other fields in which they looked at AI for instance, clinical epidemiology, and they sampled 71 papers, and they found that 48 of those papers had errors. And 17 out of 17 papers in satellite imaging had errors, and so on. And then we did a bunch of our own analyses as well, and these are on the left citations to a couple of our own papers here. So when different scientific fields start adopting AI as a research tool, in general, things don't look good. And this is, I think, pretty depressing. And one of the most shocking things that we found is that, in particular, in political science, we showed that a whole subfield was filled with erroneous claims about predicting civil wars highly accurately because they were just testing on the training set. And when we published that, the response from the political scientists involved was that, oh, no, the train test split or whatever, that's best practice in your world, in the AI world. But in political science, they've been doing statistics for 50 years, and in stats, you don't do train test splits because your models are so simple, they can't really overfit. So this is what we do. So this is just a legitimate methodological difference. It's not an error. And, that's just a bonkers claim. You can either predict civil wars really well or you can't. There is a notion of ground truth here. You can't have different legitimate methodologies that can result in very different conclusions about whether or not you can highly accurately predict civil wars. Anyway, the point is that AI tools are very easy to use, but best practices on how to use those AI tools, including things that are as simple as train test splits, forget about more nuanced things, those are not being ported quite as well to various scientific communities that are using AI. And I think that's obviously a serious problem. So I think what we need is specifically to build AI for error detection. And people are starting to do this, and that's great. But right now, they're focusing on the text of papers. We think they should focus much more on the code of papers because that's where a lot of these errors are going to be lurking. And you can't even figure it out from reading the text because a lot of those specific decisions are not documented in the text. They're only in the code. All right. So let's look at the next one. How is the use of AI for science increasing or decreasing our ability to let go of flawed theories? And here I want to give you a historical analogy. I was talking about the model of the universe with the Earth at the center earlier. And as I was saying, they got really, really accurate at being able to predict the motions of planets by these hacks such as epicycles. And eventually it got really, really complex. But the problem is, prediction is not the same as explanation. This is a perfectly accurate predictive model. It's so good at prediction that even today, planetariums use this kind of model as a way to draw the planetary motions on the screen above you. There's nothing wrong with it from a predictive perspective, but of course, it's a completely wrong explanation of the solar system. Right. And our worry is that the exact same thing is happening with AI. It's optimized for prediction. And this is a paper, I think, recently from ICML. First author is Kian Bafa, where they trained a transformer on a bunch of planetary orbits. And again, you see this perfect prediction despite having a completely incorrect world model. But this is typical. This is just one example. So when people start using AI, they start reframing the goal of what the scientific activity is. It goes from understanding how the solar system works, or whatever the equivalent is in your field, to predicting the motions of planets. And so if you're purely focused on prediction, you're going to be optimizing for that without necessarily getting to a better understanding of the underlying scientific phenomenon. And I think we need to change that. This is a kind of op-ed that we wrote on this topic in the journal Nature. But I think this is one area where neuro-symbolic AI might help. But more generally, I think when we're building AI tools for scientists, we should focus much more on getting the world models right, as opposed to just getting predictive accuracy right. Okay, so last few minutes, how is AI impacting human understanding? And this is where that picture comes in. When we use AI for science, I think the vision in many cases is to automate the whole process, but I think that's particularly dangerous because it gets you directly from the problem to the solution, bypassing all of the human understanding that happens along the way. But in a way, I want to argue that we solve scientific problems and publish scientific papers, but in many scientific disciplines, really the point of that whole activity is the thing that sorry about that. What happened here? The point of that whole activity is the human understanding that happens in the middle, because that's what allows us to generate new problems, new theories and paradigms, correct errors, train new scientists, and apply scientific knowledge to policy or industry or things like that. And we're very far from AI being able to replace all of those things. So I think we should be very careful about skipping this step in the middle. And this can be seen very clearly in a case like mathematics, which is a little bit of an extreme example, admittedly. But I would say that in math, the instrumental value of proving theorems, especially in pure mathematics, is close to zero. The theorems are not valuable on their own. It's not as if we're going to be applying those theorems to practical problems this year or next decade or even next century. Typically, it takes, if at all, multiple centuries for new mathematical knowledge to find application. And so if you're just building AI for proving theorems, bypassing the human understanding on the way, you've made things worse, not better. And there's a great paper on proof and progress in mathematics. This was written long before debates about AI, explaining that the goal of mathematics is not really to find solutions, but that's just an excuse for the activity that happens along the way, which is to build up human understanding. And so my provocation is, what would AI tools look like, whether in mathematics or in other branches of science, if the goal was not to solve the problem, but really to improve the understanding of the scientists who are going to be using it? I don't know the answer, but I think it would be a useful goal to pursue. So, to summarize my talk, in the first part, I talked about AI research itself and how, while we're very good at exploiting a particular local minimum, we do tend to get stuck there, and that's why it's important to have subcommunities who value different things, who have different notions of progress. And in the second part, I talked about AI for other sciences like medicine or mathematics. And it seems like, based on the three bottlenecks that Sayash and I identified in our essay, arguably the way that we're building these tools today is making all three bottlenecks worse. And I gave some ideas for building different kinds of tools. Thank you so much, and I look forward to your questions.
Okay, thanks, Arvind. I just want to say there's so much urgent truth in everything Arvind said. This is amazing. So I wish there were. We should donate money to your cause or whatever. You're like, so, I just want to mention a few things, which is somehow translating some of the questions too from the audience. So, but let me first relay one anecdote that illustrates one of the things Arvind said. So, this thing of being so benchmark driven right now. I mean, it's a good thing, of course. It like gives us a way to say what's better and what's worse, but very celebrated in ML. But also can be a very bad thing, as Arvind said. So I remember when, if to do speech recognition, you had to do some version of FFT plus hidden Markov models. That was the only way, because it was locked like that for, I don't know, 10 years, 15 years, something. Why? Because there were a DARPA competition, and you had to win that, and you had to compete with basically very well-tuned models that were using that paradigm. So there was no way to come with a different idea that anyone would pay attention to. I, as a PhD student at the time, was like, I don't know anything about this area, but what about one big non-parametric model, say, that is flexible enough to kind of learn all that? This is, of course, now what we do is neural nets. But there was no way to squeeze it. It was very difficult. You had to actually progress with the new approach so much that you eventually beat the benchmark. But you had to survive long enough with the ideas. That's a problem. And so super, super true, very real, everything Arvind is saying. So I also want to point out this train test issue you brought up. It's not just like weird fields that don't understand statistics. It happens in AI. Now, so we do this. This is shameful, but we do it, half knowingly. Everybody knows that there's a lot of cheating in papers. We do tune on the test set when it's available, and so on, because there's so much pressure. You can't get your paper published unless you have beaten other things in your table of results at the end. So let me just say, everybody doing that, shame. Okay, and that's like whatever 75% of everybody, I think. So let's see. Here's a question. During the 70s, there was a huge debate on AI. What is Arvind's view of Hubert Dreyfus and his work? What computers can't do? etc. If you're familiar with that.
I'm vaguely familiar with it. I mean, in some ways, we're having a lot of the same debates, but in some ways, things have changed a lot. If I recall correctly, it was Hofstadter, perhaps, who did say that large language models did cause him to significantly revise his ideas of what AI can and can't do. In my own work, I've tried to avoid really getting into predictions of what AI can't do. I'm happy to leave that one to philosophers. But I find it more productive to think about just comparing different approaches or paradigms in AI and what might be the limitations and how to transcend some of those temporary limitations.
One of the questions was, isn't Arvind the author of AI Snake Oil? So, Arvind, do you want to say a little bit about the book? I think, first of all, extremely illuminating book. I took a little look at it, so highly recommend it to everyone. But do you want to say some of the high points from the book?
Yeah, definitely. Let me point out that the subtitle of the book is "What AI Can Do, What It Can't, and How to Tell the Difference." So it's not, it's not a skeptical book. It's about let's get detail and let's try to separate the wheat from the chaff. That's the theme of the book. And in particular, the kind of AI that we're most skeptical about is predictive AI that's used in things like criminal justice and hiring. And these are used particularly to make decisions about typically lower income individuals, people who are facing the criminal justice system, or people who are, being recruited for low level roles in companies, etc. And these models, a lot of these models, in our view, are just elaborate random number generators. And there is this pretense that these are highly accurate predictive models and you can predict who's going to commit a crime. And based on those predictions, people are jailed without a determination of guilt. So these are the kinds of deeply morally problematic things that the book goes after in the first part. And then we switch to generative AI, which we very much acknowledge the potential. We say repeatedly that it is useful to every knowledge worker, but also we call out a lot of the hype around generative AI and predictions about superintelligence, which is something we're especially skeptical about. And in our more recent essay, AI is Normal Technology, as well, we talk about how a lot of the superintelligence worries are misguided.
So let me just ask. So, first of all, I love your, starting with Thomas Kuhn, who was one of the most influential books for me. So, one of the things in Kuhn's sort of exposition of the topic is he talks about the resistance that happens, active resistance, because in the current paradigm, whatever it is, will have staked, built their reputations in that paradigm. And when a new thing comes along, a classic illustration is Einstein's theory in his book, then whoever was made their reputation in the previous physics tends to want to actively kind of suppress this new thing or poo-poo it or whatever, and it comes in the form of maybe not getting your papers published, maybe not getting grants. And it's because all those people who make those decisions are the people in power are in the current paradigm. Now, so this, when you talk about, first of all, any comments on that? Love to hear. Well, let me start with that.
Yeah, it definitely happens in AI as well, I think. And in fact, in AI, you don't even necessarily have to go so far as being very creative about how you poo-poo the new paradigm. You can just be like, this doesn't beat the state of the art, right? Why should I pay attention to this? End of story. But then there's also the commercial aspect. The industry is very invested in protecting current paradigms in a lot of cases. They might not be able to quickly switch over to a new way of doing things. So all of that introduces additional inertia compared to what Kuhn was talking about.
Here's the other thing is, about the active kind of suppression or whatever, but maybe closely related to that is active deception. So there's the, which is hinted at with snake oil. So do you think which parts of it, like let's say people talking about super intelligence, what part of that? Now we can debate. Many people legitimately feel we're on the cusp of super intelligence. I would put forth that probably most real AI researchers don't think so, but I could be wrong. But what part of it do you think that
Sure.
either that topic or some other example is
Yeah.
actual active deception versus self-deception or whatever true belief?
Yeah, I mean, I would say I think where a lot of this hype comes from is from people's inadequate understanding of human intelligence. So our key thing is that even if one were to assume that recursive self-improvement is possible, there are still many bottlenecks that will prevent the realization of what people usually think superintelligence will be. So we break this down into what are the barriers to human intelligence, and which of those, we have three barriers, which of those three barriers will AI be able to surpass? So the three barriers, one is computational. Simple example is chess. AI is already so much better at the human world champion at chess because the limitations are primarily computational. The second is intrinsic limits. On many tasks, this is as far as you can do. There's irreducible error. So when you think about, for instance, AI being used for writing, I think AI very quickly over the last decade or so, large language models rose up to the level of a mediocre human writer, but they're having a lot of trouble surpassing that plateau because there's not a clear signal. What it means to be an excellent writer is very much a matter of taste and judgment, and what it means, what good writing means for one group of users might be different than another group of users. These we think are intrinsic limits, and there can exist no superhuman writer who is going to write a page of text that is so persuasive that you change your political beliefs, for instance. Just think about whether that might possibly happen to you. And if it won't happen to you, why would it happen to anybody else? And if it can't happen to anybody, what does that say about whether it's even possible to be a superhumanly good writer? And the third limit is knowledge limits. A lot of people say, "Oh, superintelligence is going to be, the most amazing doctor, etc." Well, there the limits are how much we know about the human body, and to surpass human performance actually requires conducting new medical research. And we're not going to let AI autonomously do medical research on thousands of people, so that introduces a bottleneck. So, to summarize all of that, the key thing is not about how fast the computational elements can improve, but it's about the bottleneck when you interface with the rest of the world that are going to introduce limits to superintelligence. Do you mind? I know, Alex, you're asking the questions, but I do want to pull one question out of the chat
Please,
that I wanted to address in my talk, but didn't have time to. And this is from Ramalingam Chalapa, who says AlexNet became popular because it did better on the ImageNet benchmark. Absolutely. So I think the implication is, why are you so down on benchmarks? It's because of the benchmark that we realized that deep neural networks could do well. But here's the thing. I wanted to get into the story. But as you know, the principles of deep neural networks were published in the 80s. So why did AlexNet not happen in the 80s? Because back then, GPUs weren't around. Our ability to build these super large benchmarks weren't there. And so it took several decades for the data sets and for the hardware to catch up so that deep neural networks could prove their mettle on benchmarks. So yes, eventually benchmarks got us out of it, but they held us back by 30 years before that happened.
excellent.
I don't know if we have time, but if we do, maybe we can take one last question, or we can end it here. Totally up to you.
No, we have a little bit of time. I think next talk starts at in 9 minutes. So, let me just mention one factor that is not mentioned in say Kuhn's analysis, which is, and you touched upon it, the big money that's being put in. So this is like a weird new factor, you could say. I mean, or maybe not. Maybe this is the effect of industry in paradigms. Maybe in other areas this happens too. Industry can put in lots of money into a certain paradigm and influence kind of the course of science, you could say. So do you want to comment on that?
Yeah, for sure. So I think the industry influence happens in a few ways. One is the research that comes out of industry itself. Another is industry funding of academia. And a third, and in my view, perhaps the most powerful and perhaps the most worrying, is that the question of what kind of research is considered um, valuable, meaningful by the community is just so strongly shaped by what will ultimately be commercially valuable to the industry. And that's an almost invisible factor that you can't identify by literally tracking the dollars. And I worry about that a lot. So 10 years ago, for instance, I was working on algorithmic fairness research, and it was very hard to get too far, I think, for that community because this was not considered valuable in the mainstream AIML community. But then the industry did a flip in the latter half of the last decade where they admitted that fairness is an issue that they should consider. And only then it became much easier to publish these papers. Um, I see so many more questions, but maybe we can leave it there. I unfortunately also have a constraint, need to get to another building. Look forward to catching up the rest of the talks later.
Yeah. So thank you, Arvind. Let me just say, great talk. And, we'll send all the questions that we didn't get to Arvind. So, and get his book, get on his newsletter. Thank you so much, Arvind.
Thank you, folks. This has been really fun.
Okay, so now we have a break. I just noticed we have an error in the schedule that short shrifted our next speaker by 10 minutes. So, Leilani, if you're listening, maybe you can jump on now, say. But otherwise, we'll have a break, and we'll see you all at the end of the 30-minute mark, meaning 6 minutes from now. Unless Leilani comes. Oh, here she is. Okay. Hey, Leilani. Okay. So yeah, I noticed we somehow have you at 35 minutes, but you should get longer. So,
I planned for 35, but I can always extend it, or we can take more Q&A too. I'm flexible.
Okay. What would you prefer? You want to start, or do you want to wait 5 minutes?
I guess it's up to, is everybody here who's listening? Otherwise.
Oh yeah, we have people all set, I think. I suppose I might wait to your exact start time to catch your talk.
Yeah.
But well, why don't you take it away? So let me do a quick intro. Oh, are you ready, Leilani, or
what happened?
Oh,
sorry, yes, I don't know what happened.
Okay, let me just do a quick intro. So Leilani is a professor at UC Santa Cruz. If you don't know, she's chairing the NESI conference this year. So, and that's coming up. So you should check it out. I will be there. You want to meet some of these lovely people in person, that would be the place. One of the places. And that'll be in beautiful Santa Cruz. So, and Leilani's going to talk about some very important work, on safety. So, with that kind of teaser, let me just hand it over to Leilani.
Great. Thanks for that really kind introduction, and happy to answer questions about this work as well as NESI. Can everybody see my slides? Good. Okay, great. Awesome. So So hi everybody, I'm Leilani. I'm an assistant professor at UC Santa Cruz, and I'm really excited to talk about the work I've been doing and the work we've been doing in my lab for the last few years on using Neuro-Symbolic AI, particularly for developing safer and explainable autonomous vehicles. So a little bit of an agenda of what I'm going to talk about today. So I'm going to start by motivating the problem, which is that complex systems fail in complex ways. In particular, I will be talking about autonomous vehicles, but of course, these types of approaches can be applied to any type of complex system, and I'll be describing a complex system as a system made out of multiple parts. Then I'll talk about one type of solution, which are local sanity checks, which is a neuro-symbolic approach, which basically looks at the output of computer vision systems and supplements that with different types of symbolic rules. I'll then talk about some of our work on encoding driving rules so that we can ensure that autonomous vehicles drive safer. And then finally, I'll talk about some of our ongoing work doing explainable AI with neuro-symbolic approaches. So the question I'll be trying to answer today is, how do we develop neuro-symbolic methods that can help anticipate and explain vehicle failures instead of doing after the fact analysis? So how can we develop architectures that can help us identify what the weak points of these systems are before they're deployed? And this is really important because these complex systems fail in very complex ways. So, one of the more recent examples of this is what happened when there was a woman who was dragged underneath one of these self-driving cars, Cruz, in San Francisco. And again, these cases can be very morbid and upsetting. And a lot of the reasons for that is because these are ways that just a human would never fail as a driver. And so what we really want to do is try and detect these things before they happen so that we don't have these types of catastrophic failures. There are other cases that these systems fails which are due to common sense. So this is a picture, this is a bus side ad on the back of a bus, and the Tesla thinks that this is a person crossing the street. There are a multitude of these types of failures. There's also a case where there's a Tesla. You might see here that there's a yellow light. I'm not sure if people can see my cursor. But there's a yellow light here, and the Tesla thinks that it's a yellow light, but actually it's the moon. Of course, there have been all different types of adversarial attacks, but now adversarial attacks are being done in the real world as well. So with just a few pieces of tape on the stop sign that you can see here, all of a sudden people think that this stop sign is now, or all of a sudden the autonomous vehicle system thinks that this stop sign is now a 45-mile-per-hour sign. And finally, it's been shown that computer vision systems are better at detecting faces with lighter skin tones and darker skin tones. This is part of the bias problem in computer vision. And all of a sudden, if you put that same technology on a self-driving car, the self-driving car is now better at predicting pedestrians with lighter skin tones than darker skin tones. And so a lot of the work we've been doing in my lab is basically, how can we handle all of these different types of failure cases? And in particular, how can we do that with neuro-symbolic approaches? But before we get there, we really have to think kind of where is self-driving now? And really, it's at two different extremes. So either you have cases that are very cautious but not comfortable. This is what happened in General Motors' ultra cautious self-driving car. So what happened in this case is that the self-driving car was starting and stopping for anything in its way, regardless of whether that was, a plastic bag or a person crossing the street. And what happens is because the car is kind of jerking you around, then people have this feeling that the car actually isn't safe because it's not having this smooth trajectory. And so I think it's really important that, our notion of, safety, which would be stopping at everything, actually can sometimes have the adverse effect. Then, we have what happened in Uber's fatal self-driving car crash, which is an example that I'm going to be showing today, which is what happened when they said, okay, now we're only going to stop for objects when we are very confident of what's happening. And so, the problem that we've really identified is that we need better common sense and reasoning, and the best way to do that is with a neuro-symbolic approach, because we have all the benefits of using neural nets for LiDAR and vision detection. We just need some type of common sense layer on top of that to be able to handle these types of cases. And so what we've been doing is kind of creating these models that are inspired by human organizations. And I'll kind of outline this in 3 steps, and I'll talk about a few of those pieces today. And these facilitate better communication and sanity checks for a complex system. So, you can imagine a human organization that's layered, kind of as the way I'm showing you here. There may be some middle managers and then a higher level manager. And around each one of these, we have kind of a sanity checker, the dotted line that's basically an individual checking that it's doing the right thing, but also the sub-teams checking that they're doing the right thing. And so the first thing that we do is we create overlapping of a hierarchy of overlapping committees. So committees are groups that are doing the same thing. Of course, the vision and the LiDAR system are both perceiving the world, so they're technically part of the same committee. Then we facilitate continuous interaction and communication. And the way that we do that is exactly with these local sanity checks. So we're constantly enforcing each one of the committees or subsystems, as well as the individual parts, to constantly explain what they're doing. Okay. And then when a failure occurs, a story can be made by basically combining the members' observations. And the way that we do that is with an explanation synthesizer. So basically what that does is it looks at conflicting explanations. So if the vision system says it didn't see anything, but the LiDAR system thinks that it did see something crossing the street, then it figures out which explanation is stronger. And what's really nice about this approach is it actually can mitigate a lot of the common problems that we just saw a few slides ago. The local sanity checks are able to handle situations we haven't even seen before. This is really shown in these news articles about the trollable self-driving car. I'm sure many of you have seen where people are putting traffic cones on top of Waymos to make them stop moving. And so this can justify new examples, even if the computer vision system or the neural network hasn't seen these instances before. And then the explanation synthesizer is able to reconcile essentially what happened with the deadly crash with Uber, where the Uber self-driving car unfortunately struck and killed a pedestrian crossing the street with a bicycle. And the way it's able to do that is it can reconcile conflicting reasons. What happened in this case was that the computer vision system wasn't sure of what it was perceiving, so it told the vehicle planner to basically ignore the person crossing the street. And what we're able to do is basically take the different explanations from different parts and tell the vehicle to take a different type of maneuver, especially in these safety critical scenarios. So I'll be talking about justifying these new examples. I'll talk about the driving rules that we've developed for this. And then at the end, I'll talk a little bit about how we're doing this with ongoing work and explanations. So let me kind of give you a preview of the type of scenarios that we're looking at. I am going to give a disclaimer or trigger warning. This is the front-facing camera of the Uber self-driving car incident. You will see the pedestrian crossing the street right before they are struck, but you will not see the collision. But just to get an idea of kind of what these scenarios look like. So you'll see the car is going very quickly. It's going 47 miles per hour. And the person is crossing the street. The vehicle doesn't make any type of other maneuver or anything to try and move out of the way. And again, the reason that this happened was because the vehicle was focusing too much on a single modality. It was focusing too much on the vision system and not processing the LiDAR system. And so the types of systems that we're building in my lab, and this is published in a few different things, including my PhD thesis, is basically to create these types of hybrid architectures around the existing parts of the vehicle. And of course, this is an extremely simplified view of a vehicle. Of course, there are more parts than just vision, LiDAR, and tactics, but for demonstration purposes, I'm showing what this looks like. And so what the output of my system does is it actually finds that the best option is to veer and slow down. It gets information from the vehicle tactics that the vehicle is traveling too fast to suddenly stop, that the vision system is inconsistent, it's getting that from the vision system directly, but that the LiDAR system has provided a reasonable and a strong claim to avoid the object moving across the street. Now, this was generated long before the days of ChatGPT. You can look at the date stamps on this work. And now what we're doing is trying to make this work more accessible to other types of complex systems as well. And I'll be talking about that today. So that was motivating the problem. Now, let me talk about some of the actual techniques that we use that you can also employ for your own systems as well. And I'm going to start with the local sanity checks. So when we think about how complex systems fail, they largely fail in two ways. So the failure can either be local to a specific subsystem, or it can be a failed cooperation amongst subsystems. And we just talked about that with the Uber self-driving car accident. But we're going to focus on the first case here, the local failure. And in particular, we are going to look at one particular type of failure which can happen with the camera data. And so I guess, computer vision and, a very simplified slide. So what happens is some type of neural net will label camera data. And so what this is going to look like in the self-driving car case for us is that you're going to get some image. Okay, you're going to put that through some type of neural network for computer vision, maybe the Inception network from Google, and then you're going to get some label, which is going to say that this is a pedestrian. And of course, there are many bells and whistles that can also occur here. For example, you might also get a bounding box and other things too. But this is the basic process that's done for the camera unit of a self-driving car. But there's a big problem with this. Neural networks are very brittle. They've been shown to be susceptible to adversarial examples. We already talked about some of those, but a particularly cute example of that is you have a picture of a pig. You add a little bit of noise to that, so 0.005 times this noise, and all of a sudden the computer vision network thinks that this is an airliner. Of course, we saw the physical attack here, where you can do the same thing in the physical world. And again, these are happening all the time. This is just one example. There are other things with different textures, that you could put on signs and other things that have similar types of adversarial behavior. And so the real key that I'm trying to illuminate with these problems is that when we're talking about self-driving and other types of mission critical, safety critical applications, these mistakes have consequences. And so we really have to basically monitor these systems to make better decisions, ones that make common sense with the types of knowledge that we have as people. And so what we've developed is basically a monitor for reasonable behavior within a particular domain. And so I'll be talking about that in the self-driving car domain. And the way that we do that is fairly simple. We just say, okay, we're not even actually going to look at the network. And I'll talk a little bit later in the talk about how we're actually trying to bring in neural network interpretability into this pipeline. But right now, what we're going to say is, no, we're just going to treat the neural network as an opaque mechanism, and we're just going to look at the output label here. Okay. And basically, we're going to supplement that with some type of common sense knowledge base, along with a flexible representation that can identify whether that is unreasonable or not. And then we will use that to justify whether it's unreasonable or not. And so the output of the system is twofold. You have a judgment of whether you think that that's reasonable or not, and also a justification of why it is. And so we can use that to basically say whether we should interrupt the computer vision system or not. Okay. And so we call the system reasonableness monitors, and this is basically what it looks like. So again, it takes the output of an opaque mechanism, which could be anything. That could even be a mechanical part of the car that you're not sure how it works. You then represent that with a flexible representation. You identify unreasonability. You supplement that information with a common sense knowledge base, all leading to why it's either unreasonable or not reasonable. I'm particularly going to talk about the flexible representation just for this tutorial so that you guys get an idea of how, again, you could apply this to the particular problems that you may be interested in. So what we're going to use here is a primitive representation, and that is going to encode this type of understanding. And of course, there are many different types of primitive representations that you can use. I'm using conceptual dependency theory, or CD, from Schenck in 1975. And what he came up with was basically 11 primitives that would account for most actions. And you can look at the actions here. And what I focus on for this work is basically representing this particularly for the vehicle domain. So instead of looking at all 11 primitives to account for most actions, I'm going to look at the 5 for physical actions that are highlighted here. And then I extended this to different vehicle primitives. So those could be turning, yielding, etc. Okay. So what our big problem then becomes is that we basically have to parse natural language into this representation. And what's particularly nice about this representation is that it's explainable by design, and I'll describe how that's done in a little bit. So we're going to parse this natural language into the representation. So let's take the example we were looking at earlier. This is an actual data point from New Scenes. This is the self-driving car data set. And let's say that we have this labeled as a woman, and the description of the scene is that it's a woman crossing the street. Okay. Then what I'm going to do is I'm going to take that, okay, and I'm going to basically parse this with a part of speech tagger to get, you know, the noun phrase, the verb phrase, etc. And then what I'm going to do is I'm basically going to bound the particular parts of interest of this representation using a common sense knowledge base. So basically, using an ontology, I can say, okay, actually, it doesn't matter that this is a woman crossing the street. This is a person moving in the direction of the street. And that's how I'm going to represent this so that, you know, I'm not looking at all little tiny instances. I'm looking at kind of a higher level representation of this particular scene. So again, I bind those with a common sense knowledge base to look for what are called anchor points. So we have those designed as a person, the particular primitives and other objects that we're looking at. And the way that we would actually represent this in conceptual dependency theory is basically this would be a person. They're moving in the direction, that's what the D corresponds to, of the street, and the object doing the moving is the person. Okay. Now, you don't need to, you know, understand particularly how this sort of representation works. The important part of using this representation and why we use this for autonomous driving is that this representation has implicit rules built in. Okay, and that makes it really attractive for, again, what we're trying to do with looking at reasonability and self-driving cars for making safer decisions. So, for example, if we have detected that somebody is moving, move has certain rules attached to it. So primitive for reasonability has an implicit rule built in that moving is reasonable if you have the property that you're adamant and you're located near the place where you're moving, right? So we're saying that for a particular actor and location X and Y, right? And you can see that the person is the actor here, the location here is Y. And again, it has to be that the actor has the property that they're adamant or they're located near. Of course, there are all different types of corner cases of this. You could, you know, be pushed in a certain direction and that could cause movement. But here I'm showing for one example, one type of reasonableness rule that we would have. And what works really nicely here is that if we are looking at, you know, autonomous vehicles at sort of a frame by frame basis, so we can then say that a perceived frame is reasonable if all the reasonableness rules that we have are triggered as reasonable for that particular scene. So I think that that's really nice because then we can actually have an explanation of why we think it's reasonable or not. So let me show you guys a little bit about, you know, what that looks like now for doing this type of monitoring on real data. And again, I am showing this for new scenes. This is an autonomous vehicle data set. So when this is actually in the data set, this is labeled as a human pedestrian adult. And you can see, you know, there's a bunch of information that we have here about this person. The number of LiDAR points, the category, you know, how visible they are, etc. And again, what we're particularly using here is just the category name, and we're also using some of the size and other information. But of course, you know, in future work, we're going to be looking at sort of the whole metadata that we can look at. And I talked a little bit before about how we're incorporating common sense. Let me describe why this is a particularly difficult problem just to apply here in the autonomous vehicle world. So if I am to just apply ConceptNet to this scenario and I say, okay, I have a human pedestrian adult and I want to see if I can use this common sense knowledge base to basically prove that I think that this is a reasonable scene. So if I just use this without any type of representation and just query ConceptNet, you'll see a bunch of, you know, interesting information, what an adult is capable of. So, you know, a bunch of information here. I think you can read through it. That is not very useful for this case. For example, drinking beer or, you know, explaining rules to a child. That's not exactly what we're looking at here in the scene. But there's also a lot of information that is very useful. For an example, an adult is a type of animal, and animals can move on their own, right? An adult is a type of person, and those have certain properties. And so one of the contributions of our system was really to find the right type of common sense knowledge that we'd want to represent in the vehicle world. So basically what we did is we took ConceptNet, we would query it for a particular term, and then filter that down to a very small subnetwork of common sense knowledge that we would want. Now we had to do that hard-coded for this particular system. And again, I'll talk a little bit on future work, how we're trying to do that automatically, how we're trying to learn that network as we go. So let's see a little bit about, you know, what the reasonableness monitor actually looks like for this particular scene. So it will output a judgment and a justification of why this is reasonable. So we put that through our system, it finds that it's reasonable, and here is the reason why. So it says, okay, great, this perception is reasonable. An adult is typically a large person. They are located walking on the street, and its approximate dimension, which we give here, is approximately the correct size in meters. So that works really great, right? So, and if we look at actually the New Scenes data set, basically 98% or more of the data is reasonable. And the reason for that is that, you know, these are hand curated data sets. There aren't any wrong labels. And so what we had to do to actually validate this system is we had to basically add and validate errors. So instead what we said is, okay, what we're going to do is we're going to take some of the existing labels that we have and we're going to scramble them, and then we're going to see how the reasonableness monitor does with basically finding that. And so instead, let's scramble the labels. If we label this as a movable object traffic cone, it clearly finds that it's unreasonable, and it basically says it's not a reasonable size, it's too tall, and that there's no common sense supporting this judgment. So discounting objects detected in the same region. So again, what's happening here is basically it's saying, okay, I have, you know, an idea of how big a traffic cone should be, and it definitely shouldn't be as tall as a person is. So in this case, I'm going to say that this is unreasonable, and I'm going to look for other sensor. I'm going to look for other sensor information for this point. Okay. So that's, you know, one type of solution that we're working on for autonomous vehicles. Let me talk about another piece of work that we're working on, which is basically on encoding driving rules. So this is part, you know, of a large effort that we're working on at UC Santa Cruz on building robust autonomous vehicles, which is part of a Department of Transportation, National Center for Transportation, Cybersecurity, and Resiliency called Tracer. This is led by Alvaro Cardenas, my one of my colleagues, and we're also working with Sihong Zi and Daniel Fremont. You can read more about it in the news story, but just that this is a very small part of like a much bigger effort. So we're looking at cyber physical system security, cyber physical system verification. I'm looking mainly at AI for vehicles, and Sihong is working mainly on adversarial machine learning. So when I kind of show these driving rules, they may sound like they're fairly naive, but again, they're being used for a lot of different parts of the system. So let me kind of motivate what that looks like. What I'm going to be talking about right now is the driving rule specification. So basically, how can we create a specification of driving rules, which can then be used to basically automatically generate maneuvers or simulation scenarios for driving tests. And of course, that's going to be used in many other parts of the system, including the fuzzer, which will be passed into an autonomous vehicle simulator to generate these different types of scenes. So again, I'm going to talk about the specification, how we do that, but this is part of a much bigger system as well. So let me talk a little bit about what the vision for this system is. So some of you may know, some of you may not know, but you know, autonomous vehicles are not held to the same standard that we are held to when we want to get a license. So I don't know, I feel like I'm always going to date myself, but when I went and I got my driving test or I got my driver's license, I had to physically go into the DMV, and there were two parts, right? The first part was that they would give me this driving handbook, some, you know, paper document. I think now they don't do that anymore. And I had to take a written test saying that I knew what the driving test or knew what the rules of the road were. And then there was a dynamic driving test. I would have to go in with a vehicle, and I'd have to go with somebody outlined here who is making sure that I'm making the right decisions. Now, the problem is that autonomous vehicles are not held to that standard. If an autonomous vehicle wants to be on the road, at least in the state of California, basically the governor just has to sign a piece of paper. And so what we have really encouraged is that, okay, autonomous vehicles actually have to take these driving tests. And this is inspired by the way, again, we are evaluated as good drivers. We have to go in, we have to take this test. We argue that self-driving cars should have to do the same thing. The only problem is then we have to codify these driving rules. And so what we did is basically created a way that we could learn those driving rules from text. And eventually what we want to do is dynamically generate these driving test scenarios in different environments. And again, that's part of the larger vision that we have with this Tracer grant. So let me kind of describe what that looks like. And this is all done, you know, there is no generative AI in this pipeline at all. We are working on validating our approach with generative AI to see how well that they do with generating driving rules versus our approach, but this is all with a very classic NLP approach. So basically what we did is we collected a bunch of driver's handbooks for different states and different countries. We filtered that, so we looked at the particular chapters that focus on safety. We then basically pre-processed the text, so we removed images and other things, and then we created rules, and we represented those as both natural language rules and as RDF rules, so in symbolic triples, and I'll show a little bit about what that looks like. And then we did a validation, so so this is a semi-supervised process, so making sure that we found, rules that make sense, and then we did both a manual and an automated analysis. So some of the analyses that we did was looking at, how different driving rules are different in different states. I think a good example of that is, I now live in California. I had lived in California before I moved to Boston, but when I moved to Boston and I drove there for the first time, I learned through experience that Boston drivers are a lot more aggressive than California drivers. And what's nice about these types of, if we had these driving rules codified, is that could be something in your autonomous vehicle. If it's trained in California, you can then transfer it to Massachusetts and it would have, a particular type of driving style codified for that environment. So these, we then represent these, so the sort of RDF framework. So it looks like we have a driving handbook. It used to look like this, at least when I was learning to drive. And basically we represent these in a variant of a web rule. So this is called AIR, A Morden RDF. You can kind of see what these look like. So basically they have an ontology built in, but you can define the particular type of rule you're looking at. So you can ensure that pedestrians are safe, and basically it will tell you whether there's a pedestrian in the way or not. And what's really nice about this and representing these as web rules is basically two parts. So one is that these rules could be shared between vehicles. So again, like if I'm driving around and I have an autonomous vehicle, then I can basically just transfer my rules to the person next to me. So you can basically be aware of what they're doing for safer driving. The other thing is you can also combine this with a production level reasoner. I'm including the DIG reasoner here for AIR to basically be able to prove different types of scenarios. So you can basically see what types of things you can infer from the rule set that you have, which I think is a really nice property, again, for thinking about safety and trustworthiness of autonomous driving systems. Okay. So let's see a little bit about what these rules look like. So I'm just showing a couple of these rules. We also have them all, publicly available on GitHub. I can share the link after. But these rules can identify a lot of conditions that maybe are things that we actually aren't aware of as drivers, but would probably be important for us to know, and also definitely important for our autonomous vehicles to know. So one thing that we were able to learn is that if so that's the vehicle that you're in, right? If you encounter a dust storm, then you reduce your speed. Okay. So what's interesting here is, again, if we kind of combine this, the neuro-symbolic approach, if the AV is able to get weather reports and other types of examples there, then you can correlate this to a camera feed and then adapt your driving behavior, right? So if you see, if you know a dust storm is coming and you're able to detect that, then you take some action to adapt your driving behavior in that situation, which I think is a really nice result. Other one, for those of you that don't know, Santa Cruz is along this really windy road, Highway 17, and there are a lot of trailers, and I'm always very cautiously driving around that. And I always think one of the biggest challenges is for vehicles to be on that highway. And so one thing that we were also able to discover through this analysis is that if you encounter something with a trailer, then that can cause a jackknife. So autonomous vehicles can identify if they're pulling a trailer or not, and then they can drive accordingly. Again, there's a way that we can identify sort of the length and the depth of the vehicles in the front and the back, and then the autonomous vehicle can basically preemptively drive accordingly so that they're not going to run into these types of situations. This is a jackknife maneuver. So I think these are just a couple of the rules. A lot of people ask how long this rule set is. It's I think we have 85 rules through 3 different states. And again, that's just because we're looking specifically at the safety rules, and I can talk about some of those after as well. Okay. So I talked about, 2 types of techniques that we can use to kind of combine neurosymbolic approaches for making autonomous vehicles safer, let me talk a little bit more about the ongoing work that we're doing with basically doing explainable AI and Neuro-Symbolic. Okay, so what our vision is largely in my work in my lab is really facilitating coherent communication. And that's with other systems, but also with humans. So, what I've talked about today is largely how you can take some type of learning system, that can be a deep neural net, that can be, um, a generative AI, et cetera, and basically how you pass the output of whatever that system is doing to some type of symbolic system to catch the different errors and failures that that underlying learning system can make. Okay. But really, what we'd want is we'd really want them to communicate better together. And again, I think that's exactly what a lot of us are thinking about with neurosymbolic AI. And what I argue is that we could use explanations, which is largely my area of research in explanatory AI, as a common language to complete these tasks. This is important for things like redundancy, so that you have systems that can solve problems in multiple ways, right? Taking what we saw with the driving rules, using like a very rule-based sort of natural language processing system. We can also, again, compare that to what a generative AI can do, so that we have multiple systems that are solving this interesting problem. Maybe the generative AI finds rules that our system doesn't, and vice versa. This is also important for having hybrid processes, so systems that learn from each other. There's a lot of things that symbolic systems do that are better than learning systems. They're in a lot of cases they're self-explainable, and other things that we'd really want, especially in trustworthiness. So how can we create systems that really learn from each other? And again, using these types of explanations or this symbolic language as a common language. But this is also really important for learning with humans. So I argue here we're using explanations as a debugging language. So for debugging, I mean that humans can improve complex systems. So one of the applications we're also thinking about in my lab is how do we develop this for educational systems. But another part that I think is important is this sort of, capital E education approach, so that complex systems can improve or teach humans. What I think is really interesting about this is that, it's been shown that a lot of AI systems, a lot of opaque AI systems are better at humans at detecting certain things. For example, it's been shown that there are a lot of computer vision systems that are better at detecting cancer earlier than humans alone. Can we use these systems? Can we use explanations to basically teach humans how to detect cancer and other things earlier? So, this is kind of the sort of next steps that we're working on for developing neurosymbolic architectures for coherent communication, always thinking about that in safety critical situations, but also just in general. So, how does that kind of fit in the larger scheme of things? I don't know how many people have talked about the Gartner chart, but many of you guys know Neuro-Symbolic is there for 2025, which is very exciting. And I think there are just so many questions and so many problems that are really occurring here. And one thing that I'm trying to do is to think about how do we generally solve some of the problems that I showed in the beginning of the talk, right? So for example, we have a Tesla, it's driving here, there's the moon here, and it thinks that this moon is a yellow light. What I think is really interesting is, actually, if we just query a common sense knowledge base like ConceptNet, what we find is actually the exact information that we need, that the location of a traffic light is, at the corner of two streets and it's on the street. This would, very easily take care of the case that there can't be a traffic light located up here. The problem that we have is basically, how do we come up with that representation? How do we build that into our system? And this is something that we're working on now. So a lot of the current work in my lab is in taking internal neural net explanations and then combining those with information from knowledge graphs to develop better reasoning of why certain outputs from neural systems are again reasonable or not. So taking what we did in the previous part, the sort of reasonableness monitors, but actually passing that back into the neural network itself. I'm happy to talk about that a little bit more after. Cool. So in conclusion, and you can read about all the work that my lab's doing at our lab website, or feel free, to visit my personal website or send me an email. So, I started by talking about the fact that complex systems can fail in complex ways. And I started by particularly motivating the self-driving car case. I then talked about local sanity checks, so how we can develop a rule-based system around a deep neural network to handle the different error cases that you could run into in a self-driving car. I then talked about how do we encode these types of driving rules, how do we learn these from natural language text, and how can we use that to share information amongst vehicles and hopefully use that to codify what we would need in dynamic driving scenarios. And then I ended with some ongoing work that we're doing in explainable AI and combining that with neuro-symbolic behaviors. And the goal, of the work that I'm doing and this talk was basically, how do we make sure that our autonomous vehicles don't act like this? Great. So I think that was all I wanted to talk about today, and I think we have some time for questions.
All right. Thanks so much, Leilani. Great talk. So, hopefully everyone can tell, super important stuff. Not enough people working on this. You want a great topic to work on that helps the world. Go work with Leilani. So now let me pass on a few questions. So first of all, comment George S. from Boston says hello, but he didn't actually counter your claims that Boston drivers are more aggressive. So I think that's implicit agreement. Okay. How would the representations with implicit rules work in the initial Uber crash example? In that case, wouldn't recognizing anything be helpful? For example, a cycle or woman?
Yeah, so I think, one of the problems is that a lot of these parts of a self-driving car, and I didn't talk about that in detail, but a lot of them are opaque. And some of them are opaque because they're trade secrets, some of them are opaque because they're computer vision systems. So one of the things to note is that you're absolutely right. If we detected anything, that's definitely important. But the vehicle planner is not incentivized to do that. So in a lot of self-driving car architectures, they are only incentivized to stop for objects when they're very certain of what they saw. So they're past a certain threshold. Yet when we see something as drivers, I don't care if I'm 95% sure that I saw, a person crossing the street. If I see something moving, I'm going to stop for it. And that's what the implicit rules are for. So they say, okay, I don't care if you told the vehicle planner not to stop. If I see any type of detection and it's of any type of size that I care about, if it's any type of threat that we call, that's something that we stop for. So a lot of these approaches are important because again, the existing autonomous driving vehicle stack that we have doesn't allow us to make those interrupts, which is why we kind of build our own system on top of it.
Okay, I'll just mention something. So I spoke with a self-driving car company not long ago, and a person was very stressed out. And I mentioned Neuro-Symbolic AI, and they never heard of it. But also, person was telling me, we're trying to get rid of all the rules, actually. We have some rules, but we're trying to get rid of them. Like, ooh, this sounds terrible. So I think there's a deep hints at a deeper philosophical divide. It's at one extreme, it's actually been declared by some. We need to drive knowledge, human knowledge, to zero, drive data to the max, and let the data speak for themselves, and so on. Now, I think the self-driving car, ethos that's in many of these companies right now, it sort of seems like it's that. So, first of all, are they using rules? What's the real story? And what's your take on this philosophical kind of issue?
Yeah. So I guess one thing I should say also, because I'm seeing some of the questions, and I can't talk about particular car manufacturers. I don't work with any autonomous vehicle companies right now. I would love to. If anyone has contacts that's interested in this stuff, let me know. But again, a lot of these algorithms are trade secrets, so I can't tell you exactly what they're doing. Even in the Uber self-driving car accident, which is something that I spent the majority of my PhD thesis analyzing and working on. I still don't know exactly what I only know from the vehicle reports and the testimony what we have. I don't have like a complete spec of the system. But I guess to your debate question, I think it's very interesting. And of course, I'm kind of on the neuro-symbolic side. I think, by design, and that's why I'm here. I mean, I just don't think that we are ever going to have enough data to represent all the cases that we run into. I mean, I think a great example of this is, so again, plug for Nessie at UC Santa Cruz, but Santa Cruz is a beautiful area with a lot of different microclimates. And so what happens is we have a lot of really interesting animals on campus. I think one of the best examples, we have a lot of turkeys. And there are a lot of students that have never seen turkeys in their entire life. And all of a sudden there's a flock of turkeys crossing the street. And these students who have never drove in Santa Cruz before, they've never seen this data, automatically know what to do in the case of a turkey crossing the street. They all stop, right? And I just have a hard time believing that there's going to be additional data for turkeys crossing the street, for other types of common sense scenarios. I think one that's really interesting, I always point to is if you see a skateboard go across the street, like a skateboard, without a person on it, I automatically think a group of kids is coming, even if I haven't seen that exact scenario, right? I'm always very weary if I see that, because then I think they're going to be children and, they act recklessly. And again, that's something that we can represent with rules, even if we haven't seen that data point before. So that would be my argument. But I know that it would be wonderful if we had that type of data set, but I don't think we're going to get there.
Here's a question. How adaptable are these sorts of rules-based systems when presumably the knowledge bases contain a finite set of operational/visual/behavioral conditions?
Yeah, no, it's a really good question. It's what we are investigating that right now. I mean, that's our exact approach is basically like, how can we supplement rules with knowledge bases with the existing computer vision system? For us, it's been very adaptable, but we have a very interesting scenario, because we're assuming that these computer vision systems that we're typically monitoring are like over 95% accurate, right? So we're just looking for like very particular parts of knowledge to supplement that like 5% of errors. Of course, that's not going to work if you have a system that's always wrong. But because of, the types of scenarios we've looked at, which have mainly been in simulation with different types of threats, for us, it's been adaptable. Again, we haven't deployed this in like a real world robot. That's something we're hoping to do. But I think, to your question, for this issue of like, I guess you would call it coverage or enclosure, we would ideally want a human in the loop. I think that's something that we're going to have to build in. That was kind of part of my last slides, but we haven't gotten there yet. But again, for the scenarios we've looked at, because it's been in simulation, because we have these certain assumptions, it's been pretty adaptable. But of course, for any type of real world deployment, we're going to need a lot of other people in the system.
I'm going to paraphrase a few questions. So would you learn this knowledge base / rules from the real world? And is one? Maybe start with that one.
Yes and no. I mean, it's been very interesting. This is maybe an aside point. I spent a lot of time talking to expert drivers to try and learn their behaviors for both the codifying, but also for validating our system. And I think there's some importance in that, and then there's some not. A lot of us are actually very difficult. It's very difficult for a lot of humans to explain what makes a good driver. And it's very hard. I know there's another question about the semantics. It's very hard to say, oh, a good driver is very cautious, and then take that and represent it in the rule. So again, I think a lot of it, I think a neuro-symbolic system can also be a system where the, neural part is a human, right? So I think part of that is also taking the human explanation and then representing that as a rule, and that in itself is an open problem. But I would say we can get so far, but we also need, formalized knowledge, which is a lot of what we're trying to develop.
Here's a question. You already partly answered this. Do different car companies have different knowledge bases? And is the government involved in setting standards for symbolic/explainable AI? Should all these stakeholders be involved?
So again, I don't know what car companies do. I assume that they all have I assume they all have different knowledge bases if they exist. Some of them may not. Again, as Alexander said, a lot of these car companies really want to go just data as like a first pass. So that I don't know about. The government is involved in describing some standards for explainable AI, but not as much as other places around the world. At least the US is very behind. In the EU, they have the right to explanation and they define what that means. Of course, with the AI Act, there is some language in there, but I think it would be really useful if we had standardized knowledge that autonomous vehicles need to have to be deemed safe. And I've done I do a good amount of work with policy as well. I went and talked to congressional staff exactly about that we need driving tests for autonomous vehicles. I don't know where that's going, but as of right now, there's from what I understand, and again, I'm not in the internal discussions with autonomous vehicle companies. There's not a whole lot of regulation around autonomous vehicles and not a whole lot of government oversight.
Question regarding driving tests, shouldn't we rather make an effort to avoid testing of autonomous vehicles analogous to humans, as this would be projecting metrics based on human cognitive structure and errors onto a system that is fundamentally different in how it learns and acts?
You're absolutely right. And I think we need to start somewhere. I mean, again, the fact that if I had an autonomous vehicle and I wanted it on the road, I just have to have somebody sign off on it, I think is not okay, right? We should have everybody, everyone who's on the road, whether that's an autonomous vehicle or a human, has to be held to like a similar standard of safety. So I totally agree with you, but I think we need some type of test. And I think we can start with similar to what humans do for tests, and then we can make that, a much more grandiose set of evaluations. But I do think a big part of that is the dynamic aspect, because I even remember from my driving test, I had to go through a construction zone and I was sweating. I was so nervous, right? This can't just be something in a simulation that you could hard code. This should actually be some type of dynamic environment that's different day per day, so that there can't be any type of memorization or other hard-coded situations. But I agree. I mean, I'm talking about the driving test as like a first step, and then we can get to a more holistic evaluation.
Does the evaluation of rules help the latency of the system because they're computationally easier to evaluate than a neural net, or do they actually add weight to the system?
That's a very good question. We haven't had any issues with latency, but that's also because of the abstraction that we have for the rules. So again, we're only looking at like a set of 80 rules at a time. So we don't have this type of rule blow up situation that you would get. Of course, I'm sure if that was a larger set, you'd have a lot more latency. And again, they are computationally easier because it's usually just one rule is triggered at a time. It's not like you're looking at a huge set. And again, that's by design. That's how we designed it. I think if you're to learn rules through experience, which is something we started looking at, you would have that problem. But we haven't run into that yet.
Okay, one more question from me. Yeah, you showed a little bit of your common sense rules and so on. Could you say a little bit about, sort of from a symbolic AI standpoint, are you using a kind of situation calculus, or is it, to what extent do you have temporal logic in there, or, and so on. Also, the relationship with probabilities. I really like the reasonableness calculus, or whatever you call it, but it makes a lot of sense. It's maybe helps put in lots of knowledge in a much more intuitive way, and therefore makes it faster and easier for people to put in that knowledge. You get more detailed though with probabilities and even causality, but things in my experience tend to mushroom as far as the complexity to, knowledge engineers when you do that, but obviously would have advantages. Can you comment on the form, of your kind of knowledge language?
Yeah, great question. So, I mean, everything I showed today was like first order logic. So nothing today was in any type of temporal logic. We do have other systems that do that. In fact, we use a tool from my collaborator at UC Santa Cruz, also on the grant, Daniel Fremont Scenic, which is using a temporal logic, a modal logic, which has been really interesting. So we've been trying to translate this, which doesn't always work out. But yeah, everything I showed today was first order logic, moment in time. But I think that there's a lot of space for exactly what you said, which is, incorporating different probabilities or confidence measures. I would love to do that. We haven't had the time to. And then again, we are working on higher order logics as well as temporal logics. But today I showed it just for single, again, looking at things frame by frame, which has worked well for us in the past, but now we're thinking about that more dynamically.
Okay, leave it at that. So let me just say, for all those people who are like, oh, AI needs to have a world model, this is exactly what Leilani is doing. Okay, so and she's, for very well motivated reasons. So it's a poster child for why we need world models. So thank you so much, Leilani. I follow her work. Go be her PhD student. All right. Next up, we have a tutorial. This is Mateo and Pietro from Cambridge. Are they here? Hey, all right.
Hello.
Hello.
Okay, so this is I saw an earlier version of their tutorial, which I thought was great. Triple AI. So they're going to talk about concept bottleneck models and more. So let me pass it to you guys. And, so I think this would be a nice setup for other things later about interpretability. And so fantastic stuff. Take it away, guys.
Okay. Let me share my screen, if I can make it. No, why I can't? I actually don't see my slide deck, but I can share my whole screen. Okay. Can you see anything? Can you just ping me with like a vocal feedback? Thanks. Okay, so this talk is about foundations of interpretable models. I'm Pietro Barbiero. I'm a Swiss postdoctoral fellow at IBM Research, and I will give this talk with Mateo Espinosa Zarlenga, final year PhD student from the University of Cambridge. I will discuss the first part of this talk, and we'll dig into what interpretability is, the foundations of interpretability, so what are the underlying assumptions, design principles, and we'll provide the structure of a blueprint for interpretable models. And in the second part of this talk, Mateo will talk about the instantiations of this blueprint and discuss a few open questions. Just a heads up, we'll give at the end of the tutorial like the link to the slides, so you can also download papers and materials that we discuss during this talk. So let's start about what interpretability is and why do we need interpretability in the first place. I think the previous talk was already giving us a few hints on why do we need interpretability in the first place, so I will be a bit quick on this part of the talk. The main reason, underlying reason why we may need interpretability is that a few modern AI techniques are highly parametric. They have complicated inference steps. So we don't really know how decisions are made inside these models. And blindly using these models may lead to all sorts of issues, as we have seen already in the previous talks, including hidden biases that we don't know, we may not be aware that the model is using in order to take decisions. And as we mentioned already, in Europe, at least, we have now the right to the explanation. And so users of AI models now have the right to ask for a clear and meaningful explanation for why a decision was made. So these are, I guess, the two main reasons why we need interpretability. But when are we looking at the interpretability in the literature? We may ask, well, how is interpretability defined in the current literature? And we have been looking at papers that try to define what interpretability is, and we were struggling to find a formal definition of interpretability, which might be one of the reasons why current research in interpretability is struggling in finding a unifying view of this field, and in finding the design principles that are and assumptions that are required to build interpretable models. Like recently in 2023, there is also a claim in a book saying that there is no universal mathematical definition of interpretability, and there never will be. And we think this is actually scary for the field, because if we cannot even define what interpretability is, then what are we even doing? It's worth mentioning that in other fields, like in formal systems, interpretability is actually well defined and has been formalized for since like 80 years ago. And but if we just plug and play these kind of definitions into modern AI, we might run into issues. The first one is that these kind of definitions usually come with a substantial background theory that we may need to consider. They may not be relevant as a whole for modern AI. These definitions they have not been contextualized in modern AI. So we don't know how to drive conclusions for modern AI, how to use different definitions to drive research in modern AI. So the first problem that we are discussing in this talk is, can we then provide a general and simple and actionable definition of interpretability to make this space a bit more well-defined? And to do that, we are going to consider a simple setting, a very general setting. We're going to consider a probabilistic model and the task of predicting a target Y given a set of features X describing a few objects. And we're going to use a probabilistic model, a probabilistic function that takes these inputs as these features as inputs and tries to predict the target. Now, and the kind of question we are going to ask is whether this probabilistic model is interpretable. And one way to approach this problem is to start associating semantics, a meaning to the features and the target that we are discussing now. So we can associate, for instance, the string 1 to x1, red to x2, and even to the target y. And in this way, we can establish a relation between what the model is doing and human knowledge, for instance, number theory. And if we are looking at how the model is making inferences on objects, then we can observe that we may also make an inference that is similar to, like, given the same input, we are reaching similar conclusions. And we can formalize this with the mapping that we established between the features and the strings that we defined, that basically define a translation function between the way the model is looking at objects and the way we describe the objects. And now, if we look at this diagram that we have just built, you can see that if we make inference using the model first and then translate the result in our reference system, this is we can reach the same conclusion as we would if we first translate the features into our own reference system and make inference ourselves. And if this diagram commutes. So if we reach the same results given the same input, then it means that the inference mechanism of the model and our inference mechanism are the same for the same inputs. So it means that kind of we can kind of understand what the model is doing because we make the same decisions for the same inputs. And this we call this property inference equivariance. And we say that if a model is making inference that are equivariant to humans for any possible input, then basically we are equivalent in this kind of task. And we can understand the model. Now, if we take this as a definition of interpretability, there are at least three consequences we can consider. One is that any function in theory is interpretable. We just need to verify inference equivariance for any possible input. The second one is that interpretability is a spectrum. It's not a yes or no property, because it may hold, inference equivariance may only hold for a subset of samples. So we may only partially understand the model. And post-hoc methods that we used in the past for explainability actually complicate interpretability, because instead of having one diagram where we need to verify inference equivariance, now we need two diagrams. One where we have a surrogate model that is trying to explain a very complex model like a deep neural network. And then we have another inference equivariance to verify that is the one between the surrogate model and the human. So it's actually more complicated. We're introducing more checks that we have to make. And there are the three consequences that are the three main topics of the first part of this talk. The first one is that if we want to naively verify inference equivariance, this is an intractable problem, because the size of the table that we use to describe the function that we just discussed is exponential in the number of features in inputs. So if we consider like problems that we just discussed, like image recognition tasks, where we have a high dimensional input, this is already intractable. Like we need more checks than the number of atoms in the observable universe. Second problem is that many translations might exist, and we may need a way to find the right one, and it's not obvious which one we would prefer. And then some translations are not sound, so they don't preserve some properties that we may require. So in this case, we are actually misinterpreting what the model is doing. So in the first part of this talk, we are going to discuss these three questions. And the first one is, can we identify underlying assumptions and principles to make inference equivariance more tractable? And to do that, we are going to dig into representation learning, which is the idea that if you have a high dimensional space and you want to predict a task, the underlying assumption is that you can solve this if you define an intermediate in another space that is lower dimensional. So we are compressing information, but we are preserving the information that is needed in order to solve the task. Now, then in some cases, we may be able to condition the task on this intermediate subspace such that any feature that is not, any information that is not in this subspace is unnecessary to explain the task. So basically, the task is independent on the input, a high dimensional input now, given this intermediate subspace. So the high dimensional input is not needed anymore for understanding what the model is doing. If this is true, then we can factorize the joint probability over these these spaces as two factors. One, where the task is conditioned on this intermediate space, and the second factor that gives the dependence of this space with respect to the input space. But when we want to understand how the model is making inference, we can verify now inference equivariance only on the first factor that is exponentially easier than with respect to considering inference equivariance with respect to high dimensional input now. So this is the underlying idea that we can take from representation learning to make inference equivariance more tractable. We need to project the input into a low dimensional space. Now, The second question that we are going to discuss is, can we characterize sound translations? And to do that, we are going to use a structure that we call concepts. And so before digging into sound translations, we are going to need a definition of what a concept is. And to do that, we are going to use an example. We are going to do this by example. This is a table that describes a set of objects using a few strings, where we have one if the object satisfied the property of the string, and 0 otherwise. And if we consider a string, a column of this table, we can define a function of a column of this table that, given a column, it gives us, for instance, red, it gives us all objects that are red. And at the same time, we can define a function of the rows of this table that, given a set of rows, it gives us the subset of sentences of strings that are satisfied by all objects in this set. And we are going to use these two functions to define what a concept is. And we say that basically a concept is a set of examples, so a set of these objects, and a set of sentences, so these strings, that satisfy a specific closure condition. So what is the concept red? The concept red is basically a structure that is defined by these equations. So it's a property that, given a set of objects, all these objects satisfy the string red, and given the string red, we get exactly the same objects that we give in an input. So when we compose the function gamma and beta, we are basically in this closed loop where we can compose these functions and we already return to the initial point. It's a fixed point, basically. Well, given this definition of a concept that is grounded in institution theory, we can also give practically, we can extend this definition into a probabilistic setting where we can then construct probability distribution of concepts when we condition them on a specific input. And Mateo will talk more about how we can do that in practice. But our question was, how can we use concepts to define when a translation is sound? Well, a sound translation preserves concept closure. So basically, if we have a set of objects and we describe these objects in a specific language, let's say English, and we translate this sentence into another language, let's say Latin, then when we mapped again using the beta function that we have in the Latin language back to the set of objects that make this sentence true, then the initial set of objects and the final set of objects are actually the same. While a translation that is not sound doesn't preserve this property, doesn't preserve concept closure. So if we compose gamma and beta function of different languages through a translation, the initial set of objects and the final set of objects are different, like in this example. So and now we have like representation learning that we used to compress the space, and the idea that now that we discussed how this space how can we construct translations such that we have sound translations in this space. The last question that we're going to discuss is how to choose among a set of sound translations when we have more than one that is viable for our problem. And the idea is that for a given set of instances, you may have different ways to translate what the model is doing into another reference system. And unfortunately, this happens whenever the model and the data together satisfy some conditions that basically allow this to happen. And when this happens, then there is no way to augment the data or find other or train longer the model. It's actually a property of the structure of the model and the kind of data that you have that are just observational data. And we say that in this case, finding the aligned translation, so the ideal translation, is not identifiable. And there's a whole field that is discussing identifiability theory, especially in causality, that says that whenever we don't have enough information or specific data in order to identify causal structures, the only way to proceed is to define a prior over in this case, aligned translations. And this is basically where a Neuro-Symbolic can or background knowledge can come into play. And based on what we have said, so based on the principles of representation learning, we can now discuss a few design considerations briefly that we can make on the models that we deem that we say that they are interpretable. There are some underlying principles that we have in any interpretable model. Basically, interpretable models need to compress information, so they need a sort of principle of concept invariance, so that they can discard information. The functions that we need in order to compress information also need to preserve the information that is needed for the task. So they need to respect some sort of concept equivariance. And when we discuss the function that from concept solves the task, we can use we can describe the main properties of this factor using categorical structures. Like here, one possibility is to use copy discard categorical structures that allow a sound definition of compositionality and sparsity, and they also model very well and formally different kind of human model interactions, like do interventions to estimate causal effects, and ground truth interventions that allow users to improve model predictions. And Mateo will talk more about this kind of interventions. Now, based on all these assumptions, principle discussions, we can give a very high-level description of what an interpretable model is in summary. And the idea is that you need three blocks. First, a lossless compression in order to get from a high dimensional space into a lower dimensional space that is still informative of the final task. We need an alignment prior to and pick an aligned translation to translate the representations of the model into into a representation that is aligned with the users. And finally, we need a compositional and sparse predictor that, given these aligned concepts, it returns the final task. And in the second part of the tutorial, Mateo will talk about instantiations of this blueprint. So I will stop sharing my screen, and I will give will give the floor to Mateo.
Sorry, can you guys see my screen and hear me? I hope. Fantastic. All right. Pietro, you may have to stop sharing yours, I think. It's a bit of a... Cool, amazing, awesome. Well, thank you so much, Pietro. All right, so now that we've talked about a blueprint for how can we construct and build interpretable architectures, particularly deep neural networks, which is the thing that we're going to be focusing on today, let's try to see actually how you can do this in practice, how you can actually build models that can make predictions, and you can explain those predictions with what we call concepts. And for this, we're going to be looking at this into two ways. We're going to split out the methods that we're going to be talking today into based on the main component of the blueprint that they modify. This is going to leave us to first talking about the first two parts of the blueprint. This is what we call the concept encoder, which is this probability of the concepts and theta given x, and the alignment mechanism. So this actually, we're going to be focusing mostly on how do we represent concepts and how we align those concepts. And then on the second part of the talk, of this sort of this section, we're going to look at the last part of the blueprint, which is this label predictor, and we're going to be focusing on how do we predict tasks once we have these concept representations. Now, this is an incredibly rich and large field, so there's absolutely no way I'm going to be able to talk about all of these things. However, as I'm going to be giving some of the examples, I'm going to be providing a lot of links which you can follow through if there's a specific area that you're interested in and you would like to follow through on this. Now, I'm aware that my name may be on somewhere where I put the references as well as QR codes, as well as my image. So if that happens, don't worry. We're going to put the slides online so you can actually look at them at your own pace later on. Okay, so without further ado, let's go ahead and start looking at the first part of this blueprint, like how can we instantiate that concept encoder, the P of C given X. Now for this, we're going to make a few assumptions that I hope will sort of make it a bit easier to build into this discussion, but we're going to slowly start removing these assumptions. But the first one is that for now, we're going to assume that the task predictor, the P of Y given C, will be parameterized as some interpretable, say, a linear layer, like a sparse linear layer. This was just going to make things a bit easier for now. And specifically, we're going to assume that the parameters of this model are going to be deterministic and learnable, meaning that for all samples X, we're going to use exactly the same weights. This is another way of saying that these P of C and theta given X, so the P of the concepts and the parameters given X, can be decomposed into the P of the concepts given X, which is the thing that we're going to be focusing on for now, and the P of theta given X, and the P of theta will be just be some delta distribution that is the same for all samples. So all samples will have exactly the same weights in the level in the task predictor. And then finally, we're going to be parameterizing this P of C given X as a deep neural network G of X. And this is the thing that we're going to be focusing on. In how do we actually represent concepts with a neural network, and how do we do this in ways that achieve some objectives that we have in mind? Now, the most naive and simplest way that you can do this, the thing that probably most of us would think immediately, is if you want to encode a bunch of concepts, why don't we just use some sort of big bounded scalar concept representations? In other words, why don't we use probes, where we have a G model for each of the concepts of interest. For example, if we're interested in the concept of stripes, and we're interested in the concept of claws, we're going to have two separate models, G of stripes and G of claws, that take the input, and whenever the input has stripes, it outputs a value close to 1. Whenever it doesn't have stripes, it outputs a value close to 0, like we see here. And whenever we have, for example, claws, a value without a load to 0, it means that there's no claws, and when it has close to 1, it means that it has claws. Now, this is the simplest thing that we can do. And if you have a bunch of these little probes, a bunch of all the concepts that you care about your task, then you can construct something that's called a concept bottleneck model, or a CBM for short, which is a sort of quintessential architecture in this interpretable space. And this architecture works by assuming three main things. And again, we're going to start slowly relaxing this later on. But for now, we're going to assume that we always have a set of binary concept labels C for each training sample. And we're going to assume that each of these concepts in this set of concepts C can be independently predicted from X. So just like we did with the pros, we can independently predict stripes than from claws as well. And then the last assumption is we're going to assume that the downstream task label Y can be perfectly predicted from C alone. So we have this very simple structure with observing the input features X, we can predict the concept C, and from C, we can predict perfectly the downstream tasks Y. If we assume this, the way this maps to an actual deep neural network is by having a deep neural network that has two components. The first component is the concept encoder, G of X, that takes a set of input features X and maps into a set of high-level concepts C hat, which are concepts that are of interest to predicting the downstream tasks that we care about. So for example, if we're interested in predicting the osteoarthritis grade based on the X-ray of a knee, this could be things like where there's a sclerosis on the model, in the image, where there's bone spurs in the image, osteophytes, narrow joint space, and so on, things that radiologists would care for this prediction. And then the second part of the deep neural network takes this set of concept predictions. Remember, these are going to be activations where they're either 0 or 1 or somewhere in between. Takes this set of concept activations, puts them into a single bottleneck, and then it makes a label prediction using an interpretable model like a linear layer for now. Now, because this label predictor can only see this set of high-level concepts as its input, you can think of these concepts as an explanation for the downstream task prediction. So how do you actually train the CBM? How do you do this? How do you do this alignment that we were talking about? Now we have these concept representations. We want to make sure that they're aligned to notions that that the osteophytes is always on with our osteophytes in the image and off otherwise. So the way we do this in CBMs is we're going to encourage this alignment by using the training set, and we're going to use also some losses to actually encourage the alignment. So the most simplest way is given a training set where they have, for every sample X, you have some concept annotations as well as the downstream task annotation. You can first, the most simplest way to do it is to train them all independently. You first train the concept encoder G of X to be able to predict the downstream type, the ground truth concepts from the input X, and you do this by aligning the output of G of X through a binary cross entropy that makes sure that the output of this model, which is going to be a bunch of binary neurons for each of the as many concepts you have, is the same as the output granted concepts. And then separately, you also train the task predictor f of c so that its output, when given the ground truth concepts, is aligned with the ground truth task label. And you do this independently. You can train this separately, and you put them together, and you get that with your CBM. That's the simplest way to do it. Now, the sort of next step would be to do it sequentially, where you first train g of x just like you do independently. So you train to minimize the alignment between the output and the ground truth concepts. But then you freeze it, and then you train the level predictor f based on the outputs of g of x. The idea here is that this model can actually be more accurate at test time when the model g of x is not able to always properly learn this concept, so they're not always going to be accurate, but it can still use these sort of soft representations to make its downstream task prediction. And then finally, to take it even a step higher, this will be the joint training, where you train both g of x and f of c at the same time through a weighted loss. And this weighted loss has a component that encourages alignment with the bottleneck layer and the concept activations, and it makes sure that the output, just like any normal deep neural network, is aligned with this like expected output, in this case, at level y. And then you have some sort of regularization parameter lambda here, which controls how much we value concept alignment versus task alignment. So one of the things that this sort of architecture, this very, very simple architecture, by the way, allows you to do is it supports a sort of powerful human-AI interactions that Pietro previously mentioned. And specifically, it supports something called test time concept interventions, whereas an expert interacting with the CBM at test time can look at the input, it can look at some of the concepts that the model predicted, for example, the concept of brown, and realize that some of them are wrong. So you can go ahead and correct mispredicted concepts, switching the prediction of concept of brown from 1 to 0, and then allowing the level predictor to update its prediction from an okapi to a zebra, getting the correct label. Now, you may be wondering, if you already have the expert, why don't we just ask them to predict the downstream task? Well, the usefulness of this is that you can think of concepts as a bit of a shared vocabulary between the model and experts. That is much simpler to solve than the downstream task. So I would argue that most people would know what the color brown is, but a lot of people wouldn't know what an okapi is. But however, those people that only know what brown is can actually fix the model and help it predict accurately the model just by fixing the things that they know, the simple things, and let the hard task prediction be done by the model itself. So in practice, it leads to very powerful interactions where the more you intervene, so the x-axis of this plot, the higher the task accuracy of the model becomes at test time. And if you're interested in this area, there's a lot of interesting papers. It's quite a developed area of research that look at, for example, how you pick the best concept to intervene on next, or how can the model learn to do so. And I put some references here if you want to follow up on those. Okay, so far we've talked about CBMs, and CBMs are a theoretical, useful framework. However, they, as you can imagine, they're highly constrained in practice because of this information bottleneck that their boundary scalar encodings impose. So if you have some very complicated test distribution, or like data distribution, and we try to encode it into a very small number of sets of concepts from which we then need to predict the downstream task, if this set of concepts is not informative enough about the downstream task, if it's not what we call complete, then the model will really struggle to perform accurately in that task. And we see this in practice as follows. Like if we change the number of concepts used during training and we reduce it, so we go left in this plot, we see that the test accuracy of the model becomes worse and worse as we go, and it really tanks at the end when you have very little concepts. And that's because the set of concepts in your bottleneck is not going to be informative enough to be useful for your task, and the model has this very this struggle between being accurate in the concepts and being accurate in the task. So you end up with this trade-off that it really limits its ability to be useful in practice, where most of the time concepts will be incomplete. So this begs the question then, how can we actually assign concept representations, this P of C given X, that operate in incompleteness? And the simplest way to do this is by learning, instead of a single scalar per concept, learning a dynamic embedding representation, so a high-dimensional vector for each of the concepts. For example, each of the concepts, say cysts, instead of having a single neuron for each of the concept, we're going to have a bunch of neurons, and those neurons are going to be generated by a concept generator, an embedding generator, which in this case we call phi of I. And this is useful as long as two properties are satisfied. The first of these properties is that we want this embedding space that we're learning, this dynamic embedded space, to be very separable when the concept between samples that have the concept and samples that do not have the concept. So for example, the bond spurs, we want to have very different spaces for when the sample has the bond spur and when the sample does not have bond spur. Why do we want that? Because if we are able to clearly separate samples with bounce pairs and no bounce pairs in this embedding space, we can can easily identify whether the concept is on or off, and we can construct an explanation from a concept-based explanation for our prediction. And the second space is that we want the model to use this extra dimensional dimension space that it's learning to actually encode things that are useful for the downstream task prediction, but we're not given during training. So encode concepts that were not given during training, but are really necessary to predict downstream tasks. For example, you can learn to use a very separate subspace to learn about marginal bounce pairs, and you can learn a completely different subspace to encode, for example, central bounce pairs, both of which are very important to be able to predict orthosteric grade. And in practice, this can be done with something called a concept embedding model, or a CEM for short, where what we do is we're going to generate a concept embedding C of I for each of the concepts, and we're going to write it as a mixture between two representations. A positive representation, which we use to represent the concept when it's on or present, and a negative representation, C of minus, which we use to represent the concept when it's off or absent. And we're going to mix them based on whether we believe the concept is there or not there. So if we think the concept is there, so P of I of X is high, is close to 1, then we're going to output pretty much exactly the positive embedding. And if we think it's not there, so P of I is 0, we're going to output the negative embedding. So we're going to have this sort of mixture where we get closer to the distribution of positive embeddings if it's on, or negative to the negative distribution if it's off. And the nice thing about this is that C plus, C negative, P of I, these all can be learned as interpretable. It can be learned into using very simple differentiable deep neural networks. And more importantly, you can actually intervene on this model. You can intervene by just fixing the embedding that you pick to the one that you think is aligned with the concept that's on or off in the image. So if you think the concept is present, you can fix this guy to C of plus. And if you think the concept is off in the image or in the input, you can fix that to C of minus. So this model allows you to have high dimensional embeddings that allow high performance in the downstream, even when your concept is incomplete, and it still remains intervenable, which is highly desirable for this sort of models. Now, more recent works, obviously not going to have time to talk about this, but the more recent works have adapted concept embeddings to, for example, enable better calibrated uncertainty estimates through something called probabilistic CVMs, to also compute arbitrary conditional distributions between concepts and tasks. These are called energy-based CVMs. Some of the works that we've been involved also have used embeddings to learn to ask for effective concept interventions, because when you have embedded representations, you can represent interventions in a differential manner, so you can optimize over them. And these are called intervention-aware CEMs. And then more recently, we had a work, for example, in XML, where we show how you can use these sort of representations to better generalize within our distribution shifts, something called mixed CEMs. Now, one final way of representing concepts. So we talked so far about bounded scalar concept representations, dynamic embeddings. And the last one that we're going to talk about is to use unbounded scalar concept representations, in particularly large set of those representations. One of the earliest approaches to do this is something called concept widening. It's something called concept widening, where for some reason this is not playing, but that's okay. It should be something like that. Something called concept widening, where you sort of rotate the output of a batch normalization layer. Particularly, you actually rotate the output of a widened layer, so that each of the activations are aligned with the latent space with a specific concept that you care about. And this has been taken to a different step with something called post-hoc CVMs, or PCVMs for short, where you take a pre-trained deep neural network in the task that you're interested in, you use this latent space, and then you project it into a concept space using some sort of linear concept probes. So you have this very powerful model that you train, you look at this latent space, and you learn probes to separate samples that have a concept versus samples that do not have a concept. And then once you have that, you can actually project the latent space into scores, into unbounded scores, from which you can then learn an interpretable predictor like a sparse linear layer as before. What I think is more interesting in this area, however, is the fact that you can do the same thing without probes by using actually language textual descriptions of the concepts. So if you have access to a multimodal model like CLIP. So for example, you can have descriptions of the concepts like the concept of stripes, horse, main. You can map them into a CLIP vector using a text encoder. You can map the inputs of the images into their image and vectors using the CLIP image encoder, and then you can generate scores by doing the dot product or the cosine similarity between them, and then you can learn an interpretable predictor from that. And in particular, this is very useful because it can sort of really easily be turned into a fully unsupervised pipeline if you exploit language models as knowledge bases and multimodal embeddings as annotators. So you can literally go ahead and ask ChatGPT, hey, ChatGPT, list the most important features for recognizing something as, I don't know, a dog, and it'll tell you a tail, fur, 4 legs, snout, and so on. And then you can go ahead and generate clip embeddings for each of these keywords, and then use those to generate scores for image, and you can have a model that is concept-based interpretable without having the concept annotations, which is a huge pipeline. It's a huge pipeline sort of bottleneck. These approaches are called level 3 CVMs or language-guided bottlenecks, and are one of the most popular approaches nowadays. So there's a lot of research going on there. Now, so far, we have assumed that we align concept representations and human understandable concepts by either minimizing a cross-entropy term, like in the bounded scalar representations, or by projecting samples into the direction correlated with each concept, like in CLIP in the post-hoc CVM example. However, I'm not going to have a lot of time to talk about this, but there is a lot of issues about aligning things, for example, with cross-entropy particularly, which leads to these representations leaking a lot of unwanted information about each other and about the downstream task. And this is because cross-entropy requires you to always make predictions and accurate predictions, even when the concepts are not visible, when they're opaque, or when they're really hard to predict. So the model undoubtedly learns to exploit dispersed correlations, and it learns to leak a lot of things in these representations that you do not want. There's been a lot of research to sort of try to rethink how you can do alignment to avoid this. So for example, some works like GlanceNet try to frame this alignment as a disentanglement learning task. And more recently, autoregressive CVMs or stochastic CVMs have sort of exploited the fact that have included in the architecture the modeling of concept relationships, so the model doesn't have to encode cross-concept relationships as part of leakage in the representations. Awesome. All right, so far we talked a lot mostly about how do we encode concepts and how do we align them. Now let's talk about the last part of the blueprint. How do we predict tasks once we have these concept representations? Now, as mentioned, one of the initial assumptions that we did in this part was we're assuming that the level predictor Y was always a linear layer. However, as you can imagine, linear models are not very expressive, and they may struggle to actually learn complex nonlinear relationships between concepts and labels, which makes them not accurate in a lot of complex tasks. So let's now look at different ways of parameterizing this P of theta given X and the P of Y given C, so that we can learn more powerful, but yet still interpretable architectures that predict things from concepts. So the simplest way, the first thing you can do is linear models work well. So why don't we just try to make kind of models that are linear-ish, at least in the local neighborhood of the concept of a sample. So a linear model, as before, was just given the concept predictions. You just output the top probability in the weights that you learn and the concept prediction, and you may have some sort of sigmoidal function afterwards or something like that. What we want now is a linear-ish model where we do this, but these weights are going to be a function of the input itself. So they can change based on the input. And this is useful so long as the distribution is parameterized something that we can learn, like a deep neural network. And is also encouraged to be stable for samples with similar concepts. So you have X and X prime, and they're very different feature spaces, but they're very similar. They're almost exactly the same concepts. Then they should be mapped to almost exactly the same linear weights with theta of X. And you can encourage this by using some sort of gradient matching. And if you're interested in this approach, I would recommend going to the paper of self-explained neural networks that we'll link right here. Now, another way to do this is to take more of the Neuro-Symbolic approach, and it's to exploit different parameter spaces such as logic rules. And this is usually done in this space in a two-step fashion. The first step is what we call neural generation, where we usually have one neural network, which is the concept encoder, just like in CVMs, that generates some concepts that are semantically transparent, concepts that we understand. And in this case, because we're working in logic rules, they're going to be bounded concept representations, just like in the CVM. And then you have a second neural network, which we call the rule generator, that gets X and generates some sort of rules for that sample that we're about to execute. And then the second part is interpretable execution, where we have some sort of symbolic engine that execute rules using these predicted concepts, and then generates an output, for example, in this case, determining whether the car should brake or not, given the concept of the green light and the light and the sign of a siren. Now, let's actually see how you can do this in practice. So as an example, we're going to look at something called concept-based memory reasoning, or CMR for short. And here, the first step, as before, would be, let's just predict the concept activations. Let's just predict the scalar concepts representations. And we're going to do this by aligning them just like in the CVM case. We're going to just align them using a cross-entropy, using a training set. Now, the second step is we're going to select a rule embedding from a learnable rulebook using a deep neural network. So we're going to have a rulebook of rules, and these rules are going to be encoded as an embedding. And then what we do is we're going to have this rule selection model where, given X, we're going to select one of these rules. We generate a probability distribution over the rules, and when we sample one of these rules, in this case, we sample, so for example, the rule with embedding E2, because that was more likely than that one. In the third step, we use a learnable model to decode this embedding into an actual rule that we can execute. And the way to do it is quite simple. You go ahead and for each of the concepts that you have in your set, you go ahead and you try to generate 3 different scores. You generate whether the concept should remain positive or as is for the rule that you're about to decode, whether it should be negated or whether it should be irrelevant or ignored for the rule. So in this example, C1, the concept of Kashgar was put as negated. So we want to make a rule that says no C1 or not C1. And then C2 says positive, so we're going to pass it as is. So it's going to say not C1 or C2. And C3 says ignore, irrelevant. So we're not going to even include it because it's not relevant for the task that we care about right now, which is to predict whether we should stop or not. And then the last step, we execute these rules using some sort of differential mechanism like a tenor, where we look at the concept states that we predicted from the concept encoder, we look at the rule that we just sampled, and we actually execute it. So not C1 becomes the value of C1, 1 minus the value of C1, or C2 becomes times the value of C2. And this gives you a score that you can actually then use to predict whether you should break or not. These steps allow CMR to become a universal approximator, similar to like opaque deep networks. But more importantly, in my opinion, it also allows you to decide to provide by design local and global interpretability, which allows you to formally verify desirable properties because you can actually look at the rules, the global rulebook that you learn, and you can see that they're satisfying properties that you want, like, for example, fairness, by looking at the rules and seeing what it's actually learning. Other neuro-symbolic approaches that you may be interested, obviously don't have that time to talk about these, include things like logic explained neural networks, deep prop log, deep concept reasoner, neural algorithmic reasoner, and so on. There's a lot. It's a very rich space. I would absolutely highly recommend following it because there's a lot of things coming up every day. All right, now let's wrap up with a bit of open questions here. So there's still a lot of significant challenges and open questions in concept-based interpretability, particularly making these models more real-world friendly. In particular, as mentioned, level 3 models open the door already for a bit more practical models because you don't require the concept annotations, which is the biggest bottleneck in this issue in this sort of architectures, but they're still not currently as reliable as supervised concept models. For example, it's still very unclear how you can use level 3 models without domain-specific foundation models to do the labeling for you, because we still require to have some sort of labels. What these models do is they just use foundation models and multimodal models to do the labeling, and if you don't have those models available for you for your domain of expertise or your domain of interest, you're sort of doomed right now. So this is a really, really big open question, and it's probably one of the most challenging ones here. The second one is that interventions in this sort of label-free approaches do not work very well. This is because we're using unbounded scalar scores, which are not very easy to intervene because you have to select a threshold to intervene, and that doesn't work really well as in the case of supervised approaches. And then more generally, there's some issues with scalability. Most of these approaches have been done in moderate size models and datasets. So it's kind of unknown whether we can actually scale them to large scale and multimodal approaches. And there's a lot of questions there. Like there's, for example, if you look at transformers or LLMs, where do you even put the concepts? Or what is that like? Do you do this at a token level, or a sentence level, paragraph level, text level? Like where do you actually introduce the concept encoding in the transformer architecture? It's a bit of an unclear question. There's some clear domains where this could work, but the general approach is very unclear. And then what does a concept even really mean? Like what does a concept even really mean in some domains like textual inputs? Does it mean sentiment? Does it mean topic? Does it mean some sort of grammatical feature or something like that? It is unclear. And again, it's very domain specific, similar with other domains like genomics, finance, and law. And there's been some works where they try to do specific models for specific domains like graph data, tabular data, RL, or time series, but there's still a lot of room for improvement in making this sort of use of a concept more general across multiple domains. And then finally, the sort of elephant in the room is whether we can actually even scale these architectures to very large model standards. There's some recent works that have shown that you can do this at least in the fine-tuning level, like something called concept bottleneck LLMs, which was published here at ICLR this year. It's still preliminary work. It's sort of in the sense of it's very early stages, so it's unclear whether it can actually scale where you can train a model from scratch, but it's sort of still nonetheless a bit encouraging. Okay, so just to wrap up, today, we argue that interpretability can be thought as a form of inference equivariance between the predictive process of a machine and the predictive process of a human that is sort of handled by this sound translation between the features and notions of interpretability in the humans. We showed that verifying this equivariance is intractable unless you rely on compressing your input in a set of concepts, which you would like to align with notions of interpretable human concepts through some alignment mechanism. And then we propose a blueprint for designing interpretable models, which is formed by a concept encoder, an alignment mechanism, and a level predictor. And then finally, we discuss some like several instantiations of this blueprint across the literature. If you want to have more, you're interested in this data, want to learn a bit more, we have a website here that you can go into where we have a longer version of the tutorial with extended biography and slides. And we include the slides for the stock already there, so you can go ahead and open them if you want to follow some particular reference there. And we also have a library called PyTorch Concepts, so Parisa, where you have constructs to build concept-based interpretable deep neural networks. Right. Thank you so much for your time. Really, really appreciate it. And it's been a pleasure to be here. And yeah, thank you. Let's now open the floor for questions.
Awesome, guys. Great job. By the way, big leap from the AAA tutorial. So, which I thought was good already. So this is
Thank you.
So questions, by the way, for everyone, these guys are addressing something really foundational. What is the concept? Right? And then, so, this is at the heart of any world model. So many people are not sort of skipping. These guys are starting there. So that's very good. So remember this. Now, here, a question for Pietro. You finished your part saying that lossless compression is necessary in the first place in the transition into the embedded space. However, is there some leeway on the lossless part? Since, for example, modern computer vision models, there's likely some kind of loss during compression.
Yeah, sorry, I was a bit rushing, but I can explain a bit better. So these, we are always compressing information. So it won't be lossless compression in the sense that we can always recover all the information that we had in the input. It's an approximate lossless compression where we can encode in this projected space as much as information as possible that is relevant to solve the task. And we can either encode it in, if we have a set of concepts that are complete, so if concepts are themselves can encode in their scalar nature enough information about the task, then we can use just the concept space. If concepts are not enough, then Mateo discussed a few ways. Like we can either consider higher dimensional representations for concepts, or we can introduce a side layer where we can also project some information on parameters of a rule that we will then apply on concepts. And in both ways, we can preserve more information than we have actually in our training labels.
Okay. Is there a way to automatically generate / validate concepts / features? I think this is referring to when you don't have them manually. So maybe you partly address that with some work, but go ahead.
I'll go. I guess for now, just let me sort of caveat this discussion with saying that these are quite early sort of era of this sort of approaches. So it's everything has been done very ad hoc, and it doesn't have a lot of formalisms, including the evaluation side of things, particularly in the evaluation side of things. So as of today, most of these approaches, when they are unsupervised, the way to verify the concepts is just go ahead and do a lot of filtering with some sort of expert in hand. I do not think that is a crazy thing. This may be just my opinion, but I see concepts as a very domain-specific thing most of the times. And they should be tied with experts that expect to use system. So I do not think it's crazy to have an expert having a lot of verification. Now, whether this scales, obviously it does not scale. So there's a lot of questions how you can maybe. There's quite a few works more recently that try to do very large set of concepts, and they try to do selective of them. So you can only show a few of them to experts. And so through these approaches, you can make it a bit more process it like something you can process more easily in the cognitive side of things from an expert is actually interacting with the system. But to answer the question, the evaluation is still very much qualitative today in terms of the quality of the concepts. You can look at the information value, and that's just you can do this quantitatively by looking at how can you pick something based on the scores that you get out of it. But that doesn't really tell you much, right? You can get really high accuracy scores with very nonsense concepts. So the qualitative side of things is quite crucial still today.
Okay, I'm going to paraphrase one question. The nature of concepts is also profoundly hierarchical. What about that?
Right. So we didn't have time to go to discuss this, but the actual formalization that we have in institution theory and category theory of concepts is enables formalization of how concepts can then be composed together in a hierarchy of concepts that are just a composition of simple concepts. And this is basically done by defining a lattice of concepts, where you have some basic concepts, and then you have you can recursively combine elementary concepts to build more complex one. But the semantics of concepts, of elementary concepts, is similar to the one that we discussed today. So an elementary concept has this property of relation between a set of instances and a set of sentences. And more complex concepts, hierarchical concepts, can actually generalize this idea, but the semantics is always the same.
Okay, great. We do have a few more questions, but we're at time. But we'll send you these questions. One of them is about the context dependence of concepts. But anyway, good question. But we'll. So one possibility is, if you guys have time, you can jump on Discord, and we sent you that link, so you can. So all the speakers now have the Discord, so they can see if there are any questions that didn't get answered. Okay, appreciate it, guys. Great job.
Thank you so much.
Thank you so much. Bye.
Okay, next, do we have next speaker? Parisa.
Yes, I'm here. Hi, Gary. Hi, Alex.
All right. Hey, Parisa. Okay, so Parisa, it's great to have her here. She's a professor at Michigan State, and she's been building some very ambitious, super interesting systems. She will tell you maybe about at least one of them, but she's going to cover this. We have two talks on this compositionality thing I mentioned in my overview, which is incredibly important. It may not seem obvious, but it's directly you'll see. Well, it got mentioned just now in the context of interpretability, but also really leading to this issue of cost and efficiency of data, and ultimately compute. So, but many other things. So many other core benefits that we want come from this core idea of compositionality. So with that, take it away, Parisa.
Okay, let me see if I can share the screen. How this works. Let me do entire screen because I don't know. Yes. Okay, so you see my entire screen, I think.
Yes.
And do you see now my slides?
Yes. Perfect.
Perfect. Okay. So hello, everyone. I'm going to give a tutorial. Actually, as Alex asked me to cover like kind of basics of compositional learning, so I try to do some presentation based on a survey that we did on compositional learning of AI models, theoretical and experimental practices. But I'm also giving a few downstream tasks and a little bit about the frameworks of solving problems in vision and language. So let me start with this example that I'm using to show the challenge of vision and language understanding and relate it to compositional learning abilities. So here is a kind of, let's say, classical problem of nowadays, a classical problem of vision and question, visual question answering. And the problem is as follows. There is a natural language sentence, like the red bike is to the right, is the red bike to the right or to the left of the Asian people? And there is an image that the models need to answer these questions given this image. So this example is taken from a data set that is called GQA, and this was introduced in 2019. So we gave this question to the state-of-the-art models at the time, and then we see, okay, the model is kind of excellently answers this question correct. The question looks actually difficult. The model needs to recognize the red bike, the property of the bike, that is the red, and also the relationship between bike and Asian people, and then answer this question. So this is great and interesting. But then we ask similar question, like, is the red bike to the left of the Asian people? So the same question, just paraphrased. And now the ground truth should be no, and the model answers wrongly as yes. So this is a bit disappointing at the time. So this actually makes us to think, does the model understand objects, properties, combination of the relations, and the composition of these all concepts? You might say this is an old kind of example, and the model is kind of 6 years ago. Nowadays, we have very large models. We increase the data. Even all types of questions are input to the model, and we have larger models that can answer these questions. So that is correct. Okay, we have better models right now. But now I'll show you a model that is like kind of 4 years later, and this is 2023. Also a sentence like a woman with an apple in her left hand is standing to the right of a car. Again, we have objects, properties, and the relationships here. So again, this is DALI, and this is 12 billion parameters, very large model, a huge amount of data observed. And we see actually it's interesting that the objects are recognized well, the woman is there, apple is there, car is there. But if you look at the relationships, actually the left relationship, like in the left hand, the apple is in the right hand of the woman in all the top generated images. And the relationship between the spatial relationship between the woman and car is actually kind of random. So now this is again, okay, a couple of years back. So you might say this is still old. But the point that I'm trying to make with showing this example is that, so can we really feed all possible problems and all possible solutions to the large models nowadays? Should we create examples of all possible combinations of the concepts in the world and say, okay, now the models learned everything so they can answer every question? But isn't the world dynamic? Is it possible even to create all possible combinations and be futuristic? Human can learn compositionally and generalize. Every day we have new problems emerging, and we need to be able to solve new problems based on our basic skills and composing those basic skills. That is basically to show you the problem and challenge of compositional understanding in vision and language. The models lack generalizability. Compositional learning is one aspect of generalizability. That is, we see obviously they're lacking this. And then, of course, there are other issues that are not the focus of my presentation here, like lack of interpretability. And when the need of the huge amounts of data, the data always can make the models improve and give us better accuracies. But do they really capture these compositional structures? That is the question. So now I'm going to, with this introduction of showing the challenge for vision and language understanding, let me go back to the basics of what is compositional learning. So compositional learning is actually a crucial aspect of human cognition. We use it in everyday life to be able to solve problems. Taking this sentence from Barbara Parti, 1984, the meaning of a whole is a function of the meaning of the parts and the way they are synthetically combined. So that is the definition of the compositional learning provided. And again, I'm showing some examples of the current models trying to do this compositional understanding. This is DALI 2 again, and then it tries to combine create a red circle on top of a blue square and a yellow cone to the left of the red circle with a small pink triangle on top of it, and miserably failing to do that. Or another example of compositionality, like here, it's an arithmetic expression, like 3 by 3 by 4 by 5, +2 by 2 and so on. So the model needs to actually do these basic operations and compose them to be able to solve the whole problem. We see that in some cases, actually, the model also is kind of like simply failing to do these arithmetic operations, but in some places it does it well. So it's really uncertain, like what the model is doing and how it gets things right or wrong here. Okay, so actually defining a unified formal definition of what is compositional learning, I think it's after looking at the literature, to me it seems challenging to define a unified framework and define it formally. But actually, the studies of linguistic, cognitive, and cognitive linguistic studies try to look at multiple facets of compositionality. And that is why I'm using this cited papers here to tell you about what is like assumed as kind of aspects of compositionality in the literature, mostly literature about language, actually, linguistic and cognitive linguistic. So the aspects of compositionality are divided to this like systematicity or novel compositions, productivity or lens generalization, substitutivity or synonymity, localism, and overgeneralization. And I'm going to explain this. So basically, we look at the aspects of generalizability from the cognitive perspective, and then so I will explain like how people try to evaluate models from these perspectives then. So systematicity here is how the models generalize to novel compositions and unseen combined concepts. Like here, this is an example you see in the right side of the slide. We have assumed the model has seen green circles, blue circles, triangles, white. So it has been observing different kind of colors, different kind of shapes, but the model never observed blue square. So this is basically a new composition for the model. And if a model is able to do generalize and combine concept, it should be able to recognize a blue square, though it hasn't seen a blue square at the test time. That is a kind of systematicity or ability to do to understand novel compositions. This is one facet. Second is like productivity or lens generalization. So the models actually have seen like sequences of 2 words, 3 words, and so on. And then now at the test phase, we're expecting the model to generalize over arbitrary number of the words. So this could be like sentences in natural language with a longer length, or even if we have a like nesting structures, like more like we shouldn't be limited to the depths of the nesting structures. That is basically generalization to longer or larger structures or longer sequences in the case of sequential structure. So this is called lens generalization or productivity. Then we have substitutivity or synonymity. The models are able to do compositionally generalize if they are able to recognize similar concepts. For example, the model needs to recognize if the model like knows about the red circle. If you replace circle with ring, then the model also should relate these concepts, or purple circle or lavender circle. If the model knows the concept of purple, it should be able to recognize and substitute this with other synonyms of this word in the context. So this is also one defined as one aspect of compositional generalization. Another aspect is localism. So here is basically the model needs to recognize whether the meaning is a composition of the parts or actually changes based on the whole context. So this is actually something that humans might really recognize. It's not that, okay, we talk about ability for composing concepts, but sometimes depending on the type of the concept that you put together, actually the meaning of the whole is totally different from the meaning, adding the meaning of the parts. So this is called actually localism. Here I have an example on this slide. Let's say we have 2 facts like X and Y, and we know that this X is true. The fact, like for example, the weather in Montreal is sunny today. This is true. Another fact and I don't know, the weather is cold, then another fact that is true. Now we have this new sentence that says Peter thinks X or Peter thinks Y. So based on the truth of the fact in the previous two sentences, we cannot really infer if Peter thinks X and Peter thinks Y, also they are true, though we know that X and Y are true. So basically, if we bring these sentences in the context of Peter thinks, then the truth values totally change. This is a kind of an example of localism. Also, I take this example from the work of Hopkins and all. So this is the notion of localisms, and we expect the models to recognize the level of locality or globality for composing the concepts and getting the meaning of the whole. There is another interesting aspect of compositionality that is overgeneralization. So for example, the models from the data can capture patterns if you see a lot of data. But then there are a lot of exceptions depending on the context. And the models need to recognize that and not overgeneralize to the patterns that they have observed over and over in the data. For example, if the model can recognize a cat, okay, or recognize a dog, the model can recognize it's raining outside, but then the model, if we want to generate it's raining cats and dogs, obviously this is not the picture that we expect. So this is basically a case of overgeneralization. Or we have in linguistics, we have a lot of exceptions, like you add ed to the past tense of the verbs, but for some verbs you have exceptions. So this is basically the models, if they overgeneralize, then they cannot handle those exceptions. So to just go back to the main picture, these are actually the kind of common aspects of compositional generalization that are introduced in the literature. And then based on this, for evaluation of the models to see if they are actually have these generalization abilities, there are a lot of data sets generated, like including language, vision, so a combination of language and vision to be able to evaluate these aspects of compositional generalization. However, the current benchmarks do not cover all aspects necessarily, or some aspects actually maybe are like reformalized or rebranded. For example, to my understanding, I think overgeneralization could be something like hallucination as well, because you combine concepts in a way that they shouldn't be, or they don't make sense, or it's kind of it could be seen as kind of the problem that we talk about it nowadays, overgeneralization. But some of these more older like data sets, like a few years earlier, they actually cover different aspects, mostly focusing on systematicity and productivity. So you can see the details in our survey paper here. For example, we have PCFG, Clutter, Scoop, CFQ, Scan is textual data set, COGS is GScan is a vision and language data set, Rescan vision and language is CREP, Calvary is vision and language, MIT stats is composition of objects and attributes. So here in this table, actually, we provide a summary of what kind of aspects of generalizability they cover. If, for example, here, you should read this like PCFG covers the systematicity, productivity, substitutivity, localism, and overgeneralization. And you can see all these properties for other existing benchmarks as much as we could cover. Of course, this is not exhaustive, and there are things that might be missing here. We also look at like if they are multimodal or only textual. I try to highlight two of these data sets. One of them that is focusing on text, and it's kind of, it's CFQ, compositional free-based questions. This is a work of Daniel Keisers and all. They try to do a benchmark that is realistic compared to the previous one, and this is 2020 ICLR. So this is basically the task is to translate natural language sentences to like queries in SparkQL language. That is basically for querying knowledge bases like free-based questions, the knowledge graphs like free-base. And here are examples of this kind of parsing. For example, you have the sentence like the girl saw the hedgehog, and then the girl is like there is an X, that girl X, and so on. So we map the natural language sentences semantically, parsing their semantics and formalize them with this SparkQL language. And here in this data set, they try to cover different aspects of compositionality of the models in terms of productivity and systematicity. So if there are combination of the like expressions or combination of the concepts that are not observed in the training, or if we have like longer sentences that needs to be mapped to this SparkQL formalism, then can the models do the long sentences when they are trained on smaller sentences? So these are basically the aspect of generalization that this data set has provided, basically test splits to test these aspects of compositionality. To just give an example of the vision and language data set, CREP is another data set. This is CVPR 2023. And basically, it says, can vision language foundation models reason compositionally? And then they try to give like these kind of images with multi-choice answer captions. And here the model, for example, in the systematicity, again, the model hasn't seen CREP on a skillet. Maybe it has seen boats on something or skillet, including like eggs, but not crepe. But the test time, the model needs to recognize this novel composition of the crepe on skillet. So that is basically one split that they provide. Also, they have productivity and again, lens generalization. If we have like longer captions, like brown crepe next to leafy salad and in front of the metal fork, can we have recognize this caption is aligned with this image? And they try to create really hard, different types of hard negatives to make this task difficult and evaluate the compositional reasoning of the models, vision and language models. So this is just to just wanted to mention explain the nature of these data sets and benchmarks, but there are so many of these, as you saw, again, part of them in the table that I showed you. So there are also some parts of the studies in the literature that try to talk about starting from the models and see if various models are able to do compositional reasoning. And these studies, again, there are two types, some of them empirical, focusing on the data set that I mentioned. They try to apply models to those benchmarks and evaluate and see how they perform. And there are also theoretical analyses using mathematical formalisms and try to make assumptions and try to prove if there are some compositional generalization ability in the models. So again, in the survey that we were studying, we look at the literature and saw, okay, there are some basic neural networks like RNN, CNN, LSTM, that people evaluated both theoretically, sometimes empirically, and sometimes both theoretically and empirically. There is also transformer-based models that people try to, again, evaluate. Can they generalize compositionally? Again, both from the theory and practice. And then there are also customized models, architectures proposed like neural modular networks or neuro-symbolic architectures, and people try to address the aspects of compositionality. From the modeling perspective, I'm also briefly trying to give you an overview of what kind of studies have been done in the past and also some of the recent works. One thing that I should mention before going to that, actually here the list that I have is mostly focusing on neural architectures. What about classical symbolic AI models like logic, grammars? So I should mention that actually logic and like, for example, first order logic, these are inherently compositional structures. In logic, you represent objects explicitly. You represent their composition with logical operators. And you don't have any limitations of representing any nesting architecture or nesting reasoning. So the logical formalisms or classical, in general, symbolic AI formalisms like grammars, they are able to actually express the compositional structures inherently. So no issues in that. However, why we are not using them now for compositional learning. You know, all these like classical problems of like symbolic processing in terms of like not robustness to the noise, basically handling uncertainty, all those classical issues that if we are going to go to use symbolic AI, pure symbolic AI, we have the compositionality naturally, but then we don't, we have the issues with the perception and dealing with the noisy data and variety of concepts in the real world. But now, actually, I will get back to this. That's why I don't talk about like the studies of the expressivity of the classical symbolic AI for compositionality, because that is an obvious thing for those models. But I just overview the studies that have been done for the neural modeling, because everything is implicit there. So it's hard to see if they can really generalize and can do compositional learning. So here is like some studies are done with Hopkins again et al. They try to look at models like LSTM, CNN, even transformer architectures, and try to evaluate them on various benchmarks to see if they can generalize. So they not only like just basic architectures, but also some modified architectures. Like here, for example, this is an architecture that is based on LSTM, and then it's like kind of by LSTM in 2 directions with some modifications. And they try to do attention also, and then evaluate this model to see if they do compositional generalization. There are also architectures like sequence-to-sequence convolutional neural networks on the right side of the slide, that they use CNNs for doing sequence-to-sequence modeling with some, again, some architecture built on top of these convolutional layers and trying to evaluate. There is also evaluation on the transformer-based architecture in the same work. This is Hopkins and 2020. And then the key message actually of this is that compositional reasoning is challenging. These models, like for example, transformer-based in this architecture in this study, was doing much better than CNN and LSTMs. CNNs, actually, the sequence-to-sequence CNN based on this study was even better than LSTM in terms of compositional generalization, in terms of the results and data set that they provided. But at the end, actually, they say, okay, the models perform to some extent have this generalizability, but we need more sophisticated architectures to be able to address this problem in a more reliable way. And also I point to other studies that they try to actually evaluate these neural models for this compositional generalizability. Specifically about transformer-based architectures, there are also very interesting results empirically. So empirically, people try to test on these different benchmarks, again, that are designed for compositional generalization. Some of the findings related to transformer-based architecture is that they rely on memorization of some subgraph patterns. They do actually shallow reasoning, and they look at, they linearize the surface of this compositional structure, and they remember it. That is some like results that you can see actually in like here, Yingshan Chang, and they look at the counting problem, and they say, okay, the model actually have a hard time to generalize over counting. There is other studies that also like making transformers solve compositional tasks. They try to look at different architectural components of the neural models. Like, for example, can positional encoding help us to generalize better? Can the size of the model or the encoder-decoder architectures change? Can help us, like parameter sharing and many different this kind of small architectural tweaks, I would call them. Can those help us to do compositional generalization? So the results show that all of these actually impact the performance. These are all empirical findings. The performance of the models and compositional generalization, like positional encoding, certainly influences that. But then again, these problems are not totally solved. And one interesting result that actually shows that there is always a gap between in-domain and out of domain, there is a gap between low complexity and high complexity tasks. So the gap between these two always shows that, okay, if there is compositional generalization, there shouldn't be a gap because they should be able to generalize, and there shouldn't be a difference between like tasks that have like lower complexity and like more complexity. All these results, though, they show that, okay, all architectural patterns impact the result, but they also indicate that what happens is mostly memorization and shallow reasoning, not really like essential or in principle compositional reasoning. So these transformer-based architectures are the basis of the large language models nowadays, like from the encoder-based models to like decoder-based models. And now going back to the large language models, they always also, the studies show that they inherent these limitations from transformers, and they have this lack of compositional generalization. There are studies that actually maybe not specifically focusing on the compositional generalization, but in general talking about reasoning abilities or generalization abilities of the large models. But again, thinking about compositional generalization is one aspect of this generalization in general. I think we can speak to, okay, this lack of compositional generalization also is inherent in these models. There are some interesting studies. Again, I have listed some of the references. I briefly overview. You can look at the survey paper for a little bit more information about these findings, but also the original papers, of course. Some of the interesting findings here is that, okay, the in context information or the long context can help or improve the compositional reasoning ability of the models. However, in this work, I think this was Neuro-IPS, like best paper 2023, they show that actually this emerging abilities with the large data doesn't mean that the models suddenly are intelligent and can really solve complex problems suddenly, but it's an artifact of the actually evaluation metrics, and the fact that the evaluation metrics are non-linear and they are non-continuous compared to the like loss functions that the models are trained on. So this is actually one interesting finding there. However, some other studies, like especially recent studies, show that chain of thought actually increases the expressivity and computational power of the model in the decoder-only transformers. So basically, when you generate the outputs, the longer outputs allow to the model to do more complex computations. And if the model even is linear based on the chain of thought, the model can really address more complex and nonlinear problems. So these are actually some interesting findings. They are based on different assumptions. So that's why sometimes they are actually contradictory. For example, this is an issue also of the theoretical analysis of these like language models, because there is no unified mathematical framework that we can evaluate them. For example, there is some studies in 1 and 2. One of them is theoretical limitations of self-attention neural sequence models, and another is like on the Turing completeness of the modern neural architectures. And actually, these studies, one of them, as the first paper says that hard attention transformers, okay, they are hard attention models, so ignore most of the input, and that's why they cannot solve problems requiring full input processing that includes kind of logical formulas, that is a lot of compositionality there, or parity, that there are really complex patterns over the whole sentence, so they cannot address that. While actually the earlier work says that, okay, they are Turing complete because they make an assumption that the hard attention has full access to the input information and then provides Turing completeness evidences. So again, it's really all the theoretical analysis sometimes are based on different assumptions, different mathematical frameworks, and that's why sometimes the findings are a bit hard to connect. But also there is another study that shows that, okay, transformers actually basically if the length of the input increases, or there are unseen lengths of inputs, transformers cannot really like generalize, and they have the limits of productivity aspect of compositionality. So they can really deal with the lenses that they have observed during the training data. Actually, this is, I add some information in parentheses, that this was interesting that in our research, we also realized even for like vision and language navigation models, that you instruct the model. If the model has been instructed with sentences of like 5 steps of navigation, then the model cannot generalize over 10 steps, or even two steps sometimes. Even the smaller steps are problematic for the models. And this is actually seems to be a kind of more fundamental limitation of these architectures that might not be able, we are not able to solve it with data. Again, to go back to the overall picture of the survey that we are providing here, in this survey, we cover compositional learning facets, as I explained them to you. And then we also overview some data sets that are trying to help like empirical evaluation of these aspects of compositional generalization. We have the studies on compositional ability of the learning models, looking at basic neural models like RNN, CNN, transformers, and until to large language models. We have also empirical evaluation of neuro-symbolic models for compositional generalization. The findings of these empirical findings is that, okay, there is lack of evaluation for the covering all aspects of compositional learning, the benchmarks not always covering all aspects. Even the theoretical analysis are not necessarily connected to these aspects of this that come from the cognitive basis or linguistic basis. The theoretical studies do not really connect to these different aspects. Because the mathematical frameworks are rough, more talking about expressivity stuff, not really aspects of compositional generalization. Then empirical studies have really challenges and problems. As I mentioned, the first is the lack of coverage of the different aspects. And the second is like the data contamination is really a problem. So that's why for compositional generalization, most of the cases like systematicity, we want to evaluate the model for unobserved cases. And with the current models, it's really hard to recognize if this case, this scenario is observed or not. So data contamination is a problem. And also most of the benchmarks that we're having mostly are toys. This is also debatable, is really, should we go with toy settings that is controlled and is like lab setting that we are really sure what the model is trained on and what is tested on. In other, but other challenge is that sometimes you do the lab setting and you cannot express the challenges of the realistic environment. And then we need to have really realistic environments that come from outside world. And then again, we go back to the problem of data contamination and all. So these are basically the challenge of empirical evaluation of the compositional learning facets. Theoretical evaluation has a problem because we don't have a uniform methodology, and also the current studies don't make a clear connection to compositional learning facets, and also lack of connection to the compositionality in practice, because in practice we see a lot of like emerging behavior happens. And then theoretically, we might show the limitations, but then the explanation of the gap and so on is not always clear. So this is the big picture. Again, you can look at the details of each part in our survey paper. So now I'm trying to go back to the theme of the like summer school, promise of neuro-symbolic solutions in LLM area. So era. So actually, I talked about like classical models, symbolic AI inherently address the compositionality. We have the LLMs that are really like huge with perception capabilities, observing a lot of data, remembering a lot of patterns, which make a lot of problems solvable that they were not solvable before. Now, for addressing this compositional learning in a principal way, can we combine the two worlds? Now I'm sorry, I'm going to some of the works that we did briefly in a like 5 minutes that I have, 5 or 10 minutes that I have. So here I am trying to explain you like how we can combine the two worlds, and I think actually the now we are in a good era of large language models that enable us to go back and make better use of symbolic AI for addressing these kind of fundamental problems. And here I'm going to explain one specific framework that is trying to do this compositional generalization in the like vision and language grounding setting. So let me explain the problem setup and then go back to the advantage of this combination of neural and symbolic. So basically, the problem setup is, again, this can be visual question answering, for example, that you have a complex questions with objects, attributes, and relationships. We can also have grounding, like point to the blue square that is in the same column as the yellow square. So your model needs to point to a specific place that you really have a complex and compositional explanation of it. So this is the kind of problem setting. Now, the advantage of language models. The first actually advantage of language models nowadays is that they can help us to go from this natural language sentences to formal representations with an accuracy that was not imaginable in the past before this generation of technology. So that is really great because now we don't one of the issues of the classical logic and symbolic processing is that we need to have a set of predefined predicates. And we need to cover all aspects of like real world with those predicates, which was impossible to scale up for solving realistic problems. But now we can actually go with this, what I call linguistically motivated predicates. So I'm going to say, when I say point to the blue square, I don't care. I just create the predicates based on the words that happen in natural language, like point blue X and a square X. I make every word a predicate. And then I get this formal representation with the operations, and I express this compositional structure with operations like and, or, and all this logic in this case. So I can have the compositional structure. My predicates are lexically motivated, so I'm not limited to that. This framework actually is based on the work of Josh Tannenbaum and his group called What's Left, and they have a lot of relevant works related to this same framework, but I just cited this one. So you use the language model to map from language to formal representation. Now you have the perception module. You have, again, vision models, strong vision models that can give you, they can detect objects and give you not only object labels, but also probabilities or the scores of like what is the probability or soft scores of like what is possible object in this space. Is that this is 20% like blue, 80% green, and so on. So we get kind of probability distribution of the specific predicates for each of the elements of this visual modality. Now we actually have a basically kind of probabilistic program because we have the predicates. This predicate is linguistically motivated. We have X. X is a piece of this image. It could be a bounding box here. And then I have a vision model that gives me the probability of like basically this predicate blue and probabilities of this X with this visual representation being blue. So I get the distribution for X being blue. And I get the distribution for X being a square. And then I have this AND operation, and I can do explicit composition. So now I don't have, as far as I am good in the perception and probabilities for each predicate, I can do the composition explicitly. So that's basically the compositional generalization will be solved inherently as far as we are good at these predicates and as far as we are good at the translation to this formal expression. So basically, this is a powerful framework potentially And it shows that actually it does very good in some toy environments. It does very well because in those environments, the language model can give us perfect kind of formal representation. However, there are some challenges. As I said, in the realistic setting, like mapping from this language to formal representation still is a challenge for language models because it also relates to compositional generalization and understanding. I showed you the problem of CFQ. It's the same problem, basically. You go from natural language to SQL queries. Here, I go from the natural language to kind of formal logical representation for a different purpose, but still the language model itself needs some generalization to be able to do it. But here, actually, based on the huge amount of data, these translations become more accurate, and we can do this translation here, and we can exploit the classical NLP tools for semantic parsing and all those structural representations to help the language model capture this formal representation more accurately. So this is actually the addition that we did on top of the Josh Tannenbaum work, that we tried to actually exploit the semantic parsing and put it in the context of the sentence to get better formal or more accurate formal representation of the initial query. That is one challenge here. Another is, like, as I mentioned, the lexically motivated predicates now become huge because now we are not limited to predefined set of predicates. We can go for any predicate that is for every domain that you go, you can get new predicates. And now, again, another classical challenge of symbolic processing is that the connection between the symbols, if you don't write it in logic, it's lost. So we are in a discrete space, and I don't know blue is similar to turquoise, or I don't know circle is related to a ring or anything that has similar meaning. So that connection is lost. And here is another challenge that we can solve here. We in this work that we propose this Nesikoko. And there in Nesikoko, we try to actually not have a model per predicate. So I'm not going to look at this blue as a kind of neural model that is going to recognize blue given this object representation. But I'm going to use a vision and language model that gets a representation, let's say word representation of the blue. I have a language encoder that gives me the representation of the blue and the visual encoder that gives me the object representation. And then I can get a decision or the softmax or the distribution of blue, this visual object with this combining vision and language. Now, if this blue representation is embedding a space is close to the turquoise representation, if I learn blue, certainly I can also connect this to turquoise and recognize this object actually is turquoise, or it is light blue, or it is dark blue. So they are very similar. So if I learn one predicate that has a similar representation as the others, it helps me to really scale up and not being limited to individually learn and seeing a lot of examples for each single predicate. So this is actually a very simple idea, but it's very powerful and helps us to alleviate the issue of like this lost similarity between analogy between different symbols. And then another thing is like, okay, if we want to basically, we have the program, we get these probabilities and softmaxes, and now we want to execute this program to get the solution. And we want to put it in the whole framework of neural learning because we want to learn these predicates at the end by getting the answer to the question and back propagating the error. So here is another aspect that we need to see. I mean, it's a kind of challenging aspects of neuro-symbolic training, how we are dealing with non-differentiable like operations like and, or, for, all exist, and how we can translate them to some soft surrogates that they can be end-to-end differentiable. And this is, again, like there is a lot of studies on this, like using the soft logic, like or Lukasiewicz operations, dot products, T-norms, T-conorms. Those are kind of different types of T-norms and T-conorms can be used as a soft surrogates replacement of this logical operations. Here I just have a table of possibilities, but this can go even more. But then with those replacements, then we can train the models end to end. And now we see that actually the models that are, they are having much better compositional generalization on like challenging compositional splits. So this is Kelver-Cogent. Kelver is a kind of well-known data set, and it's kind of simple, it's kind of synthetic, the queries are synthetic, but Kelver-Cogent is kind of a version that is created for evaluation of compositional generalization. And actually the split B is the one that has a novel composition, which is hard. And we see now with this Nesi-Coco framework that we deal with this basically explicit composition and neural learning. We see that we can actually do much better in the split B, which is compositionally challenging. For the split A that doesn't have the compositional novel compositions, all the models actually, vision models also can do very good. But then we have also another data set that is ReScan that has also very complex novel compositions. ReScan is actually one of the, it was listed in my table of data set, and actually is very, it has very challenging splits for compositional generalization. And here we see even much more improvement when we use these frameworks like Nesi-Coco and left compared to the classical or like more like neural vision models. We see that we can even improve like 5% accuracy, which is a lot in the higher on these tasks. So I'm going to skip because of the lack of the time. So we have also recent work that we show that, okay, instead of using the vision models and training them, we can also decompose questions and exploit the large vision and language models and do the composition explicitly at the inference time by just getting the basics from the language models and composing them explicitly at the inference time. But actually, there is not time to talk about this, but this is actually not easy due to the inherent problems of these language models. They are biased towards the training data, and sometimes answering the complex questions actually is harder for them than answering some basic questions. These are some surprising results that actually we see that with this new data set that is gaming environment, this is an example of the new data set that I think it's kind of less prone to the contamination of the training of the current large models because it's a gaming environment, but still realistic. And we see, like, for example, InterVL that does 75% in referring expression MS-Coco, it does 7% on RefGTA, which is very surprising. So these are actually some current results not published yet, but still is very interesting to see how the models are biased and find shortcuts based on the context to answer questions or ground the information, ground vision to the language compared to like really having compositional generalization. Just the last moment, if I have time, Alex.
Super quick.
Okay. 1 minute, and then I just do the conclusion. I just wanted to say, okay, Neuro-Symbolic is really promising. That is what I wanted to show you with the application that I showed, especially given the emergence of these large language models. But now another issue that I want to raise here is that Neuro-Symbolic modeling is challenging, is more challenging than like working with large language models or designing neural architectures because of the current libraries that are so advanced for the neural modeling. And that's why I wanted to point to briefly to the framework that we develop in my group. It's called Dominoes. And we try to connect some symbolic language to PyTorch library and try to facilitate this logical representation and abstract away the logical representation and problem declaration from the neural model that is running underlying the system and the algorithm that actually tries to combine neural and symbolic aspects. Due to the lack of time, I'm going to skip this, but we just have like different algorithms are covered for combining neural and symbolic and getting differentiable executions. And we have a declarative language that we can define concepts and relationships. Just if you are interested, I have included a link and we have a demo also about this. Just to summarize my tutorial today, I try to cover basic concepts and definition of compositional learning. And I overviewed some of the benchmarks for evaluation of compositional reasoning. Sorry for the typo here. And I overviewed well-known architectures and their compositional expressivity. And then I pointed to some downstream tasks and generic frameworks for compositional reasoning. I think this slide has some typos, sorry for that, I did it quick. And the future directions is like, okay, LLM's evaluation for compositional reasoning is challenging due to data contamination, memorization, and theoretical analysis also is hard, a variety of mathematical formalisms with different assumptions. And then we need more benchmarks. The diverse theoretical methodology makes the evaluation hard. Lack of integration with cognitive science, and especially with theoretical analysis and cognitive aspects of compositional generalization, is something that is missing. And we also need, of course, new expressive architectures that inherently, hopefully, are able to address the compositionality. Thank you very much, and thanks to my students helped me to do this study and do the survey. And then please, I would be happy to answer questions if there's time.
Okay, great. Thank you so much, Parisa. Very chock full of good stuff. Covered a lot of great ground.
Thank you.
So we only have now just a minute for questions for the next talk. But you brought up, I'm going to paraphrase a question, is that we have these terms, compositionality, that maybe we could imagine mathematically, but what about the cognitive kind of interpretation? What do we know there?
So yeah, that is I think these aspects of compositionality are kind of inspired by the cognitive linguistic studies, like lens generalization, nesting structures, and part-whole definitions, and so on. But I think the issue is like, and then I think the benchmarks try to, again, the vision and language benchmarks, especially the language benchmarks, try to resemble those abilities in the benchmarks. But I think the connection between the benchmarks and these cognitive studies is much stronger than theoretical studies and these kind of cognitive aspects. So the more mathematical formalisms of generalizability and expressivity are less connected to these cognitive aspects. I think this is a really a challenge here. I'm not the expert in that area, but I hope that there are studies to address those challenges from the theoretical perspective.
We'll squeeze in one more question, which is, are there ways of measuring which are not benchmark based on the data set?
So I think this is theoretical studies, like basically looking at the expressivity, modeling these architectures based on mathematical frameworks, like, okay, this is a linear model, or this is a non-linear model, or the modeling their input and output and expressivity from different mathematical perspectives. Sometimes they are mapped to, let's say, algebraic structures. Sometimes they are mapped to some other kind of functional kind of representations. So as I saw in our survey, as I mentioned also during my talk, there are different formalisms used, and they make a lot of different assumptions depending on the formalism that they use for evaluation of the computational complexity and the assumptions that they make. That's why I think there is a way to do it, but it's not a standard, and it's not really helpful in terms of connecting those different studies to each other. That is a problem that I see there. So yeah, I think this is actually the gap that hopefully there are more research in this direction, like what will be the best way of evaluating these systems, and making clear assumptions and possible assumptions, and making these connections between the theoretical studies is something that is missing. And I think for me, myself also, will be helpful if there are more works in this direction to understand this.
Okay, great. And that's a great segue to our next talk. So thanks again, Parisa. There are more questions, but we'll send them to you, or jump into the Discord if you have time.
Okay, sure. Thank you so much.
That. All right. Thanks again, Parisa.
Thank you for having me. Bye-bye.
Okay, next up, do we have Pari? There he is. Okay, great. Welcome, Pari. So now this is was deliberately adjacent to Parisa's talk, because Pari's going to talk about mathematical definitions of compositionality and how it relates to generalization. So I'm a little biased, but I think this is great work. So, all right, take it away, Pari.
Okay, thank you, Alex. Okay, so Parisa gave a great introduction for compositionality and what it means to generalize compositionally. In this, the work that I will be presenting, we take the theoretical view. We try to understand what it means to be compositional. So it's a little theoretical, but we do take the next step of using the theoretical insights to understand how it can help us. And this is joint work with Tim Klinger, Ken Clarkson, and Sashank Kubaru from IBM Research, and Alex Gray at Centaur Institute. And this work is based, this presentation is based on a couple of papers that we have out. You can find them at the QR code on the bottom. So to kind of motivate what it means to be compositional, I always like to think about this problem. This problem was presented in this 2018 workshop paper. It's called List Operations, or List Ops for short, where essentially we are given a sequence of tokens. So you have opening and closing brackets, you have some numbers, and as human beings, we understand what these numbers mean. There are some operators in like min, which implies minimum, sm, which implies sum, mod 10, max, median. So these are concepts that we understand. So then when we are given, as humans, when we are given this problem to solve, we can solve in many different ways. But for example, one algorithm we could use is to just find the smallest enclosing brackets and then resolve them and keep doing that recursively. So we keep doing that recursively, and eventually we get back to get the final answer, what the solution of this sequence is. And the answer is always between 0 and 9. So for any sequence of such opening and closing brackets and digits and operators, the answer will be between 0 and 9. So as a modeling problem, you can also think about it as a sequence classification problem. I'm given a sequence of tokens, and I want to predict a label between 0 and 9. But as human beings, we know what these symbols mean, so we deal with them in specific ways. And the way we resolve this sequence kind of highlights what it means to be compositional. As Parisa mentioned in her tutorial, a compositionality is often described as the meaning of the whole is a function of the meaning of the parts and of the way that they are syntactically combined. So that's what compositionality is kind of thought of. And this definition comes from linguists. I think Barbara Partry is attributed. This definition is often attributed to her. But you can actually somewhat write this definition in math. So one way to write this is given by this formula, and I will kind of walk through what it means. But effectively, we have a meaning function mu. So we want to understand the meaning of some sequence, and the sequence has subterms. These u, I to un. So the sequence is made up of subterms, and then they're combined using some rule, possibly an unknown rule. So, but the subterms are combined, and then we want to understand the meaning of these subterms combined with the rule. And the way it's defined is that the meaning of the subterms depends on a rule-dependent function of the meaning of the subterms. So the meaning of the full sequence depends on the meaning of the subterms, and then they have to be combined in a specific way. And this is a very general definition, but one important aspect here is that this definition is recursive, right? So the meaning function appears both on the left and the right-hand side. So to understand the meaning of the whole, we have to recursively understand the meaning of the subparts. Just as we kind of walk through in this example, where to kind of resolve the whole sequence, we have to resolve individual subparts of it, and then combine them in a problem-dependent manner to get to the final answer. And you can think of the rule here as the operators, like whether it's a max or a min or a sum mod or a median. But the way we combine the meanings of the parts also depends on kind of a rule-dependent function. So this is one way to it's a high-level way of thinking about what's a compositional function. And then if you want to kind of understand more definitions of compositionality, there's a paper about 15 years ago, and they have two papers, Pagan and Westerstahl. They talk about compositionality and then all kind of related definitions and variants of that. But why is this interesting, right? So why is it compositional? So as humans, and hopefully as any machine which learns to say understand what these digits mean and what these operators mean, it should be able to immediately solve a different problem where I say switch one of the digits, which I highlight as a 3, to a 1. The moment I change it, it should still be able to solve that problem, right? Like it's kind of falls into that systematic generalization case that Parisa was mentioning of unknown combinations of known parts. So I know what a 1 is. I know what a 3 is. If I swap the 3 with the 1, I should be able to solve the same problem without any issue. My solution path will change a bit, but it should be solvable. Similarly, if I swap certain subparts, right? So if I took the left subpart, the max 322, and the right subpart, min 862, and swap them in the sequence, I know how to solve this, or I should know how to solve these subparts, and if I can then still solve this new problem where these subparts are swapped. I should be able to solve them. So that's kind of, this is also a version of systematic generalization. And this kind of highlights the property of localism, that if you make changes in local parts, your overall answer can change, but you can still solve the local parts and translate the answer accordingly. So that's why I like this list operations problem a lot, because it kind of highlights a lot of these desirable properties that we want in models which are solving compositional problems. Again, another version of compositionality is productivity, where I'm only trained on sequences of length, say 15, but then I'm given the similar sequence using the same digits and operators and brackets, but they just happen to be of length 50. I can still apply this overall implicit algorithm of matching the smallest enclosing brackets and solving them recursively to get my answer. And so this problem also has that property of productivity. But when I'm applying that algorithm to solve this problem, the algorithm to solve each problem of this form is the same, like find the smallest enclosing bracket and resolve it. But each specific solution for a specific input kind of induces this computation graph, right? So in this problem, for example, I kind of take kind of the max 322 subsequence, and then if I think of them as nodes in nodes, then I effectively are using these nodes to create the next level, solve the 3. So I can effectively create like a computation graph of how I solve this problem. I have been processing the subsequences recursively to get to my final answer. And so the algorithm that I'm using to solve this kind of induces implicitly this computation graph, or this kind of a trace, if you want to think about it. Now, in contrast, how would neural network-based models, like sequence processing models, solve this problem? A common technique is where we kind of think of each of these terms as tokens and learn like token embeddings. You can do position encoding and whatnot, but you can think of them as token embeddings. And then you can kind of pass them through some giant model. So for example, in this picture, I'm trying to highlight that the first level does some kind of a convolution of the tokens. So everything is looking at their previous to and post to tokens to get the next level representation. And then you do some kind of a pooling. And then you do some kind of a convolution again and pooling and then to a certain level. And then you eventually arrive at some representation of the sequence, which we can then pass it through some kind of a readout layer. So you can think of it as like a final classification layer, which takes the representation of the sequence and tries to predict the label. And in this case, like creates a probability distribution over the possible labels and takes the kind of the max probability output. So that is the way that neural networks would solve this problem. It's different than how my implicit algorithm that I had in my head was solving the problem, but it is still also kind of creating this computation graph to solve this problem. Instead of using a convolution network, for example, I could do a recurrent network where, in fact, I could do a bidirectional recurrence. I can recur through the whole sequence in the forward direction and then recur through the sequence in the backward direction. And then again, take the final representations, pass them to a classifier, try to make a prediction. This is how some kind of neural network-based model would solve this problem. But what is interesting to me and kind of a connection to the way I was solving the problem is that in both these cases, we have this computation graph, which is implicitly defined by some algorithm. So in the previous case where I was solving it as a human, I had the algorithm of finding the closest, smallest enclosing brackets and solving it. And with neural networks, the algorithm just is convolve, look at your next neighbors, and then create the next token, or recurse through the next token as in a recurrent model. But we are all still kind of computing this computation graph. And to me, this computation graph is kind of, I see that as a connection between these two ways of solving this problem. I'm not saying that the neural network that creates this computation graph is the right way to do it. In fact, it's kind of based on the inductive bias we give to this model. A recurrent model, we can only create a very specific computation graph. And with a convolution model, we can, again, create a very specific computation graph. But given these components, I like to think about how would I define a model, right? I would define a model with these components. I have the token encoder. Basically, it takes tokens and turns them into some kind of representations. I have a span processor. Effectively, it's telling me, okay, I'm going to give you a subsequence, part of the span, like a subspan of the sequence, and I'm going to ask you to combine them and create a new representation. So in a recurrent model, you effectively take your current token and your previous token or previous hidden state token, and then combine them and create a new representation. With something like attention, you look at everything in your history and then combine it to create a new representation. So you can think of those as span processors. Then there is some implicit algorithm or modeling choice we have made, which generates this processing hierarchy. So one can think of this as a computation DAG function. a function which takes an input sequence and tells me how its computation graph should look like. And it's usually going to be a DAG, a directed acyclic graph. So how should that graph look like? Usually we don't like run models like this, but implicitly I can think of them as having a function which looks at a sequence and tells me what the computation graph should be. And what this effectively is giving me the processing hierarchy, and you can think of it as the trace of the underlying sequence processing algorithm. So whatever my sequence processing algorithm was, if it was the problem-specific smallest enclosing bracket matching, or whether it was a recurrent processing, or whether it was a convolutional processing, there is some underlying algorithm I choose when I choose my model, and then this function is effectively giving me the trace of that algorithm when I apply it to the problem, to the specific problem. And the algorithm is probably the same for all inputs, that is implicitly applied, but the trace can be input dependent. And as we will look at some theoretical results, the trace actually should be input dependent. And then I'll tell you, give examples of situations where the trace is input dependent or not input dependent. And then finally, we have the readout function that I was saying. Like it needs to take this final representation that we kind of create recursively, build up through the model to use to make the final prediction, whether it's like what's the meaning of the whole sequence. In some cases, it could be a label, like is it between 0 and 9? It could be a number, or it could be the next token. Like I'm looking at this sequence, what do you think is a reasonable next token? That would be, the readout function can also be a simple classifier that predicts that. So I kind of say like any model, sequence processing model, has these components. I'm not claiming that any model that has these components is compositional, but rather that any sequence processing model has these components, and based on these components, we will talk about compositionality, what it means to be compositional. But first, I'm defining this function as something that kind of applies these the span encoder recursively over the computation DAG. So so essentially you take your sequence, you do a token encoding, then something gives you this computation DAG. In practice, it's often built on the fly, but imagine you were given it beforehand, you can apply your span encoder recursively up the computation DAG to get your final output. So that would be what I'm calling a compositional function. And like in light of the summer school focusing on neuro-symbolic architecture, I like to think of this definition as having kind of a neuro-symbolic structure as well, where one can say that these token encodings that I'm creating, or the way I'm processing tokens in the subspan using the span encoder or the final classifier, as neural components of this model. And the function that is giving me the actual computation graph, that kind of implicitly or explicitly is giving me this computation graph, is what I consider as a symbolic component of this model. Of course, like as discussed in a previous in Alex's introductory talk, neuro-symbolic can mean many different things. In fact, Henry Kautz gave a talk, I think, in 2020 when he classified neuro-symbolic into various forms, and the way we are interpreting any model with this neural components and a symbolic component, where the symbolic component is actually an actual graph. It's a graph. It's a DAG. One can argue that this way of thinking about models falls in these specific categories of neuro-symbolic as per Henry Kautz classification. But I won't get too much into detail. It's just a small comment just to make it relevant to this summer school. But here's a kind of example of how such a model could be executed, right? So imagine I have an input of sequence 5, and I'm given, something gives me this computation graph. So it's just a very simple graph that's shown on the left. And then the way I would process this function is the following, right? Like first, given my input of length 5, I would create token embeddings for each of those inputs. And then I would recursively apply my span encoder G over this computation graph. So I would take the first and second token, create a new representation, third and fourth token, create a new representation, and then I would use that new representation and the fifth token to create yet another one. So I'm like processing through the computation graph recursively, and finally I arrive at a single representation highlighted with the brown node, the sink of the DAG, which I will then pass to my final classifier, H, the readout function, to make my final prediction. So that's the way that we are kind of defining an abstract function. Like we think of this as an abstract function, which processes the input in a compositional way, given this computation graph. You can also like have very complicated functions. Here's an example of a very complicated computation graph. I'm not going to get into the details of how this is evaluated, but you can see like it can express very complicated problems and complicated functions. But going back to the original definition, or the verbal definition of compositionality, that the meaning of the whole is a function of the meaning of the parts and of the way that they're syntactically combined. The way we are thinking of a compositional problem, the way we defined it, kind of hits upon parts of this specific verbal definition. Like the meaning of the whole is the function f, the composition function f that we want to define. It is a function, the readout function of the meaning of the part. So the subspan encoder G, which takes parts of my input and creates a new representation as the function which is computing the meanings of the parts. And then the way that they're syntactically combined is given by this computational DAG function. Again, this is all at a very abstract level, but I'm just saying that if my function had these components, then it would fit the definition of a compositional model, which is good, but it's also kind of problematic because we can show that many existing models fit this definition. And in fact, most off-the-shelf models fit this definition. So the definition is general enough that it's like recurrent models fit this definition, where you think of the computation DAG to look like this. So on the left, I'm showing the unidirectional recurrent neural network, and it would have a computational DAG such as this for an input of length 4. Bidirectional computation graph will have the one showed in the middle, whereas a tree RNN, basically an RNN which first creates a tree for the input, like say using some kind of a parser or learned parser, creates a tree and then processes the input recurrently up the tree, will have a computation DAG of this form. Convolution network, where they're convolving neighboring tokens and then pooling over them and doing that recursively, can also be shown to fit this framework, which like if you think of the convolution and the pooling as a single operation, then you can also like get a similar DAG for this model. Even transformers fit this framework. So imagine you had a self-attention based transformer, which is looking at everything, every token looks at every other token, and you do it in a multi-layered way. Then you end up with a computation graph as the one showed in the left. It has a lot of edges because every node in one layer is connected to everything in the next layer. You can also have sparse attention transformers. There are many different kinds where the number of edges go down. The number of nodes remain the same, but the number of edges go down. But this DAG is highlighting the actual computation that would go into a transformer. And then you have like causal attention transformers on the right, which have a specific structure where the edges only go to the next token in the next level, not to any previous token in the next level. So our definition on one hand is very broad, that it includes a lot of existing models in this framework, but that also means that it's kind of, it can be kind of vacuous, right? Because if that's how I'm defining a composition function and all of these are composition functions, then that's kind of counter to what we've seen, right? Like these models are inherently kind of not compositional. So to kind of understand that fact, what we argue is that compositionality is not an individual binary property. It's not like either you're compositional or you're not. It in fact is something that's on a spectrum. How compositional you are is on a spectrum. Some models can be extremely compositional and some models can be very complicated. So for that, we kind of develop a notion of compositional complexity. Not computational complexity, but compositional complexity. How complex is this composition that your problem, that your function induces on the inputs to solve it? How complex is this composition? And it kind of is, we quantify it with this notion we call the locus of influence, or LOI of a source node in this computation graph. And the neat thing is that this complexity measure, the composition complexity measure based on this locus of influence, takes in the complexity of both the neural part, the span encoder, the neural network model that would take a small part of my sequence, a subspan of my sequence, and convert it to a new representation. That's the neural part, but also of how complex is this computation DAG that is implicitly generated. So it combines the complexity of the both these components. But before I kind of talk about what these complexities of existing models are, I want to highlight what this locus of influence means. So the locus of influence effectively quantifies the sensitivity of the output given changes to the input, specific input tokens, because input tokens kind of correspond to sources in our DAG. So if I change a specific input token, then how much effect can it have on the output? And then in some cases, the effect can be pretty significant. It can change the whole meaning of the input. In some cases, it should have no effect because it was something that was ignored previously anyways. So locus of influence quantifies the sensitivity of the output given changes to the specific inputs. So for example, in these two in this particular computation DAG, it's the same one, the one on the top and the bottom, but we highlight kind of the effect of the first node with the yellow highlight, showing that's the part of the DAG that this particular source node has effect on, whereas the third node affects a little bit more larger part of the computation graph. And we have two notions of this locus of influence. The absolute notion, basically how sensitive a particular source node change is to the output, how sensitive the output is to a change to a source node, and then relative, which kind of evaluates how important is a single source node compared to the other source node. Are there special source nodes which have really high importance, or are all source nodes equally important? And that is important because if every source node is every source node has high sensitivity or high LOI, and all source nodes are very, very complex, then your whole relative LOI is actually as low as it can be, because everything is equally important, because everything is equally hard. In this example, it doesn't look like any specific source node will have a large effect on the computation graph. But if we have a different computation graph such as this, you can see that some source nodes, like the fifth source node highlighted with the blue, has a large effect on the computation graph. It pretty much touches all internal nodes in this graph because of it's a very critical token. And in this case, the relative LOI will be high because some specific source node has a higher effect than all other source nodes. And then why is this important to characterize, right? So when we characterize it, we can think about what it means to have small, absolute, and relative LOI. It just tells us that we have really simple compositional functions. One example is where your DAG is always a tree, always a nicely balanced binary tree. Those models will have very small absolute and relative LOI as long as the neural component is not super complex. But it's not an interesting class of problems, right? Because class of functions, because most problems are not solved through a nicely balanced binary trees. You can also have one where every source token can be very important, and then that means you have small relative LOI but large absolute LOI. But this is a very extremely complex class of extremely complex compositional function. They're very, very complex. The compositional complexity is extremely high. And then there's not a lot we can say about that. But there's a sweet spot. There's a class of functions we can think about where you can have moderately large absolute LOI, but also large relative LOI, which means that we allow some tokens to have a lot of influence. Like we do in language, right? Like we say something, but sometimes we change a single word, like not, or change something to is not to not is, and that changes the whole meaning of the sequence. We can see that some tokens can have a lot of influence over the whole input, but most tokens have a simple compositional structure. So they have these properties of localism and synonyms and systematic generalization that Parisa was mentioning. So this middle class of functions is what we think is an interesting class of functions, and our formalism kind of allows us to distinguish between these different classes of compositional function. But we can also kind of analyze the compositional complexity of existing models, like the recurrent models or the convolution or the transformer-based models. And what these numbers, and without going into the detail, you can see that the quantity C actually is, which shows up in the absolute LOI, is something that encodes the complexity of the neural span encoder. So there's a neural component, and you can think of the C as how complex this neural function can be, how complex functions can this neural encoder model. And the more complex it can model, the higher the complexity. But the remaining factors like L and M, these correspond to the sequence length and properties of the combinatorial properties of the DAG that the function induces. And if these DAGs tend to be really, really complex, then these compositional complexity will be very, very high. Again, these are theoretical quantities, not something we can compute by hand. But for a given model, we can kind of compare between models. Another factor beyond compositional complexity is kind of like, can these models operate on any length sequences? And nowadays, a lot of these off-the-shelf models can, in fact, do that. Except transformers have a tiny issue of position encoding if they need to learn the position encodings, or if their position encodings are something that they have to explicitly store, then for longer sequences, they end up with like out of distribution generalization and start struggling if they're given longer sequences than what they have seen at training. There are ways to mitigate it. Of course, the other thing is, any of these models induce an input-dependent computation graph? And the sad news is almost all models do not. Some specific form of convolution and pooling models do give us input-dependent CDAGs, and transformers with specific form of sparse attention give us input-dependent computation graphs. Now we might ask, why is this important? Why do we want an input-dependent computation graph? And to kind of understand that question, we understand the effect of an input-dependent computation graph. We ask the question, how well can a compositional function with the input agnostic CDAG approximate a compositional function of the same complexity? Everything else is same in terms of their complexity, but with input dependent CDAGs. And this is a lot of math, but what this is just writing out is what is this approximation where I'm letting the functions have the same level of complexity, but one gets an input dependent CDAG and the other gets an input agnostic CDAG, but the input agnostic one that it chooses, it can choose the best one for itself. So it's this min-max kind of result. And what we can show that this approximation has both a upper and a lower bound, which means that the lower bound means that you can never do better than this. And the upper bound means that the gap between the fixed input agnostic CDAG models and the input dependent ones is upper bounded as well. But in both cases, this upper bound, these bounds depend on this locus of influence, the absolute locus of influence. The higher this is, the larger the gap. And if more complex the composition, so the more complex the compositional complexity of the model, the worse the approximation. And input agnostic CDAGs cannot sufficiently approximate input dependent ones. So you don't have expressivity, kind of connecting it to what Parisa was mentioning previously. But for the same absolute, you also want higher relative locus of influence for better approximation. And so input-dependent ones are just more expressive. But beyond that, beyond expressivity, can we say something more? And one of the things that we kind of try to analyze is generalization. What can we say about generalization of such a compositional model? And we have to, this kind of studies this systematic generalization. So it's kind of analyzing that situation where we have to talk about generalization on unknown combination of known parts. But we simplify the setup where we are even giving the ground truth function, CDAG function, and we only need to learn the span encoder and the readout function. Everything else is given to us. And in that case, we can kind of theoretically show that the gap between the generalization error, which is usually the gap between the training loss that we see and the true loss, is bounded by a bunch of different quantities. One of them is the number of training samples, so more training samples help. But the other quantity is this absolute locus of influence. Larger this is, the worse you're bound. So again, as your compositional complexity of the model goes up, your generalization bounds also go down. So again, overall, like what do we have now? So we have a novel definition which tries to kind of tease the symbolic and neural parts of a compositional function on sequences, and the definition includes many off-the-shelf sequence processing models, and this abstraction allows us to quantify kind of the complexities of the model. So we try to argue that compositionality is not a binary property, but rather something on a spectrum, and this abstraction also allows us to develop expressivity and generalization guarantees, and this was kind of part of our paper that we presented at HGAI last year. But some of the insights from this paper, from this work, was also that kind of gave us insight why transformers are just more expressive than sequence models like RNNs. It's because transformers with their softmax attention kind of implicitly give us an input-dependent CDAG implicitly, not completely. There's a subtle difference there. But they also have higher complexity, so they can just model more complex functions. But it also answers an observation from very old. So in old vision models, one of the things that was observed was that max pooling was always practically more performant than average pooling. And I don't think I've saw any answer in literature which tells us why this happens. And our theory kind of indicates that this is because max pooling actually induces an input-dependent CDAG, whereas average pooling does not do that, giving more expressivity to the max pooling-based models. And then we hope that this kind of analysis opens up a new way of thinking about existing models as being both neural and symbolic. Of course, it doesn't fit all neuro-symbolic models, but just specific class. And thinking about this, we hope that can also help us improve these models. But beyond that, we also want to see, like, does this practically help us for anything? And we kind of do a case study with transformers here, where we take like the full self-attention model, which looks at everything. The softmax kind of tries to limit what it looks like, but it's still explicitly looking at everything. So you kind of think of the picture here as kind of the attention mask, and in an alternative way of kind of looking at attention is you do sparse attention. So you have different kind of sparse attention, whether it's banded or whether it's block local, where you only look at a certain window, or you're strided, you look at every third token and so on. But there's another way of doing sparse attention where you look at only the highest attention scores, like the top 5 highest attention scores, and ignoring everything else. So in that case, you don't have a nice pattern in your attention mask, but you still are kind of looking at the highest attention scores. And from our complexity analysis, we can kind of say that the full attention model has a higher complexity and the sparse attention models kind of reduce this compositional complexity. So when you reduce compositional complexity, remember that meant better generalization. But even within these sparse attention models, these input agnostic masks kind of are inducing input agnostic computation graphs. So they're less expressive, whereas the stop K attention kind of induces an input dependent CDAG, so they are more expressive. So we also have this nice distinction, but the question is, does it matter in practice? And what we found out when we did targeted experiments to understand this is that it actually does matter significantly. So this is the training of a model, the same transformer model, everything is same, every hyperparameter is same between all the models. The only thing is we change is the attention mask. We either do full attention or various forms of sparse attention. And then we train the model, and this is for the list ops problem that I was previously showing you. And the full attention is the black line, whereas the top K sparse attention, where it's only looking at 5 highest attention scores. And then the other forms like a banded or block local are different versions. You can see that the top K actually is converging faster because it both has the expressivity it needs combined with the fact that it's just a lower complexity model. And this faster training, you can see it's converging, the training loss is converging significantly faster. And this faster training is also translated to generalization. So this one is the plot on the bottom is showing the accuracy on the held out set. And you can see that the top K model very quickly starts generalizing faster than the full attention model. Of course, none of these models are doing very great because they're at 35% accuracy. So they are not systematically generalizing as we want them to. So that's still an unsolved problem. But here's another problem where this comes from a context-sensitive language problem. It's called missing duplicates. You're given in the sequence two copies of the same sequence, and then one of the second copy has one token missing, and you have to look at the previous sequence and find the missing token. And in this case, again, the stop K attention converges in training loss significantly faster than full attention and generalizes significantly faster. And in this problem, transformers actually can solve this problem, and the stop K attention gets to 100% accuracy significantly faster than the full model. And the input agnostic masks are actually failing in this case, and they either don't have enough expressivity, and so they don't converge, or they converge much slower than the full model. And this is, again, something that was predicted by our theory. So overall, kind of our theory that we was making certain predictions, which we were able to validate empirically. And there were many other theoretical insights that we validate empirically, which was very good to see that we made some predictions and it was validated. And this paper, you can go to this. This is on arXiv right now to kind of understand our results more deeply. And this is with Ken Clarkson, Tim Klinger, Shashank Kuvuru, and Alex Gray. And with that, I thank you for your time. Again, just as a reminder, this is joint work with Tim Klinger, Ken, Shashank, and Alex. And you can find the papers that have more details at these QR codes. And thank you.
All right. Thank you so much, Pari. Just have a few minutes, but just want to comment. So this is the first in our mathematical foundations block. And, sometimes theory lags practice, but sometimes it points the way and to better practice. And I think what Pari just showed us as the punchlines of his talk is starting to do that, starting to show the way. And Arvind warned us about in his talk was we may need, in general, as AI researchers, to figure out which ideas need moving us back. Not to pick on transformers, but maybe that is the way. But if it were not transformers, this is the kind of tool that might show us the way, or might let us imagine, based on abstract properties, the kind of model that maybe we should be going for. So, as a early researcher, especially getting into neurosymbolic AI, these are the kinds of things I would look for: is fundamental concepts that could be used to build a new theory, a new framework. So really have a compositional complexity. So here's a question from Benjamin Grossoff, one of the leaders of our community at DARPA. So locus of influence in the computation graphs is quite related to dynamic dependency graphs and declarative logic programs that use, for example, tabling algorithms, including incremental tabling. That's a way to extend the neuro-symbolic further into the symbolic realm. Unless you have a comment on that part.
I mean, I would say that I would say that there probably are connections. I don't claim that this might be a completely novel idea. And I think there is a lot of existing literature that we need to look back at and understand and apply that to understanding new models. And this is just preliminary work, and we want to build on this. And I think some of the connections, I would love to look into them, and because I think it would be very critical in making these more broader. And I saw some related question on the chat as well on this. I don't have any straight answers on whether these can be exactly computable or not, but at least theoretically we can compare different models and understand what can I change in the architecture that will reduce this, at least theoretically, and that can then give me a new architecture. And that's what we did with transformers. We looked at what needed to be changed, we changed it, and we tried the experiments, and it turned out it worked. I mean, we didn't have to do any tweaking to make it work. Again, it's not solving all problems everywhere, but I feel like this is a way where theory, old and new, can help us get new architectures.
One super quick last question. If I remember well, Tim Klinger had a talk here about generating output in somewhat simple grammars from Gen AI. Is the bigger picture of your endeavor an effective system for translation? According to COTS, for example, LM to Prolog, the Psych-L in the end.
I mean, I don't think, like, I think our goal here is just to understand what's going on. I wouldn't claim that we want to do any specific kind of specific method or specific goal. It's just to understand what affects the expressivity and generalization of these models. And if we can understand the factors, we can target those factors in the architecture and see if it helps. That's a bigger abstract goal. And the examples given here could be one specific application. Honestly, I don't know much about that specific application, but it could be one such application.
Okay, we have a few more questions, but Par, if you want to jump on Discord, if you have time, that you can jump on those questions. Otherwise, thank you, Pari, great stuff. Is our next speaker here?
I think I'm here. Yeah.
All right. Welcome, Peihao. So now this is, I think, very, very interesting. So Peihao is going to see one thing I was going to mention in my overview is that you have various approaches to Neuro-Symbolic. Many of them are actually things like what we'll see tomorrow, where an LLM is guiding a symbolic solver or something. So there are still two systems, you could say. But the deep, deep kind of connection and intersection of neuro and symbolic, to me, is a very this is extremely promising, and where we should be looking heavily. And it's difficult going. Okay, so I think what Peihao is going to show us, going to give us some insight there. Okay, this requires a little bit of mathematical background, but Peihao will guide us through. So take it away, Peihao.
Great. Yeah. Thanks, Alex, for introducing. So can everybody see my screen?
Mm-hmm.
Okay, cool. Is it like in a full screen mode, or it's still in a?
It's not full screen yet.
Okay. Yeah, maybe I should put it here. And all right. Yeah, maybe I just yeah, presenting this way. Okay, cool. So yeah. So yeah. So as just Alex introduced, today my topic will be about how can we train neural networks, but can still discover the symbolic structures with gradient-based training. And this work is done with Professor Zhang et Wang. Right. Sorry. Let's do. Okay, cool. So so today, yeah, we have witnessed the surprising success of LLMs. Like just a few weeks ago, I was just witnessed the success of the LLMs in the IMO competition. So basically, there's like official announcement about like DeepMind OpenAI's models can solve math problems at the top level of students, at a level of competition level math problems. And there's like lots of like coverage about this news. And at the core of these models, I like, for example, last year, people still think of like they want to just embed all the symbolics into the language models. And luckily, they have some progress, and they produce alpha proof and alpha geometry. That has like I think it won the silver medal. But this year, they just make it totally language models, pure neural, while won the gold medal. So, but what we all know about this model is that it's just like this type of neural architectures, a pure transformer end to end. So now it raises up the question is, since the LLMs are like pure neural, and its training objective is still statistical pattern matching, we're thinking of like how it can actually do the reasoning. So because like reasoning is very quite symbolic stuff, because for example, there's like very simple reasoning tasks. So in a text should be read like this, but intelligent structures should be have this type of like very complex logical deduction. So at least each step you will see is deterministic and programmatic, and each step also follows a set of logical rules. While we are training language models, we're still asking language models to predict the next tokens, and trying to minimizing the likelihood of the data. So the natural question is, it looks like the neural networks learn to truly perform logical reasoning, while this type of statistical pattern matching. And this type of mysterious, we're gonna trying to figure out why this might happen and under what kind of circumstance it will happen. Also, okay, so so maybe we just start with some like arithmetic reasoning examples. This is what people have observed before. So by saying what we care about, like symbolic, a neural network has already exhibited these kind of capabilities. For example, if we want to teach the neural networks to perform arithmetic calculation, people have observed that if you train models to perform like 50-digit operands, they can generalize perfect to operands with like 100 of digits. And more importantly, it shows like very important compositionality. It is when you train a transformer, for example, on addition and the multiplications separately, and with like nearing new data or even like future data, you can generalize the whole models to evaluate the expressions with mixed operators. So this exhibits some compositionalities when you are training new networks. Also, people also find out those neural networks are quite interpretable because when they just probed some like intermediate layers, the intermediate activations, they saw some like interesting patterns. For example, this is a visualized attention map. We are doing some reasoning task, and it exhibited some very sparse structures. That was trying to like doing very strict and rigorous calculations among those symbols. So people maybe feel like this type of attention values can manifest as a symbolic rules among the tokens. So despite there's like very stereotypical dichotomy of symbolism and connectionism, like before people believe symbolism is rule based, so it's more like generalizable, and it's more robust. Symbolism is can have like better compositionality. But the downside of the symbolism is trainability. It's hard to find a optimizing algorithms to find out those symbolic expressions that is applicable to all these data. But while in the past people believe connectionism, while it's very trainable, but people feel it maybe it's very hard to compose like different components to form a new networks to perform new tasks. And people may also feel connectionism is still doing statistical pattern matching. So it's not that safe. It's not that robust. When you change the inputs, it's likely they will change the behavior completely. But now people surprisingly find out the connectionism is just like satisfies all these bodies altogether. They're pretty robust, and they can compose. They can do very compositional reasoning on various of tasks, and definitely they're very trainable and quite scalable. So we're trying to figure out why neural network training can actually achieve those properties. Like you training a new networks, but it manifests as some like symbolic architectures. So to begin with, let me define the problems we want to tackle here. And despite this is kind of like very narrow setting, but this actually already shows some like insights how neural networks can discover those symbolic structures. So the task we care about is the modular addition. So formally, giving a finite Arbian group A with a commutative group action, we're trying to train new networks. That takes two inputs in this group, encoded as one hot embedding, and using gradient descent to train these networks, and trying to make sure that they're composed of these two elements outputs the target values under the defined group action. And the new architecture we care about here is just two-layer MLPs. Again, it's not a transformer, but we want to use these very basic settings to show why still training such simple networks can still have symbolic structures. Again, the first layer is the embedding layer. We embed the finite groups elements into one hot embedding, and we have a new networks layer. So for each input, like A1, A2, we have like separate Wheeler matrices. We apply them to the inputs, and here we adopt a addition that we combines the outputs of these two branches, and we also assume the activation is quadratic. And later we append another layer. It's called WC, and this there gives the outputs. Hopefully in the one embedding space. And here is some like notations. So the first is n. So n is the number of the group elements inside A. So since it's embedding there, so this weighted matrices should have n many columns. And the Q, this is the hidden neurons, which means the hidden dimension of neural networks. It's just a hyperparameters we're doing the training. And the further step beyond is we want to represent those weights in their Fourier space. So that is, we do the Fourier transform over the W's, and we convert them into the Z's. So the original weights, like the column of the weights, will be represented as the Z's times the Fourier basis. And we just flatten the basis for each neuron as Z, J here, which is concatenation of each matrix, each columns of these matrices. And now our training objective is we are trying to minimize a mean square loss over all the pairs of A1 and A2. So it is this is output of neural networks, and we do some normalization, and minus the crunches, that is the A1 composed with A2, the one hot embedding. And we also apply a centering matrix, and then we to make it unbiased, and we adopt the L2 to compute the losses and sum over all the pairs. And optimization is still very standard. We want to minimize the loss defined here using gradient descent. And in a continuous regime, we consider the gradient flow. And with all this setup, we can reach the first result, which is a very interesting decomposition of the loss. So what we have shown is that given this loss H, we can reformulate the H as a sum over all these small L's in a constant values here. And all these L's, there's like lots of terms like rho here. So yeah, despite this is actually a very complex expression, but later we will show it have very simple solutions. But the core component here is this rho here. So the key observation is the loss functions are solely dependent on those rows, and those rows we can observe those rows are are some like functions. Depends on the empirical measures of those neurons. So basically, the empirical measure basically means we just sum up all these delta measures of the of those neurons. And furthermore, the H depends on the measure through a average subset of monomials. So basically, the monomials basically means it's given the vectors. We're just trying to find a subset of those elements in the entries in the vectors and do the products of them together. And you can observe those are just like basically monomials and indexed by the P, K, and J here. And we are first evaluating the monomials over one neuron, and we compute the expectations over all the neurons indexed by J here. So by those key observations, what we can generalize is that we assume that the reasoning tasks admit like very similar structures. So we define a more generalized tools called monomial potential. So the monomial potential is basically a mapping between the measure to real value. That is given the measure mu here. We are the associated monomial R evaluates on the sample Z, and then we take the expectation over all this over all these days and evaluate it on the R's. So mathematically, it can be written as the expectation of RZ here. So by this kind of generalization, what we mean is we want to analyze the limit in the measure. So even maybe this this formulation is still on the finite neuron space, but here we generalize to the infinite regime, which means we have like infinite wide neural networks. And then those rows will be redefined as the monomial potentials evaluated on a measures, like arbitrary measures over the neurons. Then the whole loss functions can be written as some functions of like rows, of like manual rows here. For example, in the original task, we define the rows like index by case. So those are just like set of like monomials. So we just define like many monomials, and we define the monomial potentials associated with those monomials. And we can transform these laws to like functions defined over all these monomial potentials. And now the optimizations transforms from the standard gradient flow, like this one, to the measure space optimization, which is naturally the Wasserstein gradient flow. It is defined as this. So intuition of this formula is that at a very like small steps, we take very small steps, and we want to minimize in the loss functional h here defined on mu, such that the minimizer has like very close distance, Wasserstein distance to the mu t at last step. And this formula itself is basically a Wasserstein gradient descent. So it measures how the mu evolves under the gradient of the loss, under the gradient or the first variation of the loss functional in terms of the mu here. So it's just like a natural gradient descent, but over the geometry of the measure spaces. So all above, we have a summarization. We have a summary of the generalization. So first is from a motivating example, we know that the loss function depends on the empirical measure of the neurons. So now we generalize this empirical measure to arbitrary measure, and we know the loss functions can be decomposed as the functions over some like expectations evaluated on some monomials. So those expected monomials is denoted as mu here. So we generalize it to a mu of arbitrary monomial and evaluate it on arbitrary measures. So it's expected a monomial. In the loss functions, we define over these. Now we can transform it to define over the coordinates of the rows, and those and the loss functions and there's another terms called L. So it is like functions, but its functions solely depends on the rows here. And the gradient descent is generalized to the Wasserstein gradient flow over the measure space. So by all this generalization, we can start our analysis to the whole framework. The first very interesting results we show is that if we go back to the modular addition example, we can find out that there's a minimizer of the whole functions, but which is like Boolean assignments. So the basic solution is that this kind of like mu's will equals to 1 if the k is not 0, and all other solutions are just like all other like rows are just zeros. So there exists a Boolean assignments of those rows such that it can make this loss to be 0. So what we can find out is that if we solve these problems using gradient sense, we have another solver which is served on the row space by assigning like Boolean assignments or Boolean variables. Make sure they are Boolean variables. We can still solve the problems on the row space. So those MPs likely plays a very similar role to the Boolean variables or the logical variables in the symbolic tasks, and then the L actually encapsulate all these rows is actually a logical expression or symbolic expressions over those Boolean variables. But this is just like a very quick intuition. So maybe we can just define it more rigorously. For example, suppose if we measure mu here, in our general setting, we define the 0 set and the 1 set as follows. So basically, the 0 set means it is the a set of like monomials that has like 0 monomial potentials over the mu. And similarly, the 1 set means we are defining a subset of like monomials that has monomial potentials equal to 1. So we define the set R1 and R0 and R1. So the 0, 1 set tests satisfiability of HMP for the matter mu here. So the solution of the test we saw before, the Arvind group reasoning, can be written as it has 0 set, which is a set of monomials that is nullified as the intersections of those 3 sets, while it has 1 set of these forms. So basically, we decouple the effects of each monomials to different sets that makes those monomials 0 and 1s. But further on, we can saw something that is even more interesting. It is given 2 measures, we can find out they do have compositionality structures over their weight spaces. So first of all, one thing we want to note is that those mu1 and mu2s, we can regard them as weights. So they are defined over weight spaces. And doing composition on the mu's basically means we're composing the neurons in the new architectures. And but the effects, what the effects after we compose the mu and the mu1 and mu2 is actually very interesting. But first of all, let's just define some operations we trying to compose those measures. The first is we want to trying to like do something like addition. So we're mimic addition, and it's very simple. We just add those measures, evaluated on A's separately, and add them together. And this is what we define as the addition operations. So we create new measures by adding 2 measures together. And then we can also define the multiplications. This is a little bit more complex, but intuitively we can understand in this way. We first sample neurons from the mu1, and we sample another neuron from mu2, and we perform the animal-wise multiplications between these 2 samples we sampled from mu1 and mu2, and then we form the star here. And this star and the distribution of these stars we define it as the products of the mu1 and mu2. And also similarly, we can find out there's like identity elements, which is like 1. That basically means if we multiply this 1 to all other measures, is still the same measures, and there's like 0 elements. So after those algebra we define between measures, we can find like very interesting structures. First is so these structures is those algebras actually form a commutative semi-ring. That is, those naturally follow some ring structures, and the LMP, the monomial potentials, is actually a ring homomorphism that actually preserves those operations between measures, and it converts it to the space of those MPs, the monomial potentials. So let me be more specific. If we add those 2 measures together and feed them into a monomial potentials, its value will equal to we evaluate the first measures over mu r, and then we evaluate the second measures over mu r, and plus the final values together. And if we multiply those 2 measures together, and it will manifest on the monomial potential space as we multiply those 2 monomial potentials evaluated on each measures. So this actually shows that the compositions under the matter space, which means under weight space, can be transformed to the row space as the same operations. While this plus and this addition, while this addition and this multiplication just follows this the most basic algebra on the real space. So this can we can show some like very interesting analogy. So we on the matter space, we're composing the neurons. We are doing addition type composition, which is where it's similar like we are stacking the neurons together. We're stacking two architectures together. And multiplication means we are coupling neurons together. So we compute on their weight space and we form a neural networks. And after we compose those neural networks, its functionalities can be composed as if we were doing additions, which is like the OR operations over the MPs. And then we are doing the multiplications between MPs, which is like the add operations between logical variables. So this actually shows that if we have partial solutions of those neural networks, we can just compose them together, and it manifests on the MP space as the same as the corresponding logical operations. And here is just like some very basic examples. Like for example, if the mu1 has 1 0 set as the RO and R1, and the mu2 has SO and S1. If we compose the weights, they will have the 0 and 1 sets as this expresses. So that basically means if we compose their weights of those two neural networks, then their 0 and 1 sets will also change accordingly through a intersection and union operations, mimicking as a logical operations. And we can just compose them to maybe follow any logical expressions as we want on. So or conversely, if we want to form a logical expressions, then we can convert it back to the weight spaces by using algebra we define over the weight spaces. So the first main takeaway is that actually those symbolic structures are hidden in the neural weights. For example, the symbolic variables is actually the MPs, because MPs encapsulate the weights and abstract the weights as a symbol, as a 0 and 1 symbols. We also find out logical connectivities. It is maybe the algebra we defined over the MPs, and then that can be translated to compilation over neurons weights. And those algebras actually admit those compositionality. So we can do composition on the weight space, and it manifests as if we're composing the LMP representing samples with the NL or logics. So by all this, we find out, okay, there's some hidden structures, hidden variables defined over neural weights that can manifest or behaves as a symbolic variables. And we define algebras that can make them do logical computations. Yeah, but with all defined build, we still like understanding that what happens during the training, because during training we are still doing optimization over the weight space. But what we know is if we regard the rows as the symbolic variables, what will happens on those variables. So here is here's the further step we want to answer. Like, can we do neural network training but still kind of like doing the optimization or the regression over the symbolic space? We have the second theorem, which shows that under like very certain condition, we can achieve this. So let me just first pull up the main results first. So it is, if we were using the oscillator gradient flow to update the measures here, and under those three conditions, I'll elaborate later. The dynamics of the molecular potentials, which is regarded as symbolic variables, will admit a trajectory. That is, we are doing coordinate-wise optimizations of each rows in terms of the gradients of L. So here is L again, means we are combining all these rows together. So it plays a role similar to a symbolic expression. And we are trying to use the gradients of this L to minimize the rows and trying to align it with the symbolic solutions here by the pure gradient descents over the symbolic variables. So this is gradient descent on the weight spaces, and this is gradient descent on the row space. And we find out under these three conditions, this dynamics actually naturally translates to these dynamics over the symbolic variables. And those three conditions are, the first is we start from Gaussian initializations of those mu's, which is very standard. And second is we assume that all these monomials we used in the monomial potentials are of degree of larger than 3, and it is odd. It's just unlike regularity conditions. And fortunately, this is actually naturally satisfied by the modular addition examples we showed before. And another very important condition is that the gradient flow or the velocity field induced by the water-Sutton gradient is OD equivalent. That basically means if we transform the if we rotate the measures inside of this bracket, then the whole velocities will admit the same rotations or transformation or orthogonal transformations. This is not really satisfied, but in our example, it's still satisfied. And yeah, we can check the more details in the paper, but it's still satisfied. And it can also be used as the additional conditions for the generalized task. For example, we use it as the principal design architectures to make sure their velocity fields is OD equivalent. And I will show you example later. But back to the main results, what we show is that under these two conditions, on a neural weight training translates to symbolic regressions. So that is a gradient flow on the measure space translates to a gradient flow over the symbolic variable space. So here's like a more intuitive illustration. So basically, if we are trying to use gradient updates over this loss landscape, and at each step, we're actually trying to transform we'll actually also have a corresponding symbolic updates in the symbolic space. Yeah, and the critical constraint that this velocity fields is OD equivalent. But what's the benefits of this symbolic gradient descent? So a very direct example is if we again go back to the modular addition example, what we're going to find out is that, for example, for these for those MPs like the row KKK, if we derive their gradient trajectories under its framework, we find out it follows its trajectories, and its convergence is that those variables converge to the converge to 1, which is the binary results we expected before the particular solutions we saw before. So this actually guarantees those variables converge to the binary assignments we want before. And here's another very important insight. It is during the whole trajectories of optimization, there is a very natural dimension reduction. That is, if we are minimizing the differential entropies, while make sure those variables converges to the MP constraints to satisfy those MP variables, putting assignments, then we can show that the solution space can be the solution space over the measures in the measures can be constrained to a finite dimensional Riemannian manifold. So like the original measure space is infinite dimensional, while if we convert the whole optimizations to the symbolic space, and by this concept and by this means we can show that where we can also constrain the whole neural solutions to the very low dimensional space, and this actually guarantees the neural net weights has like very limited trajectories during optimizations. Here's another series about renormalization group type degree of freedom reductions, but I'll skip it here to save some times. But the main message has already been delivered. The first it is that the measures represent the neural weight space will go through a dimensional reduction process, as we showed in these slides. And simultaneously, what we can find out is that the neural network training can reveal a symbolic learning process and at the MP level. And another very, very important message is that we need those models to follow some geometric constraints. So here another insight is geometric constraints is more like a continuous version of the symbolic constraints. So for example, graphs are very symbolic stuff, so symbolic subjects. But we can, and the graph is topological nature. But we can translate those graphs to their geometric embeddings. For example, doing Laplacian decompositions, and we then obtain their geometric constraints, geometric embeddings. And if we put the geometric embeddings to neural networks, then it starts to work because it embeds those symbolic and discrete structures with continuous embeddings. So this is the core components here. And we again show that those geometric constraints actually can facilitate our neural network trainings to follow a symbolic regression process. And we also provide a result to show that we can do the symbolic, we can do the invariant starting with neural networks with some like sample complexity guarantee. But what I want to really emphasize is that we recently come up with a instantialization of this idea that we try to embed those OD invariances into architectures by improving the position embeddings of transformer architectures. So we think of this as one step towards we want to enhance some like geometric constraints in the new architectures, then to discover the symbolic structures better. And here are like two slides of a very quick summary of what we did. So we proposed a position embedding called tape. And a tape is actually position embeddings jointly nerd with the token features. How it was jointly nerd with token features, it is we use these position embeddings and specifically their inner products to modulate attention weights. And this is quite standard as used by lots of like attentions. But simultaneously, we also use the attention weights to update the position embeddings. And we'll also use the feature of the tokens to updates to inform those position embeddings. So by these two mechanisms, we actually inform the position embeddings with the token features. And what we start from is that we actually want the architectures to embed some geometric constraints, and all these steps naturally follows the OD equivalent with respect to the position embedding part. So this gives us a geometric constraints in the transformers. And theoretically, we show some like interesting results. It is if we consider the attention with our proposed position embedding and the attention with some, like, for example, rope, the very standard position embeddings, we can show that the pure attention is known to be under TC0 circuit complexity. That means those attentions can only simulate a very limited class of algorithms in those complexity classes. Well, we can show that if we contextualize those position embeddings and under those geometric constraints as well, we can enhance these algorithms reasoning capacities by provably show that the architectures equipped with our position embeddings has NC1 complete expressive powers of the algorithms. So if NC1 is proved to be strictly stronger than TC0, then we can also find out that our architecture is strictly more powerful than attention, and it can simulate a larger class of algorithms. And also kind of like inspired by last presentations, I just found out that we're talking about competition graphs, and there's like mechanisms. We actually contextualize the position embeddings with the sequences, and we can we find out those structures those context-dependent structures can provably enhance the reasoning capacities of those transformers. And also, another rule of geometric constraints is that we can make sure that this position embedding is still a relative position embedding. So, so it has like better density exploration and generalization because it encodes position information in attention with the relative distances between the tokens. Okay, so finally, just a quick summary of today's results. First is that we show like very strong algebraic structures that is inherent in neural networks. And by this, we define what symbolic variables hidden in the neural weights and what are their logical connectivities and how can we achieve compositionality over the weight spaces. And the second result is that if we use neural network training on the weight space, it can still lead to the symbolic solutions, but under the geometric constraints. So yeah, by these results, we show that under geometric constraints, the evolution of the neurons distributions will manifest as a symbolic regression processes that we are doing the gradient descent in terms of the those logical variables through the logic expressions here. And next is that we want to call for the geometric constraints in those architectures that embeds discrete structures and symbolic structures into those continuous architectures, and that actually enhanced and facilitate symbolic learning in those new architectures. And that'll be all. Yeah, thank you for listening. Maybe we can take a few more questions.
Great. Okay, thanks so much. Questions? Okay, we people are still looking up concepts in their math books, I think. But I'll ask you a question. So, just to be clear, so reasoning, for one thing, you're mapping to solution of Boolean assignment in the sort of relaxed, some kind of relaxation objective, right? So, but that's of course different from how reasoning is done in the logic world. You sort of apply some inference rule or a set of inference rules, some kind of search process. This is still a search process, you could say, but it's a gradient search process. So, but it doesn't have to sort of apply inference rules, or you could say doesn't have the opportunity to apply inference rules. So is it a pro or is it a con? How would you compare them?
Yeah, so so maybe from the very beginning of the task, we're trying to do modular addition, and I believe this is a very rule-based and it's very symbolic task here. And but if we translate it to neurospace, it is still a neural network optimizations. But what we review from those training processes is that we saw there are some like Boolean variables that is hidden in those structures, and the loss functions that are organizing and enclosing all these variables is what we believe something like the symbolic expressions of those variables. So yeah, I found this is not exactly this is not exactly what people used to believe the symbolic expressions and symbolic rules in symbolisms. But still, it reviews, I think, why those symbolic structures still emerge or inherent to neurospace. So I think maybe still need some efforts that we want to translate those languages to those rules, or even those MP space or those zero sets operations back to the symbolic constraints, right? Because here, one downside or one drawbacks of this interpretation is that we still don't find a meaning of what those monomial potentials means here. So it's some like potential variables. It looks like some logical variables, but it's not explicit variables that people can really comprehend. So all these logical-like expressions over those variables maybe it's very hard to interpret. Yeah, but we find out one thing we find out interesting is that so the logic may not be the same as what people believe or what people think, but the logic might be something else. For example, defined very implicitly using those potentials functions.
Well, I think one reason I wanted to highlight your work here is, I think this is really at the heart of, what many people think is sort of the true interface between neural and symbolic. So, for example, Yashua Bengio we had a few years ago, and in our panel, and it was a lot of fireworks in that one, so that's still my gold standard for hot, friendly debate. But the debate was about basically, do you need symbols, or in the symbolic AI way, or is it because that leads to combinatorial search, or is it better if you could and somehow necessary even for efficiency reasons to do that search in a continuous way, where translation roughly gradients. So this was Yashua's sort of, if I'm translating him right. So I think some people definitely have that intuition which you can use in many ways. Well, neural nets have the ability, in principle, is kind of what you're saying, I think, to represent the things we want that are discrete. Now, that leads to this next, but do they necessarily do it well is the next question, or can they be made to do it well? That's maybe a transition to Carlos has a question. If this work shows neural nets are able to encode symbolic constraints, why do you think that popular LLMs fail some logic? Simple logic puzzles, for example. Is it a problem with the training data distribution?
Yeah, I think this is a good question. So, so indeed we need those symbols. But I feel like maybe the symbols for the machines is maybe sometimes different from human, maybe. But indeed we need to enforce those new architectures and neural network training to find those symbols. And this is why we have the second part that if we were doing the weight-based optimizations, and when it can translate to the symbol space regression. Even though still we're doing continuous realizations, it's not like combinatorial search. But still, we found out that if we follow this symbol gradient descent on the symbol space, it converges to some like Boolean assignments. So at least for the modular addition examples we mentioned. So this actually gave us the evidence that it actually converges. But again, it's under the condition that some geometric constraints is encoded in those architectures or loss functions. And that's why we have this third part that we want to embed those structures into the transformer architectures. For example, if transformers feel hard to solve all those logical reasoning or the puzzles, that probably because it basically does not really satisfy those geometric constraints here. And our efforts here is we want to embed those or bring back those constraints into these architectures. So and again, as I mentioned before, those invariances and so these invariances, for example, ODE equivalence actually can translate to like, for example, on a computational graph, it's very discrete and symbolic structures, and it has some of the topologic and or maybe geometric constraints. It is some like permutation invariances or graph invariances, and this is like very discrete structures. And ODE equivalence actually translates those discrete structures back to the continuous space because it naturally operates on the continuous embeddings. That's why I believe those are very necessary steps. We want to, for example, inform the attention map or any continuous embeddings or activations in neural networks with those constraints. Even though this constraints looks very weird, but essentially, or I think there's might be something deep connected that it encodes the discrete structures that we need for like even harder and we want to generalize the transform and the scenarios that we want to generalize the transformers to solve like even more complex, for example, puzzles and reasoning problems.
Okay, we're a few minutes past time, but I do have one burning question. You can give a yes/no answer. Really, if there's a yes/no answer, give it. Otherwise, we'll take it offline.
Yeah.
But
Mhm.
it seems that when you're defining symbols,
Yeah.
is my impression is that what you really mean is a point mass on one dimension, and then when you're talking about these geometric constraints, what you mean is something like a knowledge graph has to be given as input. True or false? In both cases, that would mean you sort of already know what the symbols are. You want the thing. So symbol discovery is a different thing. So basically, as you set up that, you already know what the symbols are.
Yeah, my question is I don't really want to assume the symbols are known here. So I think yeah, this is also my my big assumptions over all these works. I know, and this also motivates us to find out what are the symbols in those new nets. For example, what we discover, what do we derive from those frameworks? Okay, those symbols can be have those Boolean variables, but those are all hidden in the neural network training. So when we train neural networks, those symbols are not known to us. Only when we do the mathematical investigation of all these architectures, we can find out. Okay, those are those quantities or those variables manifest as some like symbols. So
okay.
even those symbols, I feel like this is not. Yeah.
I see. So you are suggesting you don't need to know the symbols up front.
Yeah.
in your
Yes.
setup.
Yes.
Okay,
Yeah.
that's good enough.
It emerges from the training. Yes. It's hidden in the problem structures. Yeah. Yeah.
Very good. Okay, awesome. Super fascinating. I really want to ask you about the renormalization group stuff, but anyway, we'll do that another time.
Sure.
Thanks so much. Appreciate it, and I think hopefully this will inspire people to look more closely at this connection. All right. Thanks, Peihao.
Yeah. Thanks, Alex.
All right. Do we have the next speaker? Changlong.
Hi.
Hey. All right.
Yeah. I'm going to share my. Okay.
Okay. So, Changlong, another one of our early stars. Now, I mentioned.
Can you see my screen?
Yes.
Okay.
Let me just quickly introduce you. So this work I'm excited about because a lot of people, in general, in any paradigm, we sort of need to wait a while and see if certain things that seem to be deep issues, potential blockers, you could say, will they shake out? Will the paradigm eventually find a way within paradigm to shake them out? But at least one, I argue several of them, but at least this one, we have now a theoretical answer of no, you can never get rid of hallucinations with at least this next word prediction type model. So, but Changlong will elaborate on that and then show us not only negative results, but maybe a positive way forward. So I'm excited about this. Take it away, Changlong.
Okay. So thanks, Alex, for inviting me here. And this talk, I'm going to present our work on understanding the fundamental limits of learning non-hallucinating generative models. And this is a joint work with my advisor, Anand and Wojciech, when I was at Purdue. So this talk may be more conceptual than the prior talks. So it is more high-level talk. So let's briefly discuss some of the motivation of this work. So we all know that the generative models, particularly the large language models, are very powerful. For example, it recently achieved the gold medal in the IMO competition. But it also can generate something plausible that is factually inconsistent. For example, when you ask the large language model to summarize some works, to do some literature review, it will give you some fake references. So the hallucination, in some cases, it is mild. For example, if you want, so a fake citation will not harm much in your paper. But in some other domains, for example, in the medical diagnosis, you do not want the hallucination happens. For example, you do not want the large language model to make up some patient data. This will be a disaster. So there are some engineering fixes that has recently developed. For example, the reinforced learning from human feedback, and also the RAG, and or more recently the tool use, for example, the agentic AIs. But all of these kind of solutions are heuristics, so it can fail in some unexpected way, and it is hard to verify whether it will work or not work. It may be work in some domain, but it not work in the other. So this motivates us to ask the following more fundamental questions. So what is the principle understanding of when learning the factor correctly is even possible, and what is the conditions that allows us to do so? So now let us go to the big question that everybody would want to understand. So where do the hallucinations come from? So here we are not going to give a single answer to characterize for everything. So there can actually be a lot of reasons that cause the hallucination. For example, it may be due to the quality of the data. It also may deal to the knowledge standards. For example, maybe your knowledge is old. So it can also happen, for example, because of the computational limitation, because maybe your transformer cannot compute the function that gives you the functions that do not hallucinate. So here we take a different route. So we consider a fundamental problem. We will understand the hallucination from a statistical point of view. So we want to understand. So we will consider some scenarios so that even you are given a completely faithful data, and even you have unbounded computational powers, there can still be some learning scenarios where you cannot learn with non-hallucination models. This impossibility is information theoretically hard. So in order to do so, we will develop a learning theoretic framework. So there are two reasons to develop a learning theoretic framework. The first reason is to understand why the hardness happens. And another reason is more important, is to identify the minimal extra structure that allows us to learn a model that is non-hallucinating. Okay, so here I will give a quick overview of today's talk. So firstly, I will define formally for what do we mean by hallucination, and then I will define the learning goals. So what do we mean by learn a model that does not hallucinate? And then I will show you some impossibility results in what we call the agnostic proper learning scenarios. And we will show that even for very simple classes, you will not be able to learn a model that do not hallucinate. And then we will introduce our constraints. So we will introduce some conditions so that if you satisfy this condition, you will be able to learn a model that do not hallucinate, which we call a constraint class on the factor set. We will discuss later. And then we will present some positive results and also some lower bound. And finally, I will show you some potential new learning paradigms that can be derived from our theory. Okay, let's begin with the formal definition of our problem. So firstly, we will have a class X, where X is the set of all sentences, for example, or the collection of all English sentences. Now we also assume there exists a T, where T is a subset of X. We call the T to be a fact set. This fact set is we just assume there exists some fact set. There's maybe we don't know how to represent it, but there exists some set. Okay, then a generating model is simply a distribution over the sentences. So you can imagine the distribution generated by autoregressive transformers. So here the distribution is over the entire output. It is not a conditional probability. So every generating model is just a distribution over the sentences. Then we define the hallucination rate to be the probability. So for any given model P, and for any factor set, the hallucination is defined to be the probability you assign outside of the fact. Okay, then we define our observation model. So what do we observe here? So we will assume that your sample is generated from a faithful demonstrator, where a demonstrator is also a distribution over the data. So we assume that the demonstrator is faithful, meaning that it has no hallucination. Then what is a learning rule? A learning rule is a function that's mapping from the data. The data is a collection of sentences to a model, to a distribution over the sentences. By using the data just generated IID from this demonstrator here, we just assume it is IID for the ease of a theoretic analysis, but we do not have to be if you want to generalize this framework. So given this data, this learning rule will generate a model, P hat. So our core goal is to learn a model from some model class, for example, from the class of transformers, so that it achieves the minimum hallucination rate. So we are not going to learn a model that achieves absolutely zero hallucination. We just want to learn a model within this class that achieves the minimum hallucination rate. So this is a weaker goal. But we will show that even for this weaker goal, it can be impossible in some scenarios. Okay, now here is a picture of our definition. So the big ball is the entire sequences, entire sentences. And this green ball is what we call the fact set, which is unknown. So from this fact set, there are some demonstrator which is supported over this fact set, and it can generate some samples. And then another will use this sample to generate a generating models, and this generating model will support it over this circle, this small circle, and the hallucination will be this red part. This red part will be the hallucination for the different p hat. And here is a picture to illustrate the entire learning paradigm. So we can see that we have a model class P. There are not models, and if we know this fact set, then we can search through from this model class and find the best one that achieves the minimum hallucination rate. Okay, but this is just the ideal case. We never be able to know the entire fact set. What we actually know is some samples generated from this fact set, and we will use these samples to search through this model space to find some p hat. So we want to learn a model p hat that is as close as possible to the best models. And our question is, how can we use this sample to guide this search to find a no hallucination models? And under what conditions it is possible, and under what conditions it is impossible. Okay, so now here I will highlight some of our setup. So firstly, the hallucination rate will depend on some fact set which is unknown, even though it exists, but we don't know. So we only observe samples from some demonstrator that is supported over this fact set. So we consider the most clean setting where the data is completely fact. So in order for the learning to be success, we need to consider the following three conditions. The first is the expressive power of the model class, and second will be the structure of the fact set, and then we will consider the informativeness and of the demonstrator, which will allow us to handle the generalizability. Okay, so before we go to our technical result, we first define some of the technical terms. So the first term is what do we call the proper. So what does it mean for proper? Proper means that your learner must output a distribution that is within the class. So this is most common in the practical settings. For example, when you learn a transformer, your output will be a transformer also. And in order to understand the problem from a more principled view, we will also introduce another notion which we call improper. In this case, you can output arbitrary distribution in the class. So this is not realistic, but it will give us some baseline to understand what is possible and what is impossible. And here is a quick fact that we can observe. So firstly, if we can learn a distribution that is close to the underlying distribution, close to the demonstrator on the total variation distance, then this learned model will guarantee to be non-hallucinate. This is an easy consequence by definition of the total variation. But this this is actually a quite strong requirement to learn to be close to the demonstrator, because the demonstrator is unknown and it can be outside of the model class. So in order to appreciate it, in order to say that this is actually a non-trivial problem from a statistical point of view, we consider the following examples. So in this example, this is very simple. So we have three distributions: P1, P2, and Q, where Q is your demonstrator. P1, P2 will be your model class. So your model class will consist of two models, P1 and P2. And we consider two words. So in the first words, the TA, the fact set, the real fact set, will be the union of P1 and Q. So in this word, P1 will not hallucinate, but P2 will always hallucinate, right? Because it is outside of this fact set. And the second word, we call the word 2. In this word, the real fact set will be the union of P2 and Q. So in this case, the P1 will always hallucinate, and P2 will have hallucination 0. However, in both of this case, this Q is your demonstrator. This Q will be faithful in both settings. So Q will have a hallucination 0 in both of settings. So in this case, any learner that does not know this fact set will not be able to distinguish between this word, either word 1 or word A or word B. So because the learner must be proper, so it must select one of this P1 and P2. So it must make in one word the hallucination will be large with constant probability. So this is a simple example that demonstrates that the proper learning can be statistically challenged even when your model class has only 2 elements. So this will be our base example to demonstrate the impossibility result of why learning non-hallucination model is statistically challenging. Okay. Now, so one may argue that the reason the impossibility happens is because your Q gives no information, because the sample generated from Q will not be able to distinguish whether the sample is from P1 or P2. So in order to resolve this issue, we introduce a new notion of hallucination rate. We call the relative hallucination rate. So in this setting, we will define a relative hallucination to be the maximum probability mass assigned by P, your learned model, on any event, so that your demonstrator has a small mass. So intuitively, what we want to parallelize the mass on any real event under Q. So we see that P and Q, P is relatively non-hallucinate with respect to Q if for any real event of Q, for any real event of the demonstrator, the probability assigned by our learned model will be small. So this is a weaker notion than the absolute hallucination. So it is easy to show that so if the demonstrator is faithful with respect to some fact set, the hallucination rate, the absolute hallucination rate, will be upper bounded by the relative hallucination rate. So it means that the relative hallucination is a weaker notion than the absolute hallucination rate. So one argue that perhaps in this weaker notion we can learn, because this notion will depend on the informaleness of the demonstrator. So the question is, can we learn a model? Can we properly learn? Proper means that we must output the model within the model class that achieves the minimum relative hallucination rate. So our first main result shows that this is actually impossible. So we show that there exists a class P where the class has only 2 elements, such that for any proper learner again is just you need to output a model that is mastered within the class. And for any given sample size, and for any given error probability delta, there exists a faithful word. There exists a faithful word such that in this word there exists a model in the class that has no hallucination rates for both of the relative hallucination and also the absolute hallucination. But the model you learned must have a large hallucination rate. It is actually the maximum hallucination rate. It is 1. So this theorem tells that even for a class with only 2 elements, you will not be able to find a learner if you don't know the word. Okay. The idea is very similar to what we did in our first example. So we will also pick 2 distribution P1 and P2. So the model class has only 2 elements. But instead of construct a deterministic word, we will construct 2 random words. So in this case, in one word, the P1 will be bad. In other words, the P2 will be bad. And we will also make sure this Q will be indistinguishable between these 2 words. So in this case, we can show that even though there exists a model that do not hallucinate within the model, you will not be able to learn it from the sample. So what can we learn from this from a practical point of view? This tells us that by simply constraining the model family alone will not prevent hallucination. So if you are familiar with the standard statistical learning theory, we will know that if you have a small model, you will have better generalization. But in the case of non-hallucination learning, this is not the case. Even if your model class is only 2, you cannot prevent hallucination if you don't know the underlying process, the underlying model. So this means that we must require some prior knowledge about the fact set itself. So we need some inductive bias into the learning process that using the fact set itself, rather than simply choose a small model to make the hallucination small. Okay. So here I will give you some, in order to demonstrate that the result is non-trivial, that I will compare the result with some classical result in the agnostic pattern learning. So here we consider a setting that is called the agnostic density estimation. So in this case, we are giving a sample that is generated IID from some demonstrator, and our goal is to find a model within the model class such that the total variation distance between the learned model and the demonstrator is not much larger than the minimum total variation distance. So this is the minimum total variation comparing to the underlying demonstrator when the n goes to infinity. So if we can find a learning rule that achieves this, we will see this model class is agnostic pattern learnable. And it can be shown that there is a classical result that shows that for every finite class is agnostic pattern learnable in this sense. Actually, we can take this constant to be 3. So in contrast, for the non-hallucination learning, we just say that even for a class with only 2 elements, we cannot learn a model that achieves minimal hallucination rate. So that means that statistically, learn a model that does not hallucinate is harder than learn a distribution that is closest to the underlying distribution under total variation distance. This holds for both absolute and relative hallucination rate. Okay. So this result tells us that if we want to restrict to the proper learning, if we want to restrict to choose a model within a class, it is statistically impossible if you don't have knowledge about the word itself. So what about the improper learning? We just mentioned before. The improper means that you can output a model that is arbitrary. So you do not have expressive power constraints on this. This is the ideal case, but we will see what happens when you have this unbounded expressive power. So in this case, we can simply output the empirical distribution over the observer samples. So in this case, that we can say that the empirical distribution will achieve 0 hallucination rate, because we assume that your demonstrator is faithful. Everything generated from Q is a fact. So if you reproduce this empirical distribution, you will have no hallucination. But this simple rule will give us no generalization. You just reproduce your sample. There's no generalization. Okay, so the key question here is that, can we design a learner that generates novel content while remain factually consistent? And what is the minimum requirement for this to happen, for this to be possible statistically? Okay, so now our key idea is to constrain the fact set itself. We just mentioned that if you don't know anything about the fact set, there is nothing you can learn. So what about we constrain this set? So we assume that this set is within some concept class, where this concept class will be our design choice. So here you can think about this concept class to be a family of fact checkers. This fact checker can be determined by, for example, rules or constraint or simply a neural network that tells you whether a sentence is a fact or not. So here I will not make specific structure or something like this. And I will give characterization for what kind of structure is guaranteed to make you to learn model that is do not hallucinate. Okay. So conceptually, this class C, this concept class, will encode our prior knowledge about what counts as a fact. So with this definition, this is the definition that we want to assume over this fact set in order to achieve some possibility result. And as we just mentioned before, if you don't want any generalizability, we just reproduce the imperfect distribution. So in order to quantify how generalized of our learned model, we will introduce a notion we call the information measure. This will quantify how novel your learned distribution is. So a information measure is simply a mapping from your model and also your data set to some number. For example, you can think about this to be a Changlong entropy. It just measures how much information content in your learned models. And also you can think about it to be like, for example, the out of sample mass. So it is basically the mass you assigned out of your training sample. So we will use this quantity to measure how novel your learned model is. Recall that we want a model to be both novel and factually consistent. So now the question is, what kind of structure what kind of structure of the concept class C that allows us to learn factually consistent models and informative model, both factually consistent and informative simultaneously? And what is the minimum structure that allows us to do so? Okay. Now we are going to give our second main result. Our second main result says if your concept class, because this is just a set of sets, you can define the VC dimension. So if the VC dimension of this family of sets is finite, we can show that for any information measure, whatever information measure you choose, either entropy or the out of sample mass. So you can always find an improper learner. An improper learner is an arbitrary arbitrary distribution, such that if you observe this number of samples, then with probability with high probability, you will generate a model. You will generate a model that has hallucination rate upper bounded by the epsilon. Epsilon is what you can choose. It can go to 0 arbitrarily. So that means that your learned model has no hallucination rate. And also, this learning rule will also guarantee that the information measure of the learned model is larger than the information measure of the demonstrator. It means that the learned model is as informative as the demonstrator. So actually, we can construct a learner if we constrain the concept class, then we can achieve a learner so that it can achieve simultaneously no hallucination and informative comparing to the demonstrator. Okay, so the learner is actually quite simple. So what we're doing is that we will choose a family. So recall that the C is all the fact set that is possible. And so we have a set of data x1 through xn, and we will choose a subset Cn of the original concept class by choosing the fact set that is consistent with all the data. So if your candidate fact set do not include some of the true data, then I will exclude it from this set. So this Cn will be all the remaining consistent fact set. So all I'm doing is that I will choose a distribution, an arbitrary distribution that maximize this information measure, subject to the constraint that it has the hallucination rate over all fact sets or over all the consistent facts to be upbounded by epsilon. So with this rule, we can achieve these two guarantees. Okay. Okay. So here is a brief sketch of proof, but I will quickly go through it. So what we're doing is we first define a version space, which is the consistent fact set that is consistent with the current data, and then I can use some generalization theorem from the VC theory to show that if you observe this number of samples, then the actual this should be Q. Sorry, this should be Q. The demonstrator will have a probability less than epsilon for all the fact sets, and then the key point is that because the underlying truth, the demonstrator is within this class, and if you maximize this quantity, your information measure will always larger than the comparator, the demonstrator. So this will guarantee that you will. So this condition will guarantee your model is as informative as the demonstrator, and this quantity, this restricted set will guarantee that anything you choose from this set has no hallucination rate. And we can actually show that this sample complexity is tight. Our third theorem will show that if you choose this information measure or the out of sample mass, it means it is the mass you assign, not on the training set. Then we can construct a VC class such that your sample complexity must grow as like this. This matches our upper bound. So this means that the uncertainty of your fact set will determines how many samples you need to observe in order to learn a model that do not hallucinate. Okay. So we just say that in the improper learning case, if we restrict the fact set to some concept class with finite VC dimension, we will be able to achieve both non-hallucination and generalizability. So the question is, can this rule be generalized to the proper learning, which is more practically relevant, because we want to learn about this that is within the model class. So a simple way we can do so is to we do not maximize over the we do not do a unlimited unbounded optimization. So we just searching through a model within the model class. So this is a very simple way that we can think about. So unfortunately, this rule will not work in the proper learning case. The reason, even if we restrict this fact set, so you can think about our very first examples. In the very first examples, we have the concept class, and both the concept class and the model class are of size of 2. Yet any of the proper learner can fail. Particularly this rule will not work, even though it is natural. Okay, so here the takeaway is that, so even though the uncertainty about the fact checker is minimal, here we only choose between two. We only choose between two of the fact checkers. The proper non-hallucination can be information theoretically impossible. So here is a practical lens that we can see from this this theoretical result. So in order to successfully properly learn a non-hallucination models, we need both a informative demonstrator and also a suitable structure on the model class and the factual consistent class. So now we are going to introduce our final condition on the demonstrator and also the concept class and the model class. So we introduce a new notion which we call the sufficient informative. So we say that a demonstrator is sufficiently informative if for any given epsilon there exists a neighborhood where the neighborhood consists of all the fact checkers that do not violate the demonstrator up to some parameter. This parameter is determined by some function. So if there exists such a neighborhood such that for any model in the model class, the worst case fact checker will have the hallucination rate upper bounded by epsilon, then we will be able to construct a proper learner, actually just this learner we just mentioned before. So if this condition is satisfied, and then we can use this learner to produce a model that achieves the hallucination rate upper bounded by epsilon. Okay. So another question is whether the sufficient informative is a necessary condition or not. And we do not have a complete answer for this problem, but we have an argument that shows that the sufficient informative is close to minimum. So for example, suppose you take a demonstrator that does not satisfy a condition, does not satisfy a sufficient informative condition. Then in this case, we can say that there will exist some epsilon such that for any threshold, this quantity this condition will happen. So in this case, any learner must output some models. Any proper learner must output some models in the model class with this probability. So in this case, we can see from here that this model that you output must have a large hallucination rate if we choose the real fact set to be the set that's corresponding to the P to satisfy this lower bound. Okay, so here is a open problem. The open problem is whether our sufficient condition is necessary for the proper non-hallucination learning in the general case. Okay. Okay, so here are some of the future directions that I can think about that can be derived from our work here. So the first future direction is to develop some representation of the T. So far, we just give some condition. We say that if your T has a finite dimension, then you can learn the hallucination non-hallucination models. The more practical problem is how can we represent it? So one way we can do is to using neural networks, and also we can use maybe Neuro-Symbolic methods, which I'm not the expert at, but I think there are many experts in this workshop that knows how to do it. So another problem is to handle in the case when the demonstrator are not faithful. So far, our ORS theory will assume that a demonstrator is a faithful demonstrator. It has no hallucination. So what happens? There are noise. Another problem is that we can study some kind of scenario where the sample is not RID. For example, if we allow the sample to be active choosing, depending on the fact checker. So what can we achieve? The final thing is I will propose some of the more practical way for the learning rule, which we call the joint training of the generator and the fact checker. So here is this is our ongoing research we are currently doing. So here we propose a method to jointly training the generator and the verifier. So here we will parameterize by the verifier or the neural network, which is simply a function mapping from your sentences to 0, 1. So we don't know the actual verifier, but we know there exists someone in this class. And also the generator is parameterized by some theta. For example, this can be a transformer. And we also choose a information measure. And what we are doing is that we will training a model that minimizes this objective. So this objective has two parts. The first part is the informativeness, is your novelty of your model. The second part will parallelize whether it is parallelize the fact. So what we are doing here is that in the outer minimum, we will increase the informativeness, and in the inner minimum, in the inner maximum, we will parallelize the strongest verifier that is consistent with our data. So this is basically derived from our theorem 2, but in a more computationally efficient way. So this problem is generally non-convex and non-concave in general, because the model class is not convex. But we can approximate it by using a alternating gradient, the outer gradient descent and then the inner gradient ascent. So this will give us some heuristic approach to solve it, and this is actually inspired by the GAN. And again, this is still a proposed and ongoing research, and we haven't validated this approach yet. And here is the end of this talk, and you can You can find the full paper from here, the no-for-knox theorem, fundamental limits, and it is appear in the ICR this year.
Very nice. Thanks a lot, Changlong. Excellent stuff. So, I'll have a few comments, but first, so let me just say, for everyone, especially students, this demonstrates how did Changlong get to these results. This is a extremely skillful use of learning theory, among other things. So, so learn your learning theory is one lesson from this. You can see if we were really trying to get to a GI, for example, the G is generalization, then we have to be talking about essentially learning theory, right? That is our theory for talking about generalization. So just for those kind of looking to figure out what to learn, this is you've noticed learning theory used in a number of our talks. So now on learning theory, here's a question. I'm going to take this in a way as a general learning theory question. Given two neural net models, A has 10 times more parameters than B. Both get identical accuracy, let's say, on indifferent tasks. Is there a formal way to prove B's representational capacity is about the same or almost the same as A's?
Okay, sorry, what was the question? So you have two models.
What one is 10 times bigger in terms of parameters, but they both get the same accuracy.
On the training accuracy or the testing accuracy?
Let's say it's testing accuracy on some tasks. Is there a formal way to prove B's representational capacity is almost the same as A's?
Actually, I'm not quite sure what does it mean for representation power here in this context. So ideally, if you have a model with more parameters, then you will have a larger representation power. And then in this case, you say you are training this model and then you achieve the same testing accuracy. Then you're asking whether these two models will have different ability, right? Actually, I'm not quite sure. Yeah, possible.
Okay, Afra, if you want to refine your question, maybe think about it. Let me ask, so in your setup, what I'm wondering, first of all, let me point out that Changlong is another great example of theory possibly leading practice, meaning from this theoretical understanding, and it's also potentially giving insights about how to make a new method. He's not quite there yet to show us evaluation of that method, but I think what he's shown is a nice illustration of what it could inspire. So just a little side note. Now, in your setup, you have the concept class of true stuff. Now, I'm just wondering, about something. So one thing that could make that, the problem, as you pointed out, is, you want as many true factual statements as you can get, but it's sort of hard. You're always going to be limited by the size of that set. So, but one thing that we can sort of do is leverage the power of reasoning, meaning or some compositional model, let's say, but logic is the ultimate compositional model, you could say, meaning if you have some facts that you know are true, whatever size that set is, then reasoning can basically prove a whole bunch more facts that are also true.
Yeah, reasoning is actually one way to build the verifier. It's one way to incorporate the inductive bias into the learning process.
Okay, do you want to elaborate a little bit more?
So I'm not sure. So there are two ways you can incorporate the reasoning. One way is to incorporate in the architecture itself. The other way is to in the data, like what the people do in the chain sort reasoning. I think both of these will give you some inductive bias when you're training the model. So it will favor. So if you have some architecture design on the model class, and when you're training it, it will automatically favor the sentence that is more factual, more logically consistent.
Okay, and
this is a different way by designing outside the checker. This is a different way. Yeah.
Oh, so after as a follow-up. So so let's say they both model A and B have the same test results, okay, on some arbitrary cases. So we're talking about test accuracy. So how can I prove mathematically that these two models are equivalent somehow?
Okay, so let me look at this problem. So A has 10 more parameters than B, and both get identical accuracy on n different tasks. Either a formal way to prove B's representation capacity is almost the same as A. I think we need to first define what do we mean by representation capacity here.
I think he's asking, you know, I think what you're saying is capacity
ability, or
it goes with the size, the number of parameters, but he's asking, yes, but since they both get the same predictive accuracy, there must be some other quantity other than the normal kind of capacity measure that, you know, is there another quantity that captures more faithfully the fact that they get the same, you know, accuracy?
So I think what he was asking is, if you're testing on n task, whether it can, what happens for a different task. So I think the representation capacity will be, if you test on a different task, whether these two models will behave differently, right? If I understand correctly.
It could be. Could be.
Okay. I don't know. I don't know the answer.
Okay.
Yeah.
Okay. So, we're at time, but we don't have our next speaker, and
Okay.
I'm told we're trying to get a hold of him. So that could be that we wait, or it could be that we try to squeeze him in tomorrow. But any last questions for Changlong? Okay, I think what we'll do is maybe give everyone some time back. We'll provide the video later anyway for Sridhar's talk or tutorial. It's a shame, another exciting one, category theory. But anyway, and maybe we'll give it as a bonus after the panel tomorrow. Okay, well, thank you so much, Changlong.
Yeah, thank you very much for inviting me here.
We'll see everyone tomorrow, same time, and we have a very, of course, another exciting lineup tomorrow, ending in our finale, some great results in mathematics, and then finally our star-studded panel. Thanks, everyone. See you tomorrow.